Hi, and welcome to Remoticon. My name's Elliot Williams. I'm managing editor of Hackaday.
And I'm Angie Weiss-Gamel, and I've had the pleasure of being the event coordinator for Remoticon this year. What a great weekend we're having. We kicked off yesterday with the first 8 presentations, and today we still have 11 live talks ahead of us. All of this is streaming on YouTube with links and full details found on the conference website, remoticon.io.
This is day 2. Yesterday was fantastic. We've been having a really good time in the Discord channel. If you haven't found your way over there, there's a link in the description of this stream and on the conference site, remoticon.io, where you'll also find the schedule and speaker info. Please be good to each other. There's a link to the Hackaday Code of Conduct also below and also in the Discord.
This is the final day of the conference, but we'll go out with a bang tonight. DJ Jackalope will perform a live set this evening. That after party is immediately following the Hackaday prize ceremony, where this year's grand prize winner will be announced.
And don't forget the talks today. Today is 2 keynotes. We've got Keith Thorne coming up and Jeremy Fielding in about 7.5 hours after 11 more talks. So let's start this right up. Up next, I'd like to welcome Mike Stitch to introduce the first keynote.
Hello. I am Mike Stitch. I'm editor-in-chief of Hackaday. It's really nice to be back with you today, and I have the honor of introducing our first keynote. We can all sense gravity. So, all we have to do is like grab something and drop it. But really characterizing that becomes difficult. And like still air and a light breeze, gravity can actually fluctuate. And so scientists set out to measure this more precisely about 2 decades ago. And in order to do so, it takes things that are really large in scale, really low in temperature, really high speed, and of course, ridiculously precise. Oh, and you need some software to run them as well. And in this case, a custom flavor of Linux is part of that. Dr. Keith Thorne is a group leader at LIGO, Livingston Observatory. So LIGO is the instrument that's being used to make these measurements. It stands for Laser Interferometer Gravitational Wave Observatory. He's part of a team who is literally observing ripples in space-time, and I just can't believe how cool it is to say that. It's my pleasure today to introduce Hackaday Remoticon keynote speaker, Dr. Keith Thorne. I think you need to turn your camera.
There we go. Yeah. Okay. Thank you very much for that introduction. Oh, yes, I'm Keith Thorne. First, it actually has been about 40 years we've been trying to do this, but who's counting? Thank you very much. I'm actually here at the LIGO Observatory because someone set up the lighting so it works. And I don't have broadband at home right now due to a hurricane. Anyway, I'm going to start my talk, tell you about gravity and things that correct like black holes, neutron stars, and all the great stuff we've seen and how the interferometer is. And then about halfway through the talk, I'm going to change gears and tell you that we're hackers too, and all the great hacks we've done in LIGO to make this work. Hope it's a little inspiration to you that even we, big scientists, we do it too. So I'm going to go and get over to my presentation here. I hope people can see. And all we have to do is get this thing started. Okay, now I see it's being difficult. Okay, come on. Oh, come on. There we go. Start. There we go. That's a change the interface on me. Okay, anyway, talks about LIGO, extreme instruments for extreme astrophysics. So first, I'm going to take you through something about stars. And stars are always interesting because basically it's a fight between gravity pulling the gas in and something pushing out. So I learned in astronomy that a star is pretty much just a balloon that's inflated by the photon pressure from the nuclear fusion core fighting against the gravitational collapse. That's sort of neat. But what happens when the lights go out? When you've used up all the hydrogen and the helium and whatever? Well, it depends how big they are. If they're about the size of the sun, they end up being what's called a white dwarf. If they're up to 10 times as big as the sun, they sort of blow up stuff and then become something more extreme, a neutron star. And then if they're really big, they become a black hole. So what are these extreme things? Well, I'll mention with white dwarfs, we've seen them in telescopes. Basically, any star up to about 8 solar masses, you get a nova or a supernova. It blows off all the extra mass and gets down to 1.5 solar masses. But at that point, it's only 10,000 kilometers across. And in this case, the pressure is something called electron degeneracy. That means the electrons can't be in the same state, so they push, but they act like a pressure. We aren't detecting those with LIGO, though. But then there's something more extreme called neutron stars. And here you start with bigger stars, about 10 to 30 solar masses. They pretty much become supernova. They blow off all their other mass in a big shell, and they get down to like 1 to 2 solar masses. And they're much more extreme. They've blown all the electrons away. So it's just protons and actually just neutrons. All the electrons absorb into the protons. It's all neutrons. And it's only 10 kilometers across. And basically they get a very high spin, very magnetic field. And it's again, this Fermi, it's called Fermi degeneracy that keeps it from being collapsing. So those are pretty extreme. We've detected them. They're hard of pulsars, things like that. But you can get more extreme. Black holes. If you started at like 30 solar masses, you're going to collapse so fast, even the neutron ain't going to matter. And it's a prediction of general relativity that you're going to get down to black holes. And the collapse is so extreme that even light can never escape from the event horizon, which is about 30 kilometers or so, depends on the mass. That would be why we call it black. So it's a singularity of pure gravity. There are only like 3 parameters. It's how massive is it? Does it have a charge? Does it spins? So those are out there, but they're very hard to see, especially something that's black. And you can only see it when you have other stuff with regular telescopes, but we set out to do it. So I mentioned general relativity. You know, Einstein always comes in on this. So what did he say? The one thought Einstein had over 20 years ago was that you can't tell the difference between a gravitational force and the fact that instead of the force, if you think of like a sheet of rubber, instead of you being attracted, you have a big dump hole depression in the sheet of rubber due to the mass, and you're basically orbiting because space-time itself, in 3 dimensions, not 2, is bent. And as a reminder, you say, well, I never have to worry about general relativity. Yes, you do. Do you like your GPS telling you where to go? Well, if we did not correct for general relativity from the GPS satellites to the curvature of the mass of the Earth, they'd be miles off. So you get really lost. So, and here's a video to show you the mass also bends space and time. Matter curves space-time. Space-time then guides mass, especially in lighter masses. So for instance, we have this very massive object. A little one comes in, orbits around it because space-time is curved, not because it's a particular gravitational force. And so that's how it works. Okay, we get that in your head that you're warping space-time. But something else comes up that's exotic. Is what if you have 2 black holes? This isn't that far near each other. This isn't so far-fetched. We now, astronomers estimate about 80% of stars are in binary systems orbiting each other. And all such orbits decay over time, and eventually they're going to merge. That is, if they do it before the universe ends first, and many times the universe will end first. But what if there's 2 massive black holes eventually, using the big word coalesce? Okay, they just smash together and combine. At the end, They are orbiting at 2/3 the speed of light. These are objects that like 20, 30 solar masses. It's 2/3 the speed of light. And they're warping matter around them. So they're pushing space-time, the other one's pushing, and they're getting in the way of each other. And when they coalesce, we've observed 3 masses of solar masses of mass goes right to energy. That is, you started with something that was total 53 solar masses, and you get done, it's only 50. Where are the 3 solar masses of mass? Well, E equals mc squared, so it went to energy. Well, it didn't go into light. And what it went into is massive ripples in space-time. You can start thinking like you drop a rock into a puddle, pool of water, and ripples away. Okay, amplify that. And that's where all the energy is going. But how do you detect gravitational waves? Good question. So here's the only equation. We'll have equations after this. There may be another one. Okay, Einstein predicts this radiation. It has a funny thing, if you know about, there's like dipole radiation, like for antennas. This happens to be quadrupole. The only thing that really means is if you have a static object, it doesn't make gravitational waves. It's only you have 2 moving against each other that you get it. Acceleration. So we often express it in terms of something called strain, that is, how much is space-time stretched relatively. And we write these equations, funny numbers, but the important part of this equation, h, is at 10 to the minus 20. So it's 10 to the minus 20, that's a decimal point, 20 zeros, times whatever the mass of the object is, and that's divided by a solar mass, so times how many solar masses it is, times how far away you are, that is this r, versus 10 megaparsecs. So it dies off pretty quickly once you get far away, which is a good thing because it tear you totally apart. So in fact, what happens when you get to the Earth, and this is why Einstein really didn't care much, because you never detect it. It's really small at the Earth from these objects. Okay, those zeros. Okay, meter to a tenth of a human hair is about a factor of 1,000,000. You divide that by 1,000,000. Divide that by 1,000,000,000. And you get to 10 to the minus 21 meters. Amazingly small. So that's why I said, this will never work. Don't worry about it. You'll never be able to detect them. You can't make a telescope to see this. But apparently some scientists had other ideas. First one was Ray Weiss. He's one of our Nobel Prize winners. He was also one of our first hackers. One thing about his background, back in the 50s, he used to build audio circuits and sell them that would clean up the pops and clicks from the early hi-fi records. So he was doing his own circuits, how to filter this, and knowing how to do this helped him. But in this case, he actually assigned this as a homework problem, of course, to design some sort of interferometer, because lasers had just been invented 10 years ago. So laser interferometer is actually the ideal thing to use. But it took us about 30, 40 years to figure out how to do it. So here's interferometry 101. And you even do that when you use laser rangefinders. It's the interference between one light wave and another. You send the light wave out, you split it in 2 pieces, it comes back together, and it's the interference between them. And so if you change the arm length of one, the light no longer perfectly cancels. There's imprecise cancellation of the waves. Now, if you're using white light at about, it's 100, you can do about 100th of a wavelength, or about 5 nanometers, 10 to the minus 9 meters. Lasers, you can do a lot better, because laser light is coherent. Fancy word for saying it's single phase, goes up and down coherent at the same time, and has one frequency. So if you control that intensity, the frequency, you can get much, much smaller, what we call displacements. You can measure much smaller distances, but you have to control for the vibration and everything. So that's basically how the LIGO interferometer works. And I'll take you through a little picture here, and you're allowed to go to sleep if you're not invested in fancy design. But we start with a laser. right now we run about 40 watts is the initial laser. So we do that and we get the 40 watts and then we recycle it. So you start with 40 watts. We have what are called mode cleaners that remove all the things that aren't the one frequency light we want or scattered light. So we clean it. We have a recycling cavity. So now we've built up the power, and the power matters because that helps you with something called shot noise, which we'll talk about later. So you want as much light as possible. So we're up to 5 kilowatts just in the input part. Now we create something called a Michelson interferometer as we split it and bring it back. And interesting, we always pretty much redo. The Michelson interferometer was used back before the start of the 20th century. You just add it to figure out that there was no luminiferous ether. Say that 3 times fast. But that was the Michelson Morley's. Basically, there's no stuff out there in space. It's just a vacuum. No preferential direction. So we do that, but then we make it better by having these arms called Fabry-Perot arms. Now, the LIGO interferometer is pretty big. Those arms are 4 kilometers long. Pretty big. But you can make it better because you make it resonate, bounce back and forth with a half silver mirror almost 1,000 times. So instead of it being 4 kilometers, it's 4,000 kilometers effectively. And that helps with your precision as well. So, and also you're up to 750 kilowatts of power. And we'll come to that later. So then at the output, you bring it back down, you have more power, and they have this little thing called an output mode cleaner, which is only a box about this big, we diffuse silica glass, and we heat it a little to slightly change the resonance. So that's sort of the layout of it. And I won't go into too many details. We could go on for ages on that. But first I want to say, how extreme is the LIGO interferometer? Okay, I said 4 kilometers long. That means you can see it from any airplane. You can see it from space because we have tunnels with concrete and they go out 4 kilometers, either through a desert or a swamp. Okay, so here's where the precision part comes in. We measure things to 1/10,000th the diameter of a proton, the one in the nucleus. That's how small that distance is that we're measuring. And you should go, how can you do that? Ooh, very careful. Okay. But you get very insane sensitivities. Like we have these resonant cavity has mirrors, which because we're physicists, oh, that's not a mirror. That's a test mass. And the reason it's a test mass is it is the thing that feels the gravitational wave. And that's what we're testing is the distance between them. And it's about 40 kilograms, 80 pounds. If you get a little laser, your little pen-like laser, the photon pressure, not the heat, the little photons bouncing off the mirror are enough to control that. We can use a feedback loop. That's how sensitive the controls are. They're like nanometers or whatever. Now, when you get such an extreme control system to take out all the motion of everything, we've measured that it damps everything so well that those mirrors get to a ground state motion that's equivalent to 77 nanokelvins. There's in this dimension, there's hardly any motion. And they don't freeze. It's what their effective motion is. So that's how much we've isolated them from everything around them, which is very impressive because they're bolted to the earth, right, with suspensions. So isolating from the earth is a real challenge. Other extreme things. We use ultra high vacuum, 10 to the -9 to 10 torr, which is more extreme than outer space. But what's really extreme is how much of a volume we have. Well, the volume we have is basically the same volume as the CERN Super Collider's pipe. It's the largest volume on Earth at ultra high vacuum. In fact, we have parts of our tube, and our tube that goes out along the arms is 1 meter across, 3 mil stainless. Those arms have not been up from vacuum for almost 20 years. which is a good thing, because if we popped a hole in there, it would take us 2 years to pump them back down. So we're a little insanely crazy about our vacuum system and valves. So that's how extreme the LIGO interferometer is. But when you do extreme things, extreme instruments, you can do extreme astrophysics. Here's our latest catalog from what we call the stellar graveyard. We got about 90 mergers, mostly black holes, but some of them are neutron stars. We've seen 2 or 3, and those are really great because other telescopes can see them. We've even seen odd things where it's a neutron star and a black hole. And we're rewriting a lot of science because we're seeing things a lot of theorists predict, well, you shouldn't see anything in that mass range. And we're like, au contraire. We saw it. You're going to have to rewrite your dang theories. Sorry, our bad. So that's after our initial runs, and we've been ramping up in performance. But I do want to talk about this neutron star. The reason this is interesting, almost all the events LIGO sees, LIGO and Virgo are the only instruments that can see it. So you can imagine there's a lot of convincing to tell people like, sure, you saw those black holes. I'll sure. No one else saw them. How do I believe you? Well, the belief was finally said is we saw this binary neutron star that was pretty close. And when we predicted where it was with LIGO and Virgo, the gamma ray observatories, Fermi also saw it a couple seconds after we saw it. And then the optical telescopes went in and said, yeah, we can figure out, go back in the plates, and yeah, there's a big thing that went. Neutron stars have an optical thing. You can see them in telescopes and X-rays. And so they could see them. So we said, good, you finally believe us now when we tell you we're seeing something. But we could do some really great stuff with that. One thing is, I want to impress on you how different gravitational wave detectors are versus regular telescopes. Electromagnetic telescopes that you're familiar with, big dishes, things like that, you can focus photons, you can focus light. So they're very good at angular resolution, but they're really bad at measuring distance. They can tell you it's over there, but they can't tell you where is it, how far is it. And so they have a very complicated scheme of Cepheid variables and various things they know how much they should have in absolute brightness. And so it's very complicated to measure something called the Hubble constant, which is how fast is space expanding. There are 2 main measures they've done. They don't agree at present. The error bars don't overlap. Now, gravitational waves can't be focused. And so we don't have much directionality. It's not a dipole, it's almost uniform in distance. We use timing. So we have to use like your ears to tell you if you've multiple detectors. So it's the speed of light delay tells you which way is it coming from. So we have poor angular resolution, but we measure an entire waveform, the waveform, gravitational wave waveform, as the things go together and go smack and go down. Because we measure all that, and general relativity tells us, well, the ups and downs of that tells you how big the thing was. Well, then we just say, well, how high is that? Not the shape of it, but how much the apparent intensity is. We're great at measuring distance. Every collision tells us how far away it was. So we're great at measuring the Hubble constant. And we'll get better. And here's a comparison. Latest measure from LIGO. If you look at this plot, you'll see that there's the Planck and Shoes are the 2 optical optical measurements, and they don't agree. Those are like error bars. One says, oh, about 76. One says, no, it's like 68. But then even from our first neutron star, the black one, we could measure it. And now we can take our black holes, add them all together, and the blue is the latest one. So we're getting competitive. We're favoring one particular measurement, but there's an uncertainty there. So we hope when we get more, we may help resolve this whole issue. So, okay, told you all about our great discoveries. We'll be doing more, but I want to switch gears now and tell that we do hacking too. Just to let you know, not the only ones. why do we do this? The LIGO staff is quite so. The lab itself only has like 180 people. We have a lot of customers, but there aren't that many people working the instrument, but they're very clever people. And we're always solving novel problems not seen elsewhere. There's no Acme interferometer company you can order stuff from. And because we're doing taxpayers, we use a lot of off-the-shelf hardware as much as possible. And so to make the precision, we've had to do several hacks. I'll give you a few examples of those. We've had to do software hacks, electronic hacks, mechanical hacks, and quantum mechanical hacks. Okay. And I like to do this because I don't really get to talk about this much. So what was the first software hack? And Rolf Bork and Alex Ivanov came up with this. I just use it. Okay, the real hack was, how do we do hard real-time computing? And what does hard mean? Well, first, why do we have to do it? We use what's called digital filtering to control the interferometer, feedback loops, high-pass filters. So you're running at a certain frequency and sampling the data. Okay, we've gone with off-the-shelf computers so we can change rapidly and ride Moore's law to faster performance. We used to have very custom computers with insanely expensive compilers and stuff like that. But Linux was coming on recently. So now the standard real-time operating systems, real-time Linux, things like that, they're pretty good cycle times, but they have this tail. And the tail is what kills you. There's a long tail of rare cycles up to 1 millisecond. The problem is the LIGO control loops have to go from reading an A to D converter to outputting a D to A converter for the control at 64 kilohertz, at 16 microseconds. And we can't run long, that is skip a cycle for days. So that's hard real time. So the question was, how do you do that? Okay. We use a trick. The trick is, run your code on one of the idle CPUs. Now that you have computer CPUs with multiple cores, you can flag one of the CPUs as idle so that the OS won't use it because you're saving energy. But the trick is, you load your core as the idle loop on that processor. I mean, it's powered up, you don't turn it off, you're running. It's just the OS doesn't know you're there. And you don't get interrupted. If you work hard, you have to work very hard to turn off all the interruptions. In the original hardware, we had to turn off, you can't let the computer slow down, none of that energy savey stuff. No hyper-threading, no turbo mode. We had to turn off the USB ports on these things, PS2, because that generate interrupts. And you have to tell the operating system, no, don't knock on the door to see if we're awake or not. So we got that to work. And it's interesting when you did that, because we were doing that and we were using PCIe bus reflective memory for co-located to exchange data between computers. And we were using GPSs. And when we came up with this, we were asked to talk to a bunch of Linux gurus in Germany. I'm like, why is that? Then we found out the other people who want to do something this extreme. Fast stock traders. So I sort of feel bad that after we show them this trick, that we're going to be the responsibility for the next flash crash. So that's the trick we've used. Now, and you make the software very simple. It isn't one of these multiple loops with threads. Single thread. It's very simple. All it does is it sits waiting for a trigger that the ADC sees some new data, reads the data, updates all the filters, puts stuff out in memory for the D to A converters, and just goes back to the top. That's all it does. Very simple. Now, it has to do other things like put out data for other things, respond to user inputs. And so what you do is you spread those in tiny pieces across the 64,000 cycles per second, small enough so no time does it exceed your 16 microsecond time budget. You have to run in kernel mode, which means you can't do those nice math libraries. If you want math, you got to write yourself. And you can only communicate through memory buffers. So you have to have, and you hand off the memory. And so you use DMA, direct memory access, a lot. So you just put it there and the ADCs, the D to A converters pull it out, or the ADCs put it there. That's how you talk to all the other process you have that aren't real time to talk to users and export data. So it worked. We had another hack, same people. It was, how do you write the code? The amount of control software we're going to need for like 100 different processes, which is way more than the 2 people we had. You can't be sitting there overnight and trying to look at requests from users and write it. But it turns out it's all very similar. It's all got one filter. We use very standard filters. It's all how you package them and run the wire. So it's like a circuit. And in fact, it's a circuit. So if you could write a code generator, if you could get something that described this and you wrote the code based on that description, then you could, if someone just changed the description, it would write the program. But people want to write down, but what you really want is a graphical one. That is, you want the users to write the code for you so they can draw it out. And okay, you could write your own graphic package and do all that. But we were already using MATLAB because it has all this great stuff for digital filtering. So, but it had this other thing called Simulink, which we didn't really use. It sort of wasn't working well, but it's a great drawing package. So if you make your own parts be the filters, you put them in the diagram, and you write a parser for that file, you use that to build the code. So you save yourself writing your own graphics package. And we've used that. And so now the users can change the code whenever they want. And all the programmers do is maintain the code generator. They don't do the individual programs anymore. Those are 2 big software hacks. So typically, here's part of one, or typically complicated. So they drew all this and you parse it. And they can put comments and lots of crazy colors. So, but they also documented it. So those are software hacks. We had to do electronics hacks because the major problem we have is noise, electronic noise. Anything that is there, persists for a while, will show up in our data. So we have to eliminate a lot of noise. So things we did like switching some power supplies, you got to use linear DC supplies. And then we even put them like 50, 80 feet away in another room. So you can't see the switching noise on the digitizers. The computers that you have running flat out are noisy as heck. Oh, they're in yet a different room and use a fiber interconnect to connect to where the digitizers are. But there's even more subtle things. We find out that you often want to synchronize your digitizers. So you have a clock signal going into one ADC. You read the edge, sharp edging edge, you're all locked. You can't do that. You have a sharp edging edge in one of these ADCs, they're synchronous ADCs, you pick it up on the other channel and you screw up everything. So you can't have sharp edges. And so, because everything's you're doing analog, you're taking analog stuff, digitizing it, putting out back analog. So what you do instead is you make something called a duotone. You have 2 oscillators at 960 hertz, 961 hertz. They have 1 hertz beat signal. You fit the waveform to figure out where it crosses at the beginning of the second. And that's what you use for your 1 pulse per second timing signal. And then we were finding that we were getting 2 hertz and half hertz signals. And they were because there were LEDs, nice blinking LEDs telling you the timing system is locked. Well, but they're running all the time and they pull down the ground plane and you pick those up. So in one case, if we change the code, so when it's happy, it's constant. In some cases, the vendor says, no, they're going to be that way. That's how it is. So you just pop the LEDs off, little surface mounts. Another thing is we had photodetectors. So we're trying to pick up infrared light and we weren't big enough to get ultra custom infrared photodetectors, but you can make a infrared photodetector pretty easily. You get the can that the photodetector's in and there's a lens on it, optical, you cut the lens off. So your engineers get very good at cutting lenses off photodetector cans. Okay, then we have some electromechanical hacks. A fast shutter. Remember I told you there's a lot of power there? We were finding out when we would lose the lock, the power goes somewhere. We found it was burning holes in the substrate of the photodetectors. So we needed a vacuum shutter. Now, it had some requirements. It had to go 6 millimeters in 1 millisecond and block 45 joules of energy. Now, going 45 seconds isn't so hard. 6 millimeters, that's like an arm on a disk drive. We started looking at those to begin. But you had to be a little beefier because of the 45 joules of power. And so they came up with this thing that bounces up. I'm going to show this little video. And you'll see it goes, should trigger, go bounce up. Okay, now that's really slow. Well, that was because we used, now to get that video to make sure it was moving fast, okay, we did have to use a $500,000 camera to do this video, but it didn't work. That's what you're doing here at Caltech. Someone's got one of these cameras. So you have to design one of those gizmos. And that gets us to mechanical hacks. We have to fight vibration. We see all of these signals, we seismometers. Pretty much all the data that we do from LIGO is to tell us that it's not a gravitational wave, that it's a passing truck, that we see that the truck moved and it got into the interferometer and things like that. And so we have all these seismometers around and we're trying to figure out what the problem is. And we are finding a particular signal at about 30 hertz. And Anna Maria Effler and Arnaud Pele found this. It's use seismometers and you like turn HVAC on and off and what is causing it. And they isolated it. And you'll see this picture here. Now the graphic shows it before and after. You see this picture, that's a spring-loaded mount for an HVAC fan. Now you may see that circled thing. Now you may think that's a rock. That's a mechanical short if you ask a mechanical engineer. Okay, it's a rock. So we had to find those. Another mechanical hack, we have to damp things that are flexing. And so you have this thing that's vibrating, you're picking up that vibration. So you want to have like a tuned mass damper or semi-tuned. And so there's a lot of creativity. It's got to be in vacuum. And so one mechanical engineer came up with all these designs of different pieces of Viton with cable ties of different designs that would work. And much testing, he said the poofy hat worked. And now the Hawaiian, hat sort of worked, except it probably drooped. So yeah, we don't use cable ties, use something ultra vacuum. Brian Lance came up with this. So that's one of our hacks. So another one was cryobaffle dampers. Recently, you have a baffle to baffle light, but it's inside the tube and it's bouncing around, and you have something called eddy current dampers for the slow stuff, but not impulses. So what do? Well, you get more squidgy bits and you put them like back up against each other to keep the thing from bouncing. Arnaud came up with that one. And the final one are acoustic mode dampers. It turns out we had a problem that the mirrors do vibrate, like they have drum modes. And if that frequency is the same as a resonant frequency for the optical system, you get runaway, amplification, parametric instability. And we had a whole system to do that. But then a really clever mechanical engineer, Sebastian Biscan, came up with, use tiny little piezoelectric dampers designed for that frequency range, and they oscillate the other way to help damp it. And here it is, this tiny little thing glued onto the side of the big mirror. And the only difficult part is you wanted to make sure it didn't fall off. So it was you had to go in there and like push it and glue it on and make sure you have glue that's not going to come off. So last hack, quantum hack, squeeze light. This is our noise curve. It's logarithmic in frequency, logarithmic in strain. And it has pretty much all these curves have something at the lower frequency, sometimes 1 over F noise, but it's a combination of things here. And then it goes up at high frequency. And that going up at high frequency is often called shot noise, Johnson noise. It turns out that's a quantum effect. The effect is that because light is quantized, oh yeah, Einstein said that too. Because it's quantized, as you go up in frequency, there's only so many photons. And so you have smaller and smaller boxes when you're measuring the waveform for a photon to be in. So depending how bright the light is, you don't digitize it too well. So you have big uncertainty in the intensity or the phase. And so this is sort of, it limits how well you can measure things. And so it's only limited by how much power you can use. And now this other thing called radiation pressure at low frequency, but we'll worry about the shot noise. And so you can fix it by cranking up the laser, but you crank up the laser, light now bounces everywhere, it gets back in, screws you up. So what you really want to do is beat that shot noise, push down without raising the laser. So how do you do that? You do that, if I can get this to go. Okay, so I wanted to advance. Okay. All right, let's try this. There we go. Okay. Now these vacuum fluctuations, and here it's getting a little deep, so I'll try and make it quick. This quantum noise is actually from quantization of the electromagnetic, something called a 0-point fluctuation. But the important part to note is it's the Heisenberg uncertainty principle coming in here. The things we want to measure out this light is the amplitude, how big it is, and the phase, where does it go up and down? And in fact, in this thing, we really care about the phase because that tells us how long the arm is. Now, in normal uncertainty, you have these two variables. The joint uncertainty of them is always has to be greater than some sun. So you get this circle between x1 is between phase and amplitude. So circular. And so on average, you can never get better than a certain precision in phase or in amplitude. And so that sets the limit for shot noise. But what if it isn't a circle? And so what the hack is you use something called squeezed vacuum. Yes, it's getting pretty deep here. But the important part to you is we take the light, we basically measure how the light's going back and forth, and we rotate the uncertainty. So it's no longer symmetric. Then in fact, we take this, the area has to stay the same. So we squeeze it so that all the uncertainty is in the amplitude we don't care about, but there's much less uncertainty in the phase, which is what we do care about. And so when you do this, you can beat and improve by several dB, 6 dB or so, that uncertainty. So that was our quantum hack. So that brings me to the end of my talk. But I just want to say thank you very much. I'll take this. I think we want to maybe have some questions after this. So let me stop my share.
Spectacular presentation, Keith. Thank you so much. Can you hear me?
Yes, I can hear you. I'm waiting.
Oh, great. So we have a ton of really good questions in the channel, and I'm going to get to those, but I have one on my mind that I'm not really able to reconcile. Can you describe like the speed of the gravitational waves? Like I know you run the installation for a long period of time.
Okay, that's actually a question. And one thing I didn't put in here is a lot of things that we said about general relativity by measuring these gravitational waves. And the one thing we did with that neutron star detection is the speed of gravity is the speed of light. There's a lot of alternate theories about general relativity. They say it goes faster or smaller, but because we saw the signal with our detector and the gamma ray burst people saw it like a second or two later, basically over that great distance, gravitational waves move at the speed of light. And I improved it, which actually threw out a whole bunch of crazy theories people came up with. Does that answer your question?
Yes, absolutely.
It's at the speed of light, like everything else.
Another one, these are in no particular order, but they are all interesting questions. You mentioned putting the test masses, making them extremely cold, and isolating.
They act like they're cold. We aren't actually freezing them. That you've reduced their vibration so effectively, but you aren't actually like chilling them. So they say as if it had the amount of residual motion of 77, as if they were that cold.
Right. And
but
then
mostly because we're damping them.
Yeah, and isolating from seismic effects. So you showed some of the dampening for that. But the question is, do you have to account for Earth's motion?
Oh
in
yeah.
this?
What we have to adapt for the tides, believe it or not. That the tides move stuff. So we actually have a slow loop that adjusts for the tides, adjusting our thing. So we don't have to, the Earth, so it's mostly the tides we have to correct for. So we have a loop, a very small, slow loop, you know, for every 12 hours that adjusts the tidal motion that affects the length of our arms. So yes, we don't have to correct for the Earth itself, but for these effects from the tides.
That is wild. Let's see. You mentioned damping the mirror, and there's a question on that a little bit. So the question was actually on the runaway amplification mode
Right.
that
It's okay. What's happening is there's optical frequencies in the interferometer, and you get energy in that. And the problem is if they're over here, then you can damp them with one way. But then you have a physical mass, and physical masses have drum modes. So they go like this, and they go like this, and that. And if the mechanical mode lines up with the optical mode, as you heat the thing up, and that's what amplifies mechanical mode, you cranked up the laser, then it's right at the optical frequency. So the problem is that you can't damp this optical one anymore because you're hitting it with the mechanical. So there's various things you can do. If you heat you can change the temperature with heaters of the mass, and so they don't overlap anymore. But in some cases you can't. So it's called a parametric instability because it's a runaway feedback loop.
This one is a question on the waveform. So the question is, I didn't quite get how the distance is embedded in.
Well, the way the distance is embedded is you do the theory, if it's this big, the waveform, it's the variation of how it goes up and down and the time. Okay. So I could show, but basically if it's more massive, it takes longer. And we do the fits. We measure the waveform. Well, for neutron stars, we measure for like 20 minutes, but we measure it for a second or so. That extended waveform, if you solve what equations, what will it look like when it goes together? What will it look like? And it's the ratio of how fast it goes up. Does it have some extra bits in it? How long is it between each part in time? And the relative heights. And that, when you solve the equations, that will tell you that was like a collision of 30 solar mass star with a 10 solar mass, black hole. And either they were spinning or not, you can have some information on that. The more precisely you measure that, the better you do. So it's the shape and timing that matter. And then the absolute signal you see here at the Earth tells you and when you do the equation, it tells you where it occurred, what the absolute magnitude is, which is way more than here. But then how big is it when it gets to here? And by that 1/r, that tells you how far away you are, how much it's decayed away.
Another good question. The hard real-time system that you were talking about, is that available? Is the code for that available?
It's actually quite simple code. I think we've put it on our remote code. We've just put it on git.ligo.org. I think it's mostly public now. It's actually pretty simple. You just put a hook into your code. But yes, it is. We've been trying to make all our code public, not just because but we're going to be working with people in India and whatever. And so, yeah, there's a git.ligo.org, and I think there's a public part of it.
And we'll work on putting a link to that in the.
Yeah, we can do all that. We're trying to make it also, we have a lot going on with packaging, so it's much easier for people to install it for test stands and things. The other piece you have to do is these memory buffers, because you have to put things in. So there's a lot of tricks, but it's all in there. But yes, we are trying to make it all public. I think we currently use a custom version. We take a modification of a real-time patch to Debian 10 right now, working on 11, but we've used Gen 2 before. Eric.
This is a question about geology, and I actually had a
Okay,
question.
I can do that.
As well. So two things. The first one is, does geology of the location of LIGO introduce things that have to be corrected for? And the other one is, can you
Yes.
talk about that? There was a band on the globe when you were talking about locations, and talk about what that band is showing.
Well, that band was, that band was an uncertainty. I think we can go back to that. But first, geology. Yes, we're in a swamp. And so, and we're close to the ocean. So in fact, we had to put in more seismic isolation here at our site in Louisiana to damp out. We actually were planning it for both sites. We actually put it in here early. So where your site is matters. It's actually more seismically quiet in terms of ripples from like water and thing in here, but in the high desert of Hanford, they don't have a problem with the ground moving, except for those earthquakes. But they also have a problem with wind. They have a much higher wind velocity. And the problem is wind will take these buildings and tilt them. And so they've even started erecting wind fences on these build across buildings so they don't tilt. So now below you, it's pretty simple. Geology does affect you. Part of the low frequency problem is you aren't on a flat Earth. The Earth is curved. And so as you go to low and low frequency, you're probing farther and farther distances on the Earth in terms of mass, and it's falling away from you. It's something called a gravity gradient. And so because we're on the Earth, that affects our low frequency performance. And I've probably forgotten the thread of the rest of the part. So it's geology. And what was the second half of the question?
Oh, you already had the band on the.
Oh, no, the band on there is, it turns out if you only have 2 interferometers, that's why you need 3. You can get an uncertainty, like a ring uncertainty. As you have 2, and you can say it's like here, 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 here. So part of it is you needed to have, I have to go back to, let me go look at that one. There are several bands, but that may have a different band. I remember that graphic.
I think it was the neutron
See
star.
here. Well, I can describe it. Okay. That was actually an uncertainty from 2 instruments.
Ah, got it.
So that was not actually LIGO. But we do have, that's why we need 3, because you have 2, you can get an uncertainty. And so you need a 3rd instrument to say, and you get something here, but like you can't say if it's down here or up here. So a 3rd instrument refines it. That's why you really need multiple interferometers. But I think that one was because they only had 2 instruments and they could tell a distance. And so the ring was the where on the cosmic. Actually, it wasn't the Earth. That was actually a picture of the celestial.
I'm going to combine 2 different questions here because they're kind of deal with shielding.
Okay.
One of them says, you mentioned the computers are in another room. Are these shielded with copper tape or something more exotic? And the other question is there anything specific with electronics to protect against cosmic rays and electromagnetic radiation?
Yeah, there's been some thing of that. We don't do too much copper. I mean, what we do is we use linear power supply. So you have a big like locomotive cable, right? So you want to reduce that. That's for the DC power. The thing from the computers is there's electronic noise, but it's actually acoustic. Because they're running flat out. And in fact, we have racks of electronics that are somewhat near the interferometer. We've had to put, it's not just the electronic noise, it's the vibration doing the concrete slab that's separate, but it gets transmitted through the foil. And so we put in rubber things that are just the right, so they aren't compressed and they aren't just rocking, just enough so they damp out this vibrating rack of electronics. I'm not sure I answered that question, but the copper, I'm not sure where the copper would come in.
Like putting computers in another room and then shielding the room, I think.
Oh, yes. We have thought of, we are going to do this. What we're going to do, we think we've got the noise of one of our most critical digitizers. We're actually going to try that. We're actually going to put it in its own box and try to making a Faraday cage is actually very hard. If there's any aperture, the waves will find it in. It's really hard to make a foolproof Faraday cage.
I would like to give you some feedback in saying that you were wondering if the hacks would be well received, and someone was asking about quantum squeezing before you got to that, and then they're like, yes, quantum squeezing, I love it.
Yes, and we're doing a little more now. The little detail, because I didn't want to take up time, that squeezing that I showed you is frequency independent. It's the same. And it turns out that what happens is when you squeeze at high frequency, it helps the high frequency, but you don't get something for nothing. And so the problem is high frequency gets better, but low frequency gets worse. And it is sort of impinging on the low frequency. The way you can solve that is by having another resonant cavity that rotates it so there's no squeezing at 0 frequency and full squeezing at high frequency. But to do that, you have to make a 300-meter long cavity with a vacuum tube this big. So we're doing construction right now to go out, 1,000 feet out across the swamp with concrete and a thing to make another optic there. So that's part of what we're doing why we're down, is putting in this enhanced squeezing so that we can squeeze much harder at high frequency, but without affecting the low frequency, getting this back reaction.
I really enjoyed hearing about your software hack for connecting MATLAB up to.
Yeah, it'd be nice if they stopped changing the file format. They're almost, I think they were, it wasn't so bad. They went to XML. I think we're going to have to figure out how to parse their XML. Because they've changed, but that's what happens when you aren't writing this software.
Other huge, giant, amazing installations that are looking to have an interface for the scientists. What has the feedback been from the people that are using that system?
They're familiar with Mac, so it's great because we also make it so they can generate the software. They just design it. We give them here's how you build it. Here's how you make it. And they just do it. And here's how you restart the DAC. Otherwise known as don't call me. No, here's how to do it. You can do it. And they think it's great because they go in, they change it. Oh, I want a different thing. I want to add these things. They add that in, they rebuild it, they restart it. Now, other places use Virgo. The one in Italy uses digital signal processors. But of course, it's a much smaller community that can write those. And so you don't quite have the same ability to do it. No, it's outsourcing code creation is a wonderful thing. But no, I don't think we could have done it without it because there's just, let's say you have 30 scientists doing it. You'd need an army of programmers, right? And they don't have to write any software. They occasionally write some C code for some special thing that they want to do, but pretty much it's just wiring.
So I think just one final question, and when you were talking about the laser and you said you had a 40-watt laser, off-the-shelf laser, and no, it's a very custom design laser. It's actually the current one. It comes from an outfit in Germany called Neolaser and Hanover, and we're doing our latest one. It's actually a series of lasers, and in fact, it starts with one, and then we have pumped light that goes in water-cooled things over to a room, and it goes to an amplifier. So actually, the amplifier would get up to 70 watts. And the only reason it's at 40 watts right now is we're having trouble with these mirrors. These mirrors have like 14 anti-reflective coatings, another custom company that does that. But the problem is they get schmutz on them. We have found when they're manufactured, they can get little particles, tiny little ones. They're no trouble when you're illuminating it. When you crank up the power to kilowatts, bang. And so we have bad spots. So we've had to steer the light away. And so there's a limit. We can't go above 40 watts right now. But it's actually a series. You start with an N-Pro laser, and then you go through a pump laser and switch it back to infrared, 1024 right now. And then you go through an amplifier, all custom, to get up to actually go 35 watts and then to 70 watts. So yeah, that's all very custom. Well, this has been such a pleasure today, Keith. Thank you so much for speaking. And I think I speak for everyone. That was a wonderful talk, and we're happy to have had you here.
And I'm glad everybody show all your interest in LIGO. Of course, remember, we have hackers, so we may even be hiring. I think I saw 11 openings last year, 13 openings, because a lot of us are getting old. And so we're, in retirement, which is good, but we need new people. So, but it's going to be a little bit, you have to fight against SpaceX and Tesla and all the other great stuff everybody's doing. So, but thank you very much, everybody. I'm glad everybody enjoyed it.
All right, we will be back after a 5-minute break with our next talk from Arsenijs.
Thank you very much.
Welcome, Arsenijs. If you want to test your audio and video, that'd be great. Just remember that the feed can hear and see you.
Hello.
Hello. I can see you. Do you want to say a few more words?
Yeah, sure. It seems I can hear you.
Audio is coming
I'm
through
on.
just great.
Sorry?
Audio is coming through really well.
Okay. Is the image choppy? I should probably check the YouTube live
No,
stream, or maybe not.
it seems really good to me.
Would you be okay with testing out screen sharing?
Yeah,
I would.
let's go ahead and do that. I'll just stop the sharing that's happening right now. All right, you can try your screen share now.
Yeah, which screen is it going to? Which screen is it going to? Okay.
Yep,
Now,
I see your laptop reuse talk by me.
does it scroll correctly?
I believe it does, yes.
Wonderful. Thank you very much.
Great. All right, if you just want to mute your camera and microphone, we'll be back in just a couple minutes.
Thank you.
Hello and welcome back. I would like to, say the obvious thing that e-waste is a really frustrating problem. And I think it's not hard for pretty much everyone to see that there must be a better way for us to deal with this. And while, efforts for better manufacturing and recycling plans are improved, people like Arsenijs, our next speaker, are taking a shot at reusing component hardware to extend its life and, keep it out of the landfill that way. From batteries and webcams to motherboards and chargers, he's going to take us through his approach to repurposing the functional components from otherwise dead equipment. I'm happy to welcome our next Hackaday Remoticon speaker, Arsenijs.
Thank you. Okay, seems like I can start now, right?
Yes.
Thank you. All right. So I'm a bit nervous, haven't given a talk in a long time. Thank you for the opportunity. And I don't quite know why any of you specifically are here. I know some of you are here because you have just a few laptops that you would like to take apart and reuse. Some of you, maybe like me at times, you're on the budget and you just need parts to do all kinds of different projects. And maybe you're just looking to upgrade your daily driver laptop to maybe make it work better for your goals. But there's a high-level principle for me on why I do this. And the reason is that I believe that in the future we might have to, some of us will have to build more portable devices on our own. Currently, laptops and a lot of other devices are moving into the becoming more proprietary direction. And on the opposite side, we have values like repairability, like privacy consciousness, like waste elimination, and all of these are clearly conflicting with the proprietary direction we're currently being taken in. And that means we will have to at some point take matters in our own hands. One of the ways we can do that is through reverse engineering, and I would like to sort of equip you with a toolkit on how specifically and what specifically you can do. Because, until you have the toolkit, maybe you don't even know what's possible for you. Hopefully that explains my motivations, and now time for a bit of an info dump. So I should be sharing the screen now. And I have to select which one is it. Does it work?
Yep, looks good from here.
Okay, you can see the slides on the screen. Slides on the screen, I assume, right?
Yep, we can.
Yep. Okay, so the obvious parts I'm not going to be talking, and that's sorry, small hiccup. So hard disk drives, SSDs, RAM, I'm not going to be talking about reusing those. What I will have a side note about is that you can actually reuse USB Wi-Fi cards, Mini PCI Express Wi-Fi cards with built-in Bluetooth as high-quality Bluetooth dongles, which is probably the best quality Bluetooth dongle you can get. And the simplest option is that you just solder wires, USB and 3.3 volt power, and you get a dongle that, unlike the cheap dollar store dongles, it doesn't break as those dongles do. It has decent driver support, and with antennas that you can get from the same laptop, you get quite a bit of range compared to those dongles. Further on, if you go into the laptop hacking, you will need schematics. You will hugely benefit from schematics. You can find schematics for your own laptop or maybe similar laptops online. And board views are also useful. If you cannot find schematics, it's good. It's still good. You can still do a lot, especially given how many schematics there are available online. But it's better if you have those. So displays, you can definitely reuse displays. Older ones follow the LVDS signaling standard. Newer ones follow the EDP standard, which is embedded DisplayPort, which basically means that the simplest and the most powerful option you're going to get is to solder a DisplayPort cable into a laptop panel and plug it into your GPU, which is unironically an option, and I don't know why more people don't take this. But either way, you will need backlight connections, which usually backlight needs 12 volts or whatever's the typical battery voltage around that. And also you will typically need 2 logic level signals. Enable, which is a logic level signal, and adjust, which is a logic level PWM signal for brightness. If you use a CCFL panel, which is like old backlight type, usually LVDS, you will need an inverter. You can typically reuse a laptop inverter, and yeah, same connections as the LEDs. It's straightforward to reuse everything, but you can also buy an inverter. Typically, if you want to reuse a panel, you can just take the model number, plug it into eBay, buy the $20 kit, and you go. But if you would like to actually know like everything about the panels, or maybe you want to reuse it in a power efficient way, or maybe you want to make a really slim project, I've been building a knowledge database. It's like 30% complete, currently on hold, but there's already a lot of information on how you can actually understand the display uses intricacies. And I've been also compiling a Hackaday IO project list, also links down there, so you can look through what other people have been building. Oh, this is just an example of a project that I'm actually, at this very moment, I'm using for the streaming. So it's a second monitor that I'm currently using. It cost me $50 in parts. It's a touchscreen IPS Full HD monitor. It's very high quality, and currently it's my best second monitor. I've also, in that project that I've mentioned, there's a build log on how I reused like all the parts for this, and some other build logs. Okay. A lot of devices inside laptops are USB devices. So mostly these are touchscreens, webcams, fingerprint sensor. So what this means is that they are typically plug and play, and it's very easy to just have them work. Sometimes you need drivers, and you need to supply typically 3.3 volts, sometimes 5 volts. You need to be careful on which one the device needs, because if it's 5 volts when it needs 3, then you're going to destroy it. But again, the schematics are going to help, or a board view is going to help. And specifically about webcams, I also have an old Hackaday project that has instructions about webcams that will apply to also touchscreens and fingerprint sensors, which is nice. Touchpads, though. Touchpads is a little bit more complicated topic. I haven't actually gotten into it much myself, and old touchpads are typically PS2, and I've heard a lot of stories about people using USB to PS2 adapters with those with great success. I have a hunch, and I think that I've heard that the gesture support is incomplete because it's not quite part of original spec of PS2 or something. And if you have I2C touchpad, then it's basically a nice device that you don't know anything about. So you need to know the initialization sequence. You need to know the commands. And if you get a logic analyzer, which you should, I will talk about that. You will be able to get all of that and reverse engineer the communication protocol, and then reuse a newer touchpad, which are nicer and like smoother and everything. And the project link is a Hackaday AI project that you should check out, of someone reusing a laptop-sized, full-sized touchpad, the size of entire like keyboard. And it's a nice project, and it will give you insights into what's necessary. Logic analyzers, quite like quick interlude. Spend $5 or like up to 10 euros on eBay for a logic analyzer. You can use it with fully free open source software. It will step up your reverse engineering skills if you don't have one already. This analyzer can do streaming. It can do quite respectable megahertz, and you can reverse engineer a lot of communication protocols with that. You can definitely reuse batteries. Most people take them apart for cells, but a laptop battery is a 2S, 3S, 4S lithium-ion pack. You typically don't get midpoint connections. They're internal. You get a VBAT, you get ground, the charging circuitry is never inside the battery. It's usually always on the motherboard. So you also need to connect some kind of charger module. But the battery certainly has protection and monitoring inside. And I'm not sure, but it probably has internal balancing. I genuinely don't know. I2C protocols, I think there is some open standard subset for battery communications, like smart battery or something, but I know that there is also proprietary communications, and you can also connect the battery to a laptop, connect the logic analyzer, and sniff the communications. If you're interested in some laptop battery IC work, I have a stash of ICs sorted by like controller name, and you just let me know. I can probably share some of you if you're looking for some specific ones. Common pins you will see from schematics. If you don't have those, usually ground, 1 or 2 grounds, 1 or 2 battery pins. I2C, sometimes there is an enable output pin, which you have to pull to ground or somewhere else to get the output. But if there is no output, it's also possible that you just have a dead battery. Sometimes there's an alert pin and some kind of like maybe interrupt pin for I2C. Again, schematics help. Or you can just take the cells, and you can also take the Ultrabook batteries part for the cells, which I have gotten quite a few nice flat cells this way. But of course, just like fruit, it helps if they're ripe for the picking. So you might have to wait a little bit. By the way, if you have a Dale, I'm sorry, this is a kind of common problem. You might encounter it in the future. Speakers, microphones, kind of obvious. Atom speakers, they're usually in like a black casing of some kind. This casing is, as far as I know, is acoustically matched. So the volume of air inside is calculated, the shape inside is calculated. So don't take the speakers out of the case. It's probably going to sound worse. Digital microphones, unless you know the part number, not very reusable in my view. You have to know whether it's I2S or PDM, just like, you know, with microphones you sometimes get on the webcams. Also, you need some kind of microcontroller to connect convert the formats into something that a computer can easily understand, unless you use it with a microcontroller to begin with. And analog microphones, I mean, you know how to reuse analog microphones, just a capacitive microphone. Fans, you can definitely reuse fans, especially helps if they have color-coded wires, because some have and some don't. If you do have color coding, these are the colors you will typically see. If you don't have the color coding, like all the wires are black or some different colors, then it helps if you have schematics. Again, I might be repeating myself here, but also you can do some multimeter probing, so figure out the internal ESD diodes, kind of maybe, you know, try to spin the fan and generate a voltage, that kind of stuff. If you miswire the fan and where you don't know the pinout and you try to send 5 volts to the pins that you've selected, you're going to fry it. That's a pretty consistent experience in my book. And then, yeah, once you have done it, you can reuse the fan as you wish. You can definitely reuse heatsinks. Yeah, that's a Kurt's picture. If you want to reuse heatsink, you can basically use it for some kind of project where you have a powertrain and maybe a slim form factor. So you connect the transistor to the heatsink, and then you cool it. That's exactly what those heatsinks are used for. And then you also reuse the fan in the same way. I think that's cool. You can reuse chargers for sure. So what's the next slide? I forgot. Oh yeah, let's talk about charger voltages. So 18, 19, 20, they are kind of a scam, because the reason we have 19 and 18, as far as I understand, most of the time, is that in some kind of countries, there is a standard that if you have 20 volt or higher power supply, you need to apply for additional certifications. And usually you can just run 19 and 18 volt laptops on 20 volts. In fact, that's what I'm doing right this very moment. I think it works, right? Would be ironic if it didn't. I wouldn't suggest you go with 24 volts though. It's tempting, but a lot of capacitors on the main power line inside the laptop are rated for 25 volts, and 24 is just a bit too close. What's next? Oh yeah, Dell. So Dell, you have the whole trinity of proprietary stuff, which is Dell, HP, and Lenovo. And let's talk about charger wattage identification. So in Dell chargers, there is a third wire from the charger to the plug. And this wire is connected to a one-wire EEPROM, which has charger wattage encoded in ASCII. So you can fake that within a tiny. You can buy those replacement ICs from AliExpress if you don't have the access to original ICs. So if you need to, connect like a Dell, a power supply to a Dell, that's how you do it. With HP, it's the same third wire, but there's a high value resistor from VCC from 19 volts to the ID pin. And that third wire breaks a lot, and when it does, the laptop is not going to charge the battery, or without the battery, it's not going to boot up, or with the battery, it's going to throttle the CPU. So look out for that. You usually can easily fix the wires. Lenovo has a third wire system, which is well documented by ThinkPad enthusiasts, which are like a special breed of people. It's wonderful. And the resistor inside the plug, so you only have the wires. It's more resilient. They break less. And if they do break, it's also quite easy to repair them. One thing, if you want to repair a charger, don't buy these. Seriously, take apart the original plug with X-Acto knife and resolder it. This plug in the photo has been seen well in like hard conditions for 3 years now after the repair I've done, and it's just they always break. They're not adequate. And what's next? Oh yeah, definitely don't do this though. Please. If you need to take the charger apart, if it doesn't have any rubber feet, that you can that there's like screws under, then the best you can do is to take a chisel and a hammer, because then chances are it's ultrasonically welded. So what you do is you take the chisel, you take the hammer, and you bang it through the perimeter of the charger until it's like through the slot in the middle, and then when it's open, you do whatever you need to do, and then you can even neatly super glue it together. No need for any kind of electric tape stuff. Keyboards, just fancy key matrix. Oh yeah, say you can definitely reuse those. Key matrix, no diodes like mechanical keyboards. So anti-ghosting is by design of the key matrix layout. So there's like a weird way to lay out the matrix, like rows with one key on them and so on. Sometimes there's LEDs and separate buttons, like the power button on the same APC. You can use a microcontroller to reverse engineer the pinout by pressing keys and seeing which keys get connected to which one. You can use then that same controller or the microcontroller or different controller as a controller. These keyboards are really thin and nice. Thank God for the economies of scale. And if you want some instructions, there is some good Instructables and Hackaday IO projects. Just don't do this though, please. Okay, you know who you are. This is my solution that I've done for reverse engineering. Basically, you plug it onto a Raspberry Pi, you run a Python script, it asks you to press keys, like all keys of a keyboard, and you press those and it records the pins. So you can spend like 3 minutes to reverse engineer a keyboard, and you can buy it from me if you'd like. I've recently started selling it, but also it's two I2C expanders in a trench coat, and all my products are open source. So if you want, you can take the schematics and take my script and just assemble your own solution if you'd like. Let's talk about reusing whole laptops and modifying whole laptops. You might remember this. This is the project that actually got me started on laptop modding. So the whole like it's important to build their own laptops thing, that's a post hoc justification. Not that it's not important, but still, people have built the craziest things with those, like all kinds of peripherals inside. It's just mad. And my mods haven't been so successful, but I sure have learned a lot. One thing I'm going to warn you about if you're disassembling your own laptop, very common cause of that is that you unplug the LCD connector before you have unplugged both the battery and the AC power cable. So you have to unplug both, otherwise you're probably going to kill your motherboard, because there is potential for high voltage power lines to short to data lines, and then you can probably kill the CPU, the chipset, whatever else. Please just unplug everything, okay? What I think is that we need more laptop modding. I've been talking to a friend like a month ago, and she asked like, why don't we have like laptop mod chips like we used to do in game consoles? And I started explaining like, oh, this is the reason, and then I was personally like, oh, actually, yeah, why don't we do those? And turns out there's some great mod chips, especially ThinkPad community, because ThinkPads. Anyway, so this is a mod that taps into a certain model certain ThinkPads model dock pins, and it allows you to put a high definition display with this interposer port into your ThinkPad where it was never meant to be, and it's just something that you solder into your laptop, connect a few wires, and it starts functioning, and that's amazing to me. Oh yeah, that's what I mentioned about disconnecting power. And ThinkPad users have done a lot of different mods that it's seriously too many to share, and I don't think I can seriously just look into those. There's a lot of inspiration you can get, and I hope that we also expand into other laptops like this cutie I have here. It's my personal, like one of my personal collection laptops, and I hope that I also can do some mod boards for this one. I've recently started a mod board project, which I hope to also soon start selling, which is basically a boot device for BIOS chips. So you can have like a stable firmware BIOS chip that you boot from, and also like a socketable BIOS that you can switch to and try booting your main laptop from. So you no longer are limited to like doing BIOS research on burner laptops, which is limiting. There should be more about BIOS in a moment, but M.2, you should definitely read the M.2 specs. M.2 as a standard is very cool. Oh yeah, that's a SSD sewn in half, and that works. That's an SSD that's still works somehow. M.2 is seriously impressive, and you can get the specifications online, and there's like all kinds of PCI Express devices that you can actually like interconnect. And there's more. You can actually, in some laptops out there's like a Wi-Fi card that actually has 2 PCI Express links and also has DisplayPort. And if you make like a port for that, well, okay, as long as it works in your laptop, because different M.2 slots, even if they look the same, they have different capabilities. Depends on the laptop. And you should really, it helps if you have the schematics. If you don't, well, you can still experiment, and specifications help you figure out stuff a lot. And something I've done is adapter that you can use to connect SSD in place of your Wi-Fi adapter that I'm also going to start selling soon. You get like some exposed USB pins you can solder to in case you still need the USB Wi-Fi for some reason, because why would you need that if you have like 8 terabytes of storage on an SSD? And it's not going to work with whitelist. I'm going to mention whitelist. Don't worry, the Holy Trinity applies. Something that could be a goldmine is an adapter that abuses everything I've read about in the specifications. And hopefully, if it works out, it's an M.2 card that allows you to put one SSD into a slot that's designed to accept one. BIOS modes, something that people should definitely look into. I have done some. laptop manufacturers like HP, Lenovo, Dell, they have whitelists, so they limit what kind of PCI Express devices you can put into your own laptop, which, if you ask me, it's preposterous. And so if you hack your BIOS, you can remove the whitelists and put like 6 SSDs into your laptop. Who can tell you otherwise? You can unlock new menus in your BIOS. There is cool stuff and there is sad stuff. I'm going to mention the sad stuff. People usually use like the reflashing clips. And oh yeah, thing I've done personally is that I've doubled the security of a laptop. If you zoom in, you can see the doubled security. You can also see that you should back up the original version before reflash. And sometimes there's like all kinds of menus, but there's also side effects. If you use clips, it's not impossible that you will have problems. So it's like a clip-on thing that... what's happening? Oh, yeah. It's a clip-on thing that you just reflash the BIOS chip in system, but the power rail that you have to power also goes to other devices. So I personally always desolder the SPI chips before reflashing, and sometimes you can use this socket, which costs like $2 on Taobao, and tell the $10 elsewhere per piece. So you should probably get them on Taobao. These devices actually are 5-volt data lines by default. Look out, you have to modify them to actually properly have the data lines at 3.3 volts. Next thing, modern motherboards, they have SPI flash chips, which are connected directly to the CPU, and they are also connected to a CPU connected 1.8 power line, which means that a 3.3 volt clip is going to burn it. So I have a laptop that's on Ryzen 3500U. It's a like reasonably recent laptop, and it has this problem. And be careful out there if you connect a clip to such a laptop before testing. You're probably going to destroy something. So look out. Some benefit of well, tinkering with BIOS is that you find things that you were not supposed to find. And I was looking through some BIOS research like a few years ago, and I was like, oh, that's my laptop picture. The laptop I've used for 6 years for everything I've been doing. And turns out it has some kind of cursed Windows hacking BIOS UEFI module that it just injects stuff into Windows that you cannot detect. And I was like, okay, nice, wonderful, cool. Someone was probably paid for this or something. Well, you should do it. There's a lot of stuff that people haven't really heard about, and people uncover things from time to time. Reusing motherboards, it's basically a small computer. There are some details. I am 27 minutes in, so check out the slides.
I think you have time, so you should just finish up at your own pace.
Sorry?
I think you've got a little bit of time, so just finish up at your own pace.
3 minutes, right?
Well, we have a 15-minute break coming up after this, and it looks like even a little bit more than that. So I think it's fine to finish it out.
Okay, I'm going to take a few more minutes. Thank you very much. Thank you. So when you're using motherboards, it's basically a small computer. Sometimes you need an internal screen to see the BIOS, sometimes you don't. With Dell, connect the speakers, it's going to beep out the codes that that like any problems the motherboard has. 8-ohm speakers are going to tell you that the codes are online. You will usually need to find the power button. Again, schematics help. Sometimes you need to fake the lid sensor if it's not present on the motherboard, because the laptop will think that the lid is closed. Again, Holy Trinity. If you don't use the original power supply, fake it. If you are just soldering 19 volt or 20 volt wires, add the resistor or ID chip or whatever you need. This is a water-cooled laptop somehow, and it's a small computer. What can I say? And there is a gaming option as well. You can see this guy runs Linux. That's just self-explanatory. Also, schematics help as usual. My personal like reused laptop that I adore is a backup machine. It's an i7 powered device, like motherboard with 4 SATA ports and enough RAM. It does data recovery, it does backups from like full drive backups for me. It does compression, it does encryption, it does like all kinds of stuff that I needed to do. And it's also very low power, so I can just leave it on for days at a time if I have a particularly glitchy hard disk drive. So I just personally I adore it. It's like it's a great tool, and you can build a lot of great tools with laptop parts. I2C, there is a lot of I2C in laptops. And that means if you run Linux, you can connect your own I2C devices. You can interface with those from C, C++, Python, Bash, JavaScript for some reason. And you can get I2C even from HDMI port. So we had example from like in Discord show and tell from someone, and then like reflashing I2C devices through HDMI. And I'm also going to sell my own adapter for this soon. But you can also just get an HDMI cable, cut it in half, get I2C, question marks, profit. So that's the conclusion. I believe that we should get a lot more from our laptops. Hopefully, I have given you some of the tools you can use to make it so. Some of you are going to make your own laptops along the way. Godspeed. If you are interested, first of all, I will be publishing a lot of more research. I've been doing this for years. I'm not planning to stop. It's a great topic. If you would like, join me. I have a side project that I would like to start, which is that someone should really start cataloging all laptop mods, reuse examples, and scenarios that exist out there, so that people know what's possible and what can be done, what's the information available to people. And thank you. If you have any questions, I am on Hackaday, I'm on Twitter. Feel free to DM me on any of these 2 platforms. Also, if you like, I'm going to talk about laptop things on Twitter specifically in the future. Follow me there. Specifically, after I wake up, I'm probably going to try and describe why the cursed M.2 adapter specifically is cursed. And I hope you will like it if you follow me. Thank you. I hope this is going to help you in your adventures. There is so much more to talk about, and hopefully with some of you we can work on it together. Good luck.
Thank you so much. That was just an excellent talk. I know people have a ton of questions, so if you get a chance, we'd love to see you in the Discord channel. Otherwise, it's nice that you shared your Twitter handle as well. We will take about a 15-minute break with Remoticon. We'll be back at the top of the hour with 3 more talks from Uri Shaked, Hash Salehi, and Jay Doscher. We're going to do a little AV test for the MC of the next session. Jenny, feel free to turn on your mic and video. Just realize that it is going out to the stream. I see you've unmuted, but I don't hear you yet. Yep, now I hear you, but you're a little quiet.
I'm a little quiet, am I? Maybe there is a microphone. Let me just take my camera. Can you see the camera, by the way?
Yep, looks good. I wonder if you move your microphone just a bit closer.
Hang on.
Perfect.
USB video. Is that better? Hang on. There we are. That's the camera. That's the best one.
So now I'm just getting a black screen.
Oh dear.
It's possible your USB camera is being used by another program like Discord or I guess Chrome.
Okay, I may just jump out because for some reason I can't minimize this, get it out of full screen. Oh, exit full screen. Sorry, I found it.
Yeah.
Great. Okay. Let me just, oh yes, it's being used by something else. Let's get rid of the something else.
I see color bars.
Color bars, that should come in a minute. Here we go. Have you got me?
Yep, I see you at Techer Lab.
Yay. Excellent. Awesome. Okay. Right, so I have microphone and I have video. Do you want me to try sharing a screen?
So I don't think that you need to share screens. I'll just run the production for you. So really all you need to do is manage your own muting and camera, like turning your camera on and unmuting and doing the introductions, and I'll try and take care of the rest of the stuff.
Okay, fantastic. Okay.
Great.
I may as well mute now.
Yeah, if you don't have any more questions, you can mute your camera and microphone, and we'll be back. This countdown timer says in 13 minutes.
Okay, see you in a bit then.
All right, thanks. All right, we're going to try another AV test with Uri Shaked. Uri, if you want to unmute your camera and microphone to try them out, that'd be great. Just realize you are going out live to the stream. All right, your camera is looking good. How about your mic?
Hello, world.
Yep, I hear you loud and clear.
Can you hear me, Herbert?
Yep. Can you hear me?
Are we ready? I can't hear you. but I guess you can hear me. Maybe I will.
Yes.
I
Yep, I
don't
can hear
think I need to hear you, but let me just double check my settings.
Hello.
Pa-pa-pum.
Do you hear this?
Now I do, loud and
All right.
clear. Wow,
Excellent.
such
Well,
a radiophonic voice.
thank you. All right. Well, I think we're all set. Did you have any questions about going into it?
No,
Okay,
I guess.
great. So I think everyone's done an AV test. If you want to mute your mic and video, we'll be back in about 9.5 minutes.
See you then.
All right, thanks.
Welcome back, everybody. Next up, we have Uri Shaked, a man who described himself to us as voiding warranties for fun, but who long-time Hackaday readers will know as an authoritative expert on microcontroller internals. Over time, he's shown us projects across NRF, AVR, and ARM, and many more chips. And most recently, he's delivered the definitive lowdown on the Raspberry Pi RP2040 dual-core ARM chip. He's also turned his hand to more than one badge life project, always producing very well-engineered and fiendish CTF projects. So take it away, Uri.
Thank you, Jenny. Wow, such a detailed introduction. I didn't expect that. So before we start, I will say that, hi, I'm Uri, and let me take off my headphones and change them to my reverse engineering hat. So well, that will get us going through this talk. And let's share my screen and do this. Sharing screen number 1. You should be seeing my screen now. Let me just make sure I can see the chat. So if there is anything, you can let me know. So reversing the ESP32 Wi-Fi. Why would we want to do this? In 3, 2, 1. So why would we want to do this? I will share with you my personal reason. I'm working on an online simulator for Arduino and electronics called Wokwi, and I recently added ESP32. Let me show you that. So this is Wokwi, and on the left we have MicroPython program, and on the right there is an ESP32 connected to a NeoPixel ring. And as soon as we hit play, we can see the simulation is starting, and it does what the code tells it to do. Blinks, alternates between red and green, and we can easily stop the simulation, change one of the colors from red to, let's say, RGB of purple, hit play again, and yeah, it's that simple, just changing the code and seeing the result. But don't let this very friendly or simple user interface fool you. This is actually running a full ESP32 simulation behind the scenes. It's not a spatial version of Python interpreter that I wrote or MicroPython compiled in a spatial way, just running the stock MicroPython that also runs on your ESP32 devices. And I want to show you something. So I'm going to add an LED. Let's connect the anode to D2. And let's connect the cathode to the ground. And now I'm going to show you the power that this simulator gives us by simulating the actual hardware. So we are going to comment out this while loop. So instead of running it, we'll start a simulation and we'll get right into the MicroPython REPL. And now I'm going to do some witchcraft, and this is something pretty advanced. It's like a lot of parts in this talk. If you can't follow it, that's totally fine. You don't have to understand everything. So I'm going to write directly into some memory address in the ESP32 chip. Specifically, I'm going to write this value. And what writing this value to this address does, it sets this pin number 2 to output. And then I'm going to write another value or the same value to a different address. This time it ends with an 8. And you can see it turned the LED on. And then I can do write to a different address and it will turn the LED off. So I can use the MicroPython high-level interface to control the hardware, but I can also write directly to the memory addresses that control the hardware. And I get full control of the hardware this way. And I introduced this ESP32 a few weeks ago, and then I asked the users, hey, what do you think about it? And they all told me the same things. It's great, but we also need Wi-Fi. And this is the why I started this project. Other than bringing Wi-Fi to my own simulator, I figured out that nobody has really done this kind of reverse engineering to the ESP32 Wi-Fi stack. And it can probably be also useful for security research and other purposes. So now that we got the why covered, let's talk a bit about the ESP32. And before that, this is a link with all the links and the link to the slides itself. So someone, please be kind, take a screenshot and post it to Discord for the other people watching this. So ESP32, how does it work? The instruction set that it uses is called Extensa. It's not ARM or RISC-V or AVR that you probably have on your other microcontrollers. It's a specific different instruction set. And there is this very detailed document called the ESP32 Technical Reference Manual that contains a lot of documentation about the chips and the peripherals and how everything is set up. Let me just show you a quick taste. So this is one of the table from the TRM, and it tells us what the memory map for the ESP32 looks like. So Ramlendia, if you watch Alicia's talk yesterday, which part of memory does what? So we are interested in the peripherals, which are like the USB, SPI, UART, and also where I believe the Wi-Fi lives. And we can see all the peripherals, they sit in this memory address space starting from 3FF0 up to 3FF7. And talking about peripherals, how does the code speak with peripherals? So the main way the code that runs on the ESP32 speaks with peripherals, with the SPI, with the UART, the serial, and other peripherals, I2C, is through registers. And we have seen a demo of this just here with this LED. We just wrote to these memory addresses, which happen to lie in the peripheral address space. These are hardware registers that belong to the GPIO peripheral. And by writing to them, we were able to set its pin to output and even to turn it high and then back low. But for most peripherals that can send and receive data like SPI or UART, they also have at least a set of two registers for sending and receiving data, RX and TX registers. So if we have a UART peripheral and we want to send some data, we write it to the TX register, and that tells the hardware, hey, we want to transmit it. And if there is some data that comes in, we can read it from the RX register. So that's how it usually works with most peripherals. And most of the peripherals also have an interrupt, which is how they tell the code, hey, there is something that happened, like there is new data on the RX register that you should read, or the data that you wrote to the RX register is done. I finished transmitting it. And one more interface between the user code and the hardware is DMA, Direct Memory Access. And I'm not going to talk about it too much right now, but it basically copies data from the memory, from some arbitrary memory address the user provides into the peripheral, or from the peripheral into the memory. And the ESP-TRM tells us that the Wi-Fi has DMA, which is a nice clue that we will use down the road. So that's about the peripheral interface. And I could sit here and talk about how the simulation works. I think it's really interesting, but I already done this in a very long YouTube series where I code a Raspberry Pi Pico simulator from scratch. So you can find it in the link document with all the links. And there is also my simulator is the ESP32 part is not open source, but there is a QEMU simulator, which is open source and can simulate ESP32. So there is a link if you want to try doing things with ESP32 simulation on your computer. And finally, I want to record another video where I show how I simulated the instruction set for this Extensa architecture. It is probably coming soon. There is a link to the YouTube channel on the document with all the links. So let's talk about adding Wi-Fi. How do we go about it? Of course, the first thing I did was just Google, is there any information online? Not really. Some people did something with all the ESP8266, but it wasn't really too deep. And then, of course, I went to the data sheets and the TRM, but there was almost no information. There was this thing about the DMA that I showed you and a few other pieces of information, but nothing really very useful. And then I went to the source code of the ESP-IDF, their application framework. But apparently the Wi-Fi library is coming from a different repository. You have the link here and in the document, and it's just binaries, no source code. So you have the whole source code for the RTOS and everything else in the ESP-IDF, but not the Wi-Fi. So this leaves us with only one option, which is reverse engineering. Yeah. And let's do reverse engineering, but before we dive into it, let's define our goal. Our goal today is to find which registers control the Wi-Fi radio and figure out their meaning. What do we need to write or read from those registers in order to tell the Wi-Fi radio to do things like transmit frames over the air or receive them? So that's our goal. And let's see how we approach this goal, what tools we are going to use. So the first tool is GDB, the GNU debugger. And there is a link to a blog post where I explain about my setup. You can see it here. It's a Raspberry Pi with a custom hat I made that is an adapter to an ESP32 board. And all of that lets the Raspberry Pi speak to the ESP32 through the JTAG debugging interface. And I'm using a tool called OpenOCD, which bridges between JTAG to GDB. But the point is, I can use GDB, the GNU debugger, to debug my code on the physical hardware, as well as in the simulation. So GDB is one tool. Then we have Ghidra, and Ghidra is an open source reverse engineering tool, a very useful one. It doesn't work out of the box with Extensa. If you want to use it with the ESP32, you have to download and compile a plugin. You have the link here. And more importantly, I'm using the simulator itself to debug and reverse engineer the Wi-Fi framework. The simulator gives us access to all the internals of the ESP32, so we can see the internal state of the peripherals and the CPU while the code is trying to connect to the Wi-Fi, and then figure out how the code is trying to connect to the Wi-Fi. And we'll see that in a moment. So now that we know our tools, let's dive into this. And we are going to take, that's what I did when I started working on this. This scan example, it's one of the examples that comes in the ESP IDF, just scanning for Wi-Fi networks and printing the results. Here is the source code. There is also a link in the document. And you can see it's calling a few interesting functions like ESP Wi-Fi init, ESP Wi-Fi start, ESP Wi-Fi scan start. So it seems like it's using the Wi-Fi stack, and we are going to figure out how. But before we do this, this is a very important tip. If you are working on a reverse engineering project, you always want to turn every kind of log messages that you can up to 11. And in this case, for the IDF, there is this menu config tool, and I can configure the default log verbosity to verbose, which gives me a lot of logs. And that's super important because it turns out that the Wi-Fi stack has a lot of logs inside it, so I can see what it's doing. So whenever you're working on some reverse engineering projects, find a way to get as many logs as you can. And now that we got that covered, I compile this scan program and I apply the following method. I ran it inside the simulation until it breaks or crashes, and then I saw where did it break or crash, fix the issue, and then repeated the process all over again until I was able to get the Wi-Fi to start in the simulator, or at least the code to think that the Wi-Fi has started. Let's see how this is done in practice. So this is the simulator running scan.elf, the compiled scan program, and you can see there is a bunch of output, and then it has this yellow warning and it freezes. And at that point, when it froze, I connected to it with GDB, the debugger, and I hit the backtrace BT command, which shows me the chain of functions where it got stuck. So this is like the call stack, the backtrace where it got stuck. And it got stuck in this specific function, hallmark the init. And as you can see, the functions in this stack trace, they all seem to be related to Wi-Fi, like Wi-Fi hardware start, IEEE 002.11. And that got me interested to see what does this function do? Why does it get stuck into it? So I asked GDB, hey, GDB, can you disassemble the function for me? We don't have the source code. We are even lucky to have like the names of the functions. So the Wi-Fi binaries, they are compiled with basic symbols. So we have names for most of the functions, but we can't see the parameters and of course not the source code because it's not available, but we can at least ask GDB to decompile it, to disassemble it. And this is what I got. Even if you know how to read extensa assembly, this is like a nightmare. You can't really make sense out of this code without knowing the values of all these A9, A8 registers. So this is, I mean, you could debug it and step through it and painstakingly figure it out. But fortunately, there is a much better way to do it. So enter Ghidra. I asked Ghidra to take this scanf file, load it, and give me the hallmark the init to decompile it for me. And now I got something that looks more like a pseudocode. It's still messy. We can clean it up. I'm going to remove these memw instructions. They are just memory synchronization stuff, and clean it up a bit. So the thing on the right is equivalent to the thing of the code on the left. You can verify it later if you want. And now we can start making sense of what this function is doing. It's writing to some memory address, to some register, and sets a few bits in it, wait for 32 microseconds, and then it busy waits. It reads this same register that it has written to before, and it waits until some bit in this register, this specific bit, is set. So it hangs because in the simulator, we don't implement that behavior. So back to our method, I implemented that in the simulator. So the simulator would listen on this address, and whenever it shows this value returned to this address, it would set this bit. So hallmark the init would be happy and let me go on. And I did it several times with several functions. And I noticed something interesting. I noticed that all of those functions, they interacted with addresses that started with 3FF73, which led me to ask, okay, what's there at 3FF73? So I went to the TRM and I looked like there is this peripheral address mapping that tells me where each peripheral, like the UART PWM, lives in the memory. But apparently for this specific address, 3FF73, it says, it's reserved. They don't even tell us there is something there. They just say it's reserved. But since I figured out a lot of things are reading and writing, all of the like Wi-Fi functions I encountered are reading and writing from registers starting in this, I figured out I had my first revelation. Wi-Fi peripheral is probably at this address. So this is the range of addresses that belong to the Wi-Fi peripheral. And with that in mind, I went on with my journey. Now we hit the first part of our call. We know which registers control the Wi-Fi radio, and we just need to figure out or which range controls it. And now we just need to figure out the actual registers and their meaning. And in order to do that, we are going back to that backtrace that we saw before with all those functions. But instead of focusing on the top one, hallmark the init, we are going to focus on the one that is almost at the bottom, this pp task. And we can see it has no source code information or parameters because it also comes from the Wi-Fi. And it sounds like some kind of task that manages the Wi-Fi. It's called pp task, and it's called from this vport task wrapper, which is part of the FreeRTOS operating system in the IDF. So it sounds like an interesting place to look. I asked Ghidra to show me the source code, and what you can see here is just an excerpt of this source code. And this pp task is basically a very big switch statement which looks at some value it gets from somewhere. And then depending on that value, it calls different functions like pp process txq, pp proc txstan, rx packet. And it sounds like it's the central place for all the Wi-Fi communication. So that got me intrigued. I set up a breakpoint in this pp process dxq and started tracing what happens inside. And eventually I added a lot of logs to the simulator. So it would log all the memory reads and writes in this region, where the Wi-Fi peripheral is, 3FF73. And eventually I figured out through this rigorous process of debugging that this is the address of the TX register. So whenever the code wants to send some Wi-Fi frame over the air, the Wi-Fi stack eventually writes a DMA buffer with a packet, and it writes the address of that DMA buffer to this register. And this tells the hardware, hey, you should transmit this Wi-Fi frame over the air. But that was the easier part. It wasn't easy, but it was the easier, because with the TX, we had sort of the starting point. The code dictates when the packet would be sent, and it sort of initiates a chain of events that eventually writes to this register. But when we look at the RX part, we can't know that. I mean, we know that if pptask is getting this value, it already knows that it has to look at the received packet. But who tells pptask that it has, like, who sends this value to pptask? Who tells pptask what to do, that it should receive now a packet? Where does how does the hardware, how do we know when the hardware want to tell the code you should receive the packet? We should somehow find a way to go back in time from this point to where the hardware told the hardware to send the code to receive a packet, in order to figure out how this receive packet is triggered. So for that, we want to know who calls pptask. And in order to do that, let's go back to the stack trace, and we'll notice that in our stack trace, we had this IEEE whatever IOCTL process function. So if we could figure out what happened before this function was called from pptask, we could probably understand who orchestrates, who manages the things, who tells pptask, who gives gives pptask the values that it uses to decide which functions to call. And for that, I added an ability to trace all the functions in the simulator, so I could see every single function that is called in the simulated code. How do we do that? If we take a look at the disassembly of almost every function in the compiled binary, we can note that all of the functions are, or most of them at least, start with an entry instruction, and we can take advantage of that. So what I did, I basically told the simulator, whenever you see an entry instruction in the code, just log the address, the current program address, the value of the PC register, which holds the program address. So we will have a log of all the function calls. This is what it looks like in the simulator code. You only have to care about this line, which is highlighted. So this is the implementation of the simulation for the entry instruction. And when we get here, we just log entry and we log the current, the address of the current instruction. I also had a script that would that would read this output and add the name of the function next to the address to make this a bit more useful. And then we finally got it. So this is again that backtrace, and this is the log from the simulator where you can see all the function call that happened in the simulation. And I searched for this function, i.e. 802.11 IOCTL process. I looked a bit back, and then I found something called pppost. And pppost sounds like a good candidate. It sounds like it would be a good name for a function that posts something to the queue of pptask. And you can see it also called some queue functions down the road, like coffee theta to queue and stuff like that. So I did some more debugging, and I figured out like the central dogma of the ESP32 Wi-Fi. There is this pppost function that gets a task ID and it sends it to some queue, and then this tells pptask what to do next. So pptask is running all the Wi-Fi logic, and pppost controls that. And you might notice that the person who wrote this wasn't very good with following naming conventions. Anyways, now with that knowledge, we can go back to pptask and go back to ask ourselves, okay, so we know that this function is called when pptask received 11 hexa, but and we know now that pppost can tell pptask what to do. So somebody must call pppost with 11 hexa at some point, but who did that? So GDB has the answer. We can set up a conditional breakpoint telling GDB break in pppost only if the parameter that is stored in this register A10, if it's 11 hexa, to figure out what makes, who calls pppost with this value and get us to this switch statement. And I ran this on the physical ESP32 device. I got the backtrace, and I could see that it was like the chain of the events that called the pppost with 11. But the thing is, we get back to pptask. So it's like going back and forth. This time, pptask called another function, wdev process rxsac data all. And I was like, okay, so pptask called this function and they called pppost, and then this goes back to pptask. That's a bit confusing. Anyway, I went back to the code of pptask and I saw in which case in the big switch statement, it calls this function that I've seen in the stack trace, this wdev process rx stack data all. And I noticed it calls it when it gets 19 hexa. So I used again the same technique of asking GDB, okay, who sends us this 19 hexa? Can you please set a breakpoint on pp post, but only if the parameter is 19 hexa? And so I did. And you can see I ran it on the physical hardware and it hit a breakpoint. I looked at the backtrace, and this time the backtrace is ending with Castillo int1, which is the interrupt handler. So this function is called by the hardware when the hardware generates some interrupt. And at that point, we can start piecing this information together, all these small stack traces that we got, and build the RX frame story. What happens? Which functions are called when there is when the hardware has a new frame to that has been received over the air, and it wants to tell the code, "Hey, look at that frame." And we have all these stack traces. And at that point, I spent a lot of time debugging all of these functions. For instance, figuring out how the code knows what happened. Like it gets an interrupt, then it has to look into some register to figure out, is there a new packet available? Is there a new frame, Wi-Fi frame available? Or maybe we just finished transmitting an existing frame, or did we have an error? So I spent a couple of nights just digging into all these functions in the stack trace. And eventually I figured out there is another register which gets a pointer to a DMA buffer, and this tells the hardware it's ready, that the code is ready to receive the next frame. And then when there is when the next frame is available, when it's been received, then the hardware just sets a bit in this event register and fires the interrupt, and the code can read the frame that has been received from this DMA buffer. So at this point, I sort of have the goal figured out. I at least knew which registers are relevant for sending data over the air and receiving data, and how to use them. And let me show you what it enabled us to do. So we are going back to Walkway, but this time we are going to use a bit more complicated example. This code example has still NeoPixels and an ESP32, but it also tries to connect to the Wi-Fi and to an MQTT broker. And then it listens for messages from the MQTT broker. And whenever it gets a message from the MQTT broker, it parses it with the UJSON library as a JSON and uses the values from that message to fill the pixels in this NeoPixel ring. Let's just see it in action. I'm going to run it. And by the way, while I'm running it, you can, there is a link at the end of the document. So if you opened it, I see there are a few people, you can even try it yourself. So I'm going to start a simulation, and let's minimize this window. So now it's connecting to the Wi-Fi, and on the right hand, I'm going to connect to the MQTT broker. And the code says it's connected to this MQTT broker on the internet. And I'm going to publish to the Remoticon this message. And you can see as soon as I send it to the MQTT broker, it went through the internet and the code got this incoming message. So now if anyone wants to try and send a message to this queue, you are welcome. You have like 5 seconds to try this. Let's send another one. And so, yeah, and this is like, finally, people will be able to use Wi-Fi in the simulation as I wanted, but it's much more powerful than that. For instance, I can open the developer tools. Wait a second. Yeah, nobody's sending messages to the queue. Too bad. Anyway, I can open the developer tools, and there will be a better user interface for that, but I can download a capture file and see all the frames that went into this simulated, to the simulations. Let's just narrow it down to MQTT. So I can see all the MQTT transactions, all the packets like the IP, the TCP, And if you are going to learn about networks, I think this is going to be a very useful tool. But at least I personally love it. So to summarize, we have used 3 tools. That was a pretty high-level overview of my approach to reverse engineering. We used Ghidra to decompile and do some static analysis. Without it, it would have been a nightmare to understand what all these functions like pptask do. Believe me, I tried. We use GDB for focused runtime debugging, so setting breakpoints, looking at the values of variables, the stack traces, and we also modified the simulator code to allow us debug how the code in runtime, but in a wider manner. It allowed us to see how the code writes do things like see all the function calls that happens in the simulation, or all the memory reads and writes to a specific region, things that GDB wouldn't let us do efficiently. And there is a lot more. This is we have just scratched the surface. There are other tools other ways that I did. There are other ways and techniques that I used. And if you want to hear about them, then you may want to ask Hackaday to organize a course or a longer session about that. So I hope you enjoyed. Thank you for joining me to learn a bit about my reverse engineering journey, and see you on Discord. Bye-bye.
Thank you, Yuri. Fantastic talk. Thank you so much for that. Don't forget, as Yuri just said, if you have any questions for him, go and find him on the Discord server. I'm sure he'd love to hear from you. But meanwhile, we have about 5 minutes, and stick around because Salehi is coming up, and I'm sure you'll want to hear from him.
All right, we're going to do a quick AV test. Hash, if you want to unmute your camera and mic and give them a try.
All right. Can you hear me?
Yeah, it sounds really good. And your camera's looking good to me as well. Is there anything else you wanted to test out?
Let me see. I've been playing with the screen sharing and everything, and so I think that's fine. I guess in my own video here, I don't see it in this setup.
Right, I haven't spotlighted you.
Okay, that's fine.
And it's just because I'm screen sharing the countdown video, but I think it'll be okay.
Perfect.
All right, great. So the countdown's at about 2:45, and Jenny will come back and introduce you at that time.
Sounds good.
Great, thank you. Jenny, are you able to to start your video?
Apparently not. It says that you've stopped it. I can introduce Hash without them all having to see me.
No, I think we're going to be okay here.
Excellent. Thank you very much. Hello, everybody, and welcome back. I'm Jenny Liss, your European Hackaday contributing editor, and I'm your compere for these segments. Coming up next is Hash Salehi. Now, Hash is best known to Hackaday readers for his infrastructure work, reverse engineering smart power meters, probing their inner workings, and reverse engineering their comms protocols. Since these devices have started to appear in every house all over the place, they hide behind a veil of secrecy. His work is particularly fascinating and also vital from a security perspective. So we're looking forward to hearing about his progress and the methods he used to achieve it. Hash, take it away.
All right, thanks a lot. Okay, I'm assuming you can see me now.
Yes, we sure can.
All right, I'm going to start sharing right now. Okay, so if you're seeing my screen right now, I started with the Remoticon imagery. So let's get into it. This is a map of Dallas, Texas, and each one of these red dots you see here on the map is a smart meter. The height above the ground of the red dot represents the number of days it's been running since it last lost power. This one here, the meter ID starts with a D00, has been running for 1,767 days without a power loss. This talk will be about how I receive this data that's transmitted in the clear, driving up and down the freeway. But first, let's take a blast to the past. The year was 2010, and there was a project to reverse engineer a LiDAR on a robotic vacuum cleaner. And this is my desk from way back then, and a makeshift jig and a taken apart robot on the Thanksgiving weekend of 2010. And this is my software that I used to decode that laser transmission and ultimately display it on the screen here and move my hand inside this box. It was sometime in the middle of the night, and I was trying to win this challenge. They posted a $400 bounty, and winning it was featured on Engadget. And it was really my first kind of foray into Hackaday. Hackaday featured a number of my articles, and I really appreciate the community that Hackaday has built, and the ability for all of us to get together and see what we're working on. And so that was the early day lab right there. But let's bring it back to the present now and talk a bit about smart meters. So this is me. My name's Hash. I don't do this professionally. This is all kind of in my spare time, like a lot of us. And this is a talk I gave for the ICS Village for DEF CON earlier this year. And so what I'm going to talk about to you today is Landis & Gyr smart meters, and the ones that are used by the power company Encore that's here in the Dallas area. And I don't do that to name and shame these companies. It's just what I'm talking about. It's very specific to these meters and how it's been configured by this company. But, you know, working on infrastructure is kind of a challenging topic. And Travis Goodspeed, that I'm sure a lot of you have heard of, he's talked about stuff like this. And he had a great talk that was basically saying we should reverse engineer stuff that uses the same parts as smart meters, but not smart meters. So we don't all get, you know, hauled away and people come after us. But I think the challenge is that more and more there's ransomware events. There's all these things where stuff gets hacked and they don't even necessarily have to hack billing systems and stuff like that. Like if they hack devices, they might get shut down. They might shut down a whole network. And it's all in our best interest to make sure this stuff is secure and to talk about it openly. And so that's what I started doing. So let me just explain to you a little bit about how this network works so that you have some framework. Landis & Gyr did a great job of putting out kind of a marketing video, and we'll use it to walk through how this system works. And so what we're talking about is these smart meters that are on the side of homes and apartments and businesses that you'll see here. And in it, there's a microcontroller and there's a couple transceivers. One's a Zigbee transceiver in some of them, and one's a 900 megahertz mesh network transceiver. And so the meters, they send their data back, but they don't all send it back to the mothership directly. They send it back to other meters, and those meters relay it, and they form a huge mesh network in the neighborhood that they're deployed in. They all relay their messages back and forth until they get to some kind of aggregation device. In this case, it's either a router or a collector that's installed up on a pole. Really, the difference is a collector forwards the data directly back to the power company, and a router routes it back again to what is ultimately a collector. This one is inside of a substation with some antennas on it. If you're driving around, you'll see it, like this one here to the left that I show. And from there, it sends it back over an IP network to the power company, where they use it for billing and to see outage information and stuff like that. And so I wondered, how does this system work? You know, they don't publish anything on these things, but I did manage to find a paper at the IEEE. It was written by a couple of people that worked for Landis and Gyr, and it kind of outlined a test system that was deployed here in Dallas. And so it had some good information in it. One thing that was particularly interesting was something they called a geographical routing protocol. And when I got to that section, I was super interested, like, what is a geographical routing protocol? And so they said it's basically a routing scheme which utilizes the geographical coordinates, the latitude and longitude of the communicating nodes. And by nodes, they mean smart meters. So I thought, where could I get one of these smart meters so I could take it apart? And so I went to eBay, and you know, everything's on eBay. I have no idea why this stuff is on eBay. I don't know who's buying it other than me, although I am pretty, I buy a lot of it. So maybe this market exists solely to sell me smart meters. And so I started picking things up a couple of years ago, just slowly buying things. And so here in my lab, which is, you know, you're seeing right behind me, the test equipment I have, and a lot of meters that I've bought, and a lot of modems. The modems are used inside of other devices or backhaul devices or things like that. And I started looking at them and trying to dump the flash memory and trying to see what's going on and what processor are they using, and could I potentially get the firmware off of the processor, and to buy residential meters and commercial meters. And this is my software-defined radio setup that we'll see a little more of later, and that's the new radio running, and it's just decoding all the packets that are being broadcast around me so that I can just look at them and stare at the data and trying to figure out what they're sending. And there's a Faraday cage in the back there, and here you see one of those routers. This one's a collector that I managed to find on eBay, of course, and then a Faraday cage to isolate the transmission so that I can put smart meters inside there and try to just isolate what they're sending to understand at a singular level what's going on with this network. And so when I began reverse engineering it, I started looking at the circuit boards and just creating schematics. So these are the schematics that I started creating to get a better understanding of what are the different parts and the power meter chip and the processor that's on it and the different communication radios like this CC1020. And as you get towards the back of the meter, it's even, I don't know if it's more interesting or less interesting, but it's interesting nonetheless, is a device that is basically a huge relay. So this will switch 240 volts at 200 amps, which is 48,000 watts, 10,000 times, according to their spec sheet, on and off. So that means the power company can send a wireless signal, which takes a few seconds to arrive at the meter, and the power will turn on or off at any specific meter. And so I wondered, you know, if they can send a message to a meter to turn power on and off, could somebody else send a message to that meter? And how protected are those messages? And are there any communication flaws or anything else inside these? So I set to understand that and to try to reverse engineer these things to see, you know, how protected are they, and can someone send a message and do that? So I did manage to get the firmware off of one of the microcontrollers in the meter. This is the bootloader firmware. The firmware itself is about 384K, and when you're reverse engineering, that's a rather large file to be starting out with. So I started looking at the bootloader to see if I can understand how it loads things in and how it reads its keys from memory and things like that. And so this is using Binary Ninja, but even this is rather large. And so when I'm kind of bored on the weekends, I'll pull this open and try to make a little progress on it here and there. Now, this is the waterfall, classic software-defined radio waterfall, and every one of these little peaks that you see appear here is a smart meter transmitting, just about all of them. And you can see they're transmitting all the time. This is just an antenna that's on my house. It lets me hear what's around me. And so there's a lot of traffic that goes. And so I wanted to receive this data and start to decode it. And when I began, I started with one of these Great Scott Gadgets yardstick ones. And so it uses the same transceiver chip, but it only lets me listen to one channel at a time. There's about 240 to 260 channels. And so I was only getting to hear like a sliver of the traffic. And I really wanted to use GNU Radio to receive this traffic. It's kind of the tool in my mind. And so I started building a receiver and wanted to build a receiver that could receive all 240 channels simultaneously. And so this is a block that receives 10 channels simultaneously, or a number of blocks, and decodes them and writes them to a file. And I was able to get that working. And as I scaled it up, I ended up building this monster computer with a huge GPU in it. And each one of these blocks you see on the right decodes 10 channels and feeds it in and tries to, gather it all down and to do it 240. And that computer was just, smoke was flying out of it, trying to decode this stuff. And it wasn't really working. And so despair set in. And I went to YouTube looking for inspiration. And I came across this guy, Jacob Gilbert, giving a talk at the GNU Radio conference of a flow graph that they created that does frequency hopping, spread spectrum decoding, where it just looks for packets anywhere and it decodes it. You don't have to look at individual channels. And so, hope had arrived again. And I took this flow graph and I added this part to the bottom here and ended up creating my own block to specifically decode the Landis and Gear data. And so what I did was feed in a sync word initially, these 1010s. This from the wiki shows the sync and the header that these smart meters transmit out that I figured out. And so I added that to the block. And what that does is it filters down all the transmission it sees and just gets this initial sync and then passes those packets into this grid stream block. And what this block lets me do is kind of filter some stuff down and filter by network. So these networks, what they do is if two different power companies are using the same types of meters, they assign them a different CRC value, basically, for their packets, so that one group of meters from one power company and another group of meters from another power company don't hear each other. They don't interact. They frequency hop differently. And so they can basically coexist right near each other. And so the first step is figuring out, well, what CRC is used by the power company I want to look at. And so I can enable or disable that. There's two kinds of packets. There's this 5.5 packet, which is basically a broadcast packet as far as I can tell. And then there's what's called a D5 packet, which is more of a routed packet. It contains a source and a destination to route packets across the network. And so the packet we want to look at is a 5.5 packet. And so this block lets me filter it down and say, I just want to see 5.5 packets of a certain length, which are the ones that are broadcasting out these GPS coordinates and this uptime data. And then I can choose to either enable or not enable the CRC. So here's the Sandia Labs, the Jacob Gilbert flow graph running. And we see it decoding information and it's showing the packets down there at the bottom that it's receiving and decoding. And so I push those out to a little TCP server from the GNU Radio flow graph. And I wrote a Python script that connects to that. And it decodes the information that it's seeing. So when a packet comes across, it separates out the first number, which is the meter ID, and then the uptime in seconds. And then I convert that to uptime in days. And then the latitude and longitude, like if you copy and pasted that into a Google map, you'd see the area around my neighborhood. And then an uptime in, or a timestamp there at the end, so I can keep track of when these came in. And that's ultimately how I was able to plot all these red dots on the map. I was going down that freeway at 70 miles an hour in a car with an antenna on top of it, not doing anything special. And you can see just how much data is captured. I mean, the meter had to transmit that. But the thing is, in order to do something really interesting, we have to transmit back to this network. And so the power company, they're going to get mad if I start transmitting back to their network. And I'm sure some people will come to pay me a visit. So what I needed to do was build my own smart meter network in order to run some experiments that I'm completely in control of. And so I thought, do I have enough? Like, I've bought so much stuff. Do I have enough stuff now to build my own smart meter network? And so using the collector that I found, I got a message on Twitter that said, hey, there might be something interesting inside there. So it'd been sitting on my floor this whole time. I'd been looking at meters. And so I decided to take it apart. And there's a bunch of high-res photos of what's inside that I posted on the wiki if you want to take a look at it. And so as I opened it up, you'll see the first thing I saw was a magnetic reed switch, which is hopefully used to wipe security keys or something else if somebody happens to take one of these devices. And so I began taking it apart, and in it, there's also a large battery, and that battery is used so when power goes out, it can still relay messages to the power company. The meters also have supercapacitors inside them, and so when power goes out, or if they get pulled off the wall, they can relay a message back. This is a modem board, like the modems you saw on my desk. It's the same board slid inside there, and so that's how this device communicates with the mesh network to all the meters. And then as I pulled this off, my mind was blown. Inside there is an M-SATA drive. That's a motherboard with an Intel processor below it running Windows Embedded 7. And the whole program that this collector runs is written in .NET, which means we can just load it in some software and basically see the full source code, which we'll pull up here in a moment. So I pulled out the rest of these devices, and just for thoroughness, you'll see there's also a cellular modem in here. And so this collector, how it sends its data back is over a cellular connection. So inside that SSD drive, there was a folder called collector. Convenient enough. And so I copied that to a different Windows machine and loaded up dnSpy. And sure enough, it's able to decompile everything that's there, all the symbols, everything else that need to exist is there. And you can just see the full source code. Like there's nothing hidden at all about what's on this thing. And I can even run the thing in debug mode and set breakpoints and step through the code. And so this is that application starting up. I connected one of the modems with a USB to serial adapter over to that computer so that it could communicate with it. But I needed to set some configuration data in. This was the initialization file. I couldn't make out anything of it. But I did notice in that code that it decrypts it when it loads it, and then it encrypts it when it writes it back to disk. So I thought, well, what if I just disabled those routines? And sure enough, there's the configuration file. There's no encryption anymore. And I can set the network ID and the other things I need to set so I can build my own simulated network. And we see one of the meters I have in the Faraday cage, communicate with it, and that's its message that shows up there on the screen. And so now that I kind of have my own network, I need to build a transmitter that allows me to interact with that network. And so my software-defined radio here I have set up with kind of the signal looping back into it so I can see what I'm transmitting out. And then I also have a modem here. And this modem, I found a pin that I could set to ground internally, and it puts it into a test mode. And so I have a terminal window here with it up, and allows me to set things like the receive channel that I'm going to go to and whether I want to receive data or send test packets. And so this is the test setup now that I'm going to use to try to write my own device to transmit. But there's some challenges with transmitting to this network, and this should help to sum that up. So if we look at a graph here and we just put time on one axis and we put frequency on the other, so they transmit from 902 to 928 megahertz. They also hop around all the time, even if they're not transmitting. So every 700 milliseconds, every 7/10 of a second, the meter hops to a new frequency. Sometimes it transmits, sometimes it doesn't, but it's constantly hopping. So the challenge is, as this is hopping around, where is it hopping? What frequency is it going to be on every 700 milliseconds so that we can interact with it and send it some data there? Now, if we look at this another way, and we say, let's look at frequency on the bottom, and let's just look at power on the top. This kind of sets the stage for what you'll see with these other flow graphs. Every time a meter transmits, the burst is just shown like this, a burst at a different frequency and a peak that pops up, and the power that it transmits out ultimately. And so that's the same thing you saw on the waterfall, those little peaks that pop up and the waterfalls that flow down. And so I thought, as opposed to trying to decode and figure out the frequency hopping and building this huge scheme that allows us to hop along with the meter and hop along with different meters, they all hop differently, mind you, they're not all hopping to the same pattern. What if I could build a transmitter that just split out all 260 channels and transmitted on every single channel simultaneously every single time I sent a transmission. So no matter where the meter was, what frequency it was at the given time, it would receive the message we send. And so I set out to try to build that in GNU Radio. And so this process, this talk will only take a few minutes to tell you about it. It took a lot longer than a few minutes to figure this out. But so what I started with is some blocks here that are just simulators. They send a cosine. I set them to a few different frequencies. And this block combines those individual signals into one spread of bandwidth so that they're together. So that instead of 4 individual signals, we're sending the 4 individual signals, but on the same bandwidth at the same time. And so this initially, I thought, okay, that's cool. This block allows me to put these 4 together. And so that initial experiment I thought looked good. So the game now is to try to scale it up from these 4. And so I took 10 signals instead and fed it into this block and tried to send it. And as you do this, the thing is, the more you send, the more blocks you start to put together, the more processor it takes, other things start to happen, right? So while it seems like this should be easy, just make one with 260, it's a little challenging. So as I had these initial signals fed in there, I thought, okay, that's great. They're not doing anything. I need to modulate one of these signals and see if it still stays within its channel. And so I'm just sending some random data, but we can see one of those doesn't look like the others. And it has this modulated random data. So it's frequency shift keying is the modulation type we're working with. And so I thought, okay, well, let me send just a string of ones and zeros. So I send something other than random data and see, can I build a flow graph where I send it on a few channels and then I show that data and I decode it. So at the top here, you see that waveform representation of those ones and zeros. And on the bottom, you see that I'm sitting it on 3 individual channels. And as I slide this over, you get kind of the static. We're in the middle somewhere. We're not on a channel. And as I land on the next channel, you see it's decoding it properly. And then I do the same thing. I slide it over to the next channel here. And we say, okay, now it's decoding it properly. So I can send multiple channels of the same data. And it looks like this theory is panning out. So now what I need to do is send some actual data. So this flow graph here, what the top half lets me do is create a packet of data. So this is 512 bits of information. So it's all the bits that make up one smart meter packet transmission. And then I feed it over across through this FSK encoder. And then down across, it turns it into a little packet of information and turns it into a stream for GNU Radio. It sends it to a graph that lets me see what that looks like. And then at the bottom, transmits it out. And then you remember that loop back that I had go through on my radio? That's that part there that lets me see what I'm transmitting inside of my own flow graph. So it kind of lets me see what's the data look like that's going over to the modem, the RF data. And so at the top there, we see a much more complex signal. And at the bottom here, we see this little single channel of data being sent. So it's at 915.1 megahertz. And that's channel 131 on the smart meter network. And so this terminal window here on the left is connected to the modem, that Landis and Gear modem that you saw on the table. And these are the different functions it lets you do. It lets you send test packets and set the channel that you want to receive on and receive packets, a bunch of cool tests. And so we'll set it to channel 131 and tell it to receive. And we see, hey, it's receiving good packets. Like these packets are coming across. It's a good signal. The CRC is correct. Everything about it is looking good. The only challenge is that it's only on one channel right now. So we're channel 131, but if we change the channel, even to the channel right next to it, nothing comes across. Any other channel other than 131 right now, it won't receive anything. But on channel 131, we're doing fantastic. It's like perfect data that comes across. It receives it every single time. And so I was pretty excited at this point because it's kind of really the first time I'd ever built a stream of information in GNU Radio and managed to transmit it out and had something other than GNU Radio receive that signal properly. Like it's kind of verified with another device being the Landis and Gear modem. And so this is the kind of more complex version, but the familiar setup you saw before where we feed the signal in and we try to scale it up. So let's send the same signal, but let's send it out on 10 channels as opposed to one channel and see how that works. And so we see there's my signal. There's 10 little bursts down there at the bottom that are coming out. They're not quite spaced at 100 kilohertz at this point, but I'm sending 10 and it looks like they're all grouped together and it looks pretty clean. And so I'm pretty excited about that. And so I add in some blocks that space it properly so that it's spaced at 100 kilohertz for each channel. And I'm also feeling pretty good. So I say, what the heck, let's add another set of blocks right below that to take those 10 channels and then multiply that by 2 basically, so that we send out 20 channels of information as opposed to 10, which is that block there that you see with the 2 inputs and the 1 output. And then we feed it across again to the software-defined radio output. And so here we see the burst of 20 transmissions down there. And now when we go over to our modem and we set it to channel 131, we receive data like we would expect. We see the data once a second. But if we set it to channels near 131, now we also receive data. So we're not just sending one channel of information at a time, we're sending 20 channels. If a meter were to hop and land in any one of those 20 channels, it would receive the information that we're sending. But outside of that, it wouldn't receive anything. So now it was to try to scale it up. But as I scale it up, you see at the bottom there, that would send 40 channels of information. And then I have another one that I scaled up to send 80 channels of information. But as I started to scale this, I started to notice this problem, and this sinking feeling as that the more I scaled it, in the bottom left, what you'll see is these little U's that start transmitting out. And what that means is that it's called an underflow. And it means that data isn't passing through my flow graph fast enough to get to the software-defined radio. It's basically when it's ready to transmit, the data is not quite there yet. And so how that translates into signals up top is that you see it's still receiving a good packet, but the problem is it's not receiving it every time I transmit it. Sometimes it gets it and it comes across, sometimes it doesn't. And so the system's becoming unreliable and we're only at 80 channels. So as we try to scale it up further, as I got to 260, just nothing came out anymore. I mean, it literally, there was so many underflows. So I was in the GNU Radio chat channel. There's a ton of helpful people there. And a guy named Dr. MPEG said, hey, I think you should use this FFT block instead. Like it's way more processor efficient. So I changed the flow graph all around and transmit the data out. And now you can see at the bottom there, that's a full 260 channels that's being transmitted. And no matter where I tell this modem to go, it receives the transmission. It receives the transmission perfect every single time. And so what this meant is at this point, I have a receiver through the Sandia Labs receiver that allows me to receive a frequency hopping transmission on any channel. And now I have a transmitter that allows me to transmit back on every single channel so that I can essentially interact with this network without knowing anything about the frequency hopping. So to say I was a little excited would be just, it wouldn't even begin to describe staying up all night long and trying to get this thing going. So I was pumped up. So now the game is to load all of this into the Faraday cage and try to send some intelligent messages. Now, these meters, they're not dumb by any stretch of the imagination. When you send data to them, it has to be proper data. And so when you see this setup I have here, I have this software-defined radio going into the Faraday cage over there, and I have a couple modems. One's in test mode, and one's connected up to the collector software. It allows me to run some tests there. And the game now is to take the data being transmitted from the smart meter, and it transmits out some sequence information and things like that, and to receive it, build my own packet, and transmit it back. And so that's what I'm working on as of this moment right now. If you enjoy this kind of stuff and following along, I encourage you to look at my YouTube channel. I document all this as I work on it. It's kind of a choose your own adventure game. Like you're watching where I am right now with these efforts. And I have a website here that has some links to a Discord channel and things like that, and a wiki where I post all my information, and anyone create an account here and and share and contribute if you want. I've had other people contribute findings here, and I either include their name or don't if they want to share who they are. And I have a GitHub as well where I share this. I believe in sharing everything openly. And so the transmitter stuff that I'm working on, as soon as it's cleaned up enough, I'll be posting it here as well. And so I really want to thank Hackaday for putting this on and for really having a community where all of us can come together and share this information and see what other people are working on. It's always super fascinating, and it's nice when we kind of come out of our closed environments here and share it all with the world. So I hope you enjoyed this talk.
Well, thank you very much, Hash. Yes, I really enjoyed that talk. It was a really interesting talk. Anybody who has any questions for Hash, then I suggest you go to the Discord and he'll be there and he'll be very glad to answer anything you have. Now, we're going to have a short break, a short intermission, and we will be back after that with Jay Doscher. So please hang around.
All right, we're going to do a little AV test. Jay, I see you're in the room. If you want to unmute and turn on your camera and test them, that's great. Just remember, it is going out live to the stream.
Hey, everybody.
Sounds very good to me.
All right.
And the camera view looks good. Did you have any questions before we get started?
I do not.
Great. All right. Well, if you want to mute your camera and mic again, Jenny will be back in about 2.5 minutes to introduce you.
All right. Thank you.
Hello, everybody, and welcome back. Now, over the years, we've seen a lot of cyberdecks and other homemade portable computers, but if there's one name that stands above all the others, it's Jay Doscher. His ruggedized and mil-spec Raspberry Pi computers take some beating, and to be honest, they can take a beating. But he's never been one to stand on his laurels, and we know that whenever he produces something, there'll be another one along sooner or later to improve upon it. Now, all this work requires quite a lot of CAD work. So he's going to be taking us through his work with Tinkercad, both as an introduction, he's offering us an introduction, as well as a path for those who are about to outgrow it. So hello, Jay, welcome, and take it away.
All right. Thank you, Jenny. All right, everybody, give me a second to get my screen share going. All right. And while I get this up and going, this is going to be an interactive session. So if you hop over into general, I'm actually going to be happy to answer questions and kind of deep dive where we need to. So we have a pretty flexible agenda. So first off, if you don't know, a cyberdeck came from, I believe, William Gibson movie or book, hopefully maybe a good movie someday. But the idea is it's a computer that was used in the books to connect cybernetically into the precursor to the internet. Today, what that really means is a scratch-built computer, usually the enclosure, a screen, USB ports, many times a Raspberry Pi, even though those are getting quite expensive right now. What I did was I bought a 3D printer. I started printing out things years ago, just trinkets and things like that. And I really struggled with slicers and all of the things. And then I started to look at options for CAD. And I looked at Fusion, and the first thing that hits you with Fusion is the price tag, frankly. And one thing led to another, and I started playing around with Tinkercad. And I could go back, and maybe if we have some time, this is my production Tinkercad account, and I can go back into the cringeworthy early things that I did that were mostly cylinders and things like that. I think the first functional part that I made was a part to fix a screen door. But let's talk about what Tinkercad is. Tinkercad is primarily an educational tool. But part of what's fun about just hacking in general is taking something that was intended kind of for one thing and using it for something completely different. We're not violating any terms of service here or anything. And in fact, Tinkercad encourages and has license options to share things freely and through many open source licenses. So it's cool that it's free. You can protect it with multi-factor authentication. And it's browser-based. Now, I like to use Tinkercad on a 4K screen. So if you're going to have a 4K monitor, you might want a fairly decently powerful video card to do that. But you can do it on a laptop if you need to, or if you're more patient. But it's very easy to get started. And I'm actually going to show you, Jenny actually implied, hey, some new stuff is coming. What you see on the screen is something that I actually have parts for something that's coming out soon, and I'm going to be sharing it. And I'm trying to make them even tougher. So we're going to actually take this one and we're going to take it apart. But before we go and take it apart, what I'm going to do is I'm going to show you some examples here of how this is very different from many other CAD programs. Many other CAD programs, and I'll use Fusion because that's the one that I'm starting with as a frame of reference, starts with a line drawing, a two-dimensional drawing. So if you were to draw something out on a piece of paper, and then you take that and you extrude it or you build up from there. Tinkercad works completely different. And the only reason that's a problem is that mentally, you kind of grow attached to the one that you learn. And so famously, I've said multiple times over the last couple of years, okay, I'm not going to make anything more in Tinkercad. I'm going to go over to Fusion. I'm going to go over to OpenSCAD or something. And I always come back to Tinkercad because it's so familiar and I'm so comfortable with it. I can work very, very quickly in it. So I'm going to show you some things that this design has that I think are going to be helpful for people. There are some things, though, that I want you to be aware of that are limitations of Tinkercad. I'll tell you right now, if you were to send parts out to get them CNC'd or laser cut or some of that, it's going to be limited, and you're going to have to do some extra steps with your files. It doesn't support DXF, which is common for some machine shops, depending on what software they use for cutting their parts. And SVG is limited. So even though I'm going to use an example here, I can actually go here. Let me move my screen, and I can go export, and I can say SVG here. But guess what? There's a little bug in Tinkercad. And if I move this down, this is on the build area. If I was to raise this up off of the build area, and you can see a little shadow there, and I export this as an SVG, it's an empty SVG. So there's some bugs like that. And that's, you kind of got to work around some of that. And the biggest one, the number one thing that you're not going to be able to do with Tinkercad is generate step files. And a perfect example is, I have a 3D model here. I could export this as an STL right now. In fact, I've printed a number of these. But if I wanted to send this to a machine shop, maybe I wanted to make a really cool one out of aluminum, which I would love to do, I can't do it with Tinkercad. And so I have to generate what's called a step file, and that's required for milling. And so guess what? The challenge is maybe I might be able to somehow convert an STL into a step or something like that. But if I need to go and modify it, if the machine shop comes back and says, hey, this tolerance is too low, and we'll talk about tolerances in a second, and you have to move this or move that, you're now jumping through all these extra hoops. Whereas if you were using Fusion or something like that, you could just move the whole reprocess, export the step file. So if you're planning on doing professional CNC, build in the time to learn a new tool. That said, if you're just going to 3D print stuff, let's have some fun, shall we? So this file is I'll tell you one of my secrets right now. I love to print on a smooth bed. So the face, and if I flip this over, let's see if this will flip over for me. This face is going to be on the print bed, and it's going to come out nice and smooth. Or if I have a textured bed, I could get the cool textured finish. But I don't use supports, and I try to make things that don't use supports. So when you're designing something, you want to keep that in mind. And I'll use an example. This is the frame for a cyberdeck. And I'm going to lower this back down. Okay. And if you look, here's my bracket, and I use these two little holes. I have a little hole there and a little hole here, and those two align it. Now, another thing that CAD programs are great for is making parts line up. If you need a hole to line up, or if you need a joint or a hinge or something like that, there's all these complex functionality that you can do for that. I have some tips and tricks that we're going to show on how I do it. So first off, I'm going to select both of these parts. I'm going to come up here to align. And then what I'm going to do is I'm going to click the red part, and I'm going to click this to align it to the left. And then I'm going to click up here to align it to the top. And then I'm going to pivot down, and I'm going to align it to the top. And you can see here, it's kind of got this weird color. But if I click this green one and I just raise it up, I've made these parts so that those holes line up, and I'm going to show you how I do that. And we'll start with this bracket. The bracket's the easy one. So you can go in, by the way, any of the stuff that I've shared on back7.co, and I point back to the Tinkercad files. I get many, many people that say, hey, can you send me the mechanical drawing for this? Or hey, can you send me the source for this? Tinkercad's really cool. All you got to do is go in here and click ungroup. And we click ungroup, and what do we see? We see what's called a softbox, and then we have another softbox inside of it, and then we have another a set of cylinders. Now, each one of these cylinders has a specific size. I'm going to talk about sizing in just a second. But this middle piece is here just to save on plastic. We could easily, what I like to do is instead of deleting it, I like to raise it up. We can look at it this way. So I could easily print that. It's going to print more plastic, and it's not going to help us any. So I'll hit Control Z and put it back. Now, a few of these holes are for the screen mounts. So you can see those are 4.3. I actually had to make these larger because I heard back, like I mentioned earlier, I heard back from a CNC shop that said, hey, we can't make holes that small, make them bigger. And so I did. So these are all 4.3 millimeters. And if you'll notice, these are 5.1. Now, if you know any of my builds, you know I love M5 screws. I love to use M5 screws. And part of it is because I kind of have these kinds of things on speed dial. And so if you look though, why would I make a hole for an M5 screw 5.1? And it's a very simple answer. When you 3D print, even a very well calibrated printer is going to extrude a little bit out, which means the part's always going to be a little bit bigger than what you wanted, and the holes are all going to be a little bit smaller. So when I make this, I don't actually want my M5 screw catching on these holes. So I make it just ever so slightly bigger. Now I'm going to leave that ungrouped, and the more interesting lessons come in this red part. And so I'm going to ungroup that. And boy, you see a bunch of crazy stuff. So first off, we're going to look at this hole here. And I'm going to ungroup that. You're going to see this one. And if I extrude this up, you're going to notice they match. This is part of how I do parts. So if I wanted to actually make another one of these, I could actually bring it in. And I'm going to lower it down a little bit. And again, align it with this one. And we'll make it a little easier to, we'll make it a different color here. We'll make it a nice pink. And again, I'm going to hold down my shift and select both things and then go to align. Oops. Ooh. Undo. I'm going to hold that and that one and align. And I don't want this bottom one to move. So I'm going to click the yellow. And now you notice the pink part. So now in Tinkercad, I literally can Control C, Control V, and bring up. And so now I have, and I'll make it orange so it's easy to see. I'm going to zoom in here, and I can actually then center it based on this bottom one. Select it, move it up. I'm going to change it from orange to a hole, and I'm multi-select the pink part, and now I'm going to group them together. Now I have a hole that lines up with the part below it. So it can be a little tedious, can be a little bit messy, and it's time consuming, sure, but you can easily make parts that line up like brackets. So now what I'm going to do though, is I'm going to get rid of that bracket. We don't need it with what we're going to do next. So now you can see I've got the base. You can see I've got the hole for the screen, and I'll tell you, if you are looking at making parts, and if you don't have them already, just for handy reference, a metric, I use just a cloth tape measure for big stuff, just to get rough part size, and then calipers. You get cheap ones. I think they're 20, 25 bucks on Amazon, and measure, and test print. And we'll talk about that in a little bit. So we've only got a few minutes left, so I'm going to kind of go through this a little bit faster. But if you look, you can see I've got everything kind of grouped together. So here's the jack for the Ethernet. And I know, hey, there's my M3 screw, but notice I've got it at 3.5. I know from experience, the Ethernet brackets or the Ethernet ports or jacks that I buy don't have great tolerance. And they got a little nut that kind of floats in there a lot. So I've made that hole just a little bit bigger. But I can take this piece, and this piece, and I can literally group them together. So now I can take those and I can move those wherever I want in my project. So, so that's like an Ethernet jack. it makes it really easy for me just to go through and reuse one, on future projects. Here's another one of my favorites, actually. This is a more recent one. And we're going to move it out so it's a little easier. Oops. Control Z here. Yep. So let's see. Yep. Okay. All right. So thank you, Jenny. So if we ungroup this, if you look, this is a notch for the USB-C power. And if I group this together, and now this is going to require a little bit of mental gymnastics, but bear with me. So the hole that I know that it needs for the jack is 15.5 millimeters by 15.5 millimeters, but it's got a flat side to it. And that flat side keeps it from twisting. It also makes it aesthetically a little cooler because, well, frankly, it makes it so the USB-C port always kind of lines up one way or the other. But it would be a really complicated thing to go through sometimes and create some custom grouping or something. In fact, it's actually pretty easy. So I start off with my cylinder, and notice it's not a hole. And here's my flat side that I know happens to be 1.1 millimeters. And I'm going to take those and I'm going to group them together. So now I have my flat side cylinder, and then I can change this from a solid to a hole. And then I can actually stretch it out and make it as big as I want for grabbing on. I can move it around. So, and if you look, you heard the expression kind of turtles all the way down. This is groupings all the way down. So if we go and take this apart, what you're going to see, if we take this and ungroup it, it's more rounded rectangles. We've got some trickery up here, but it's a pretty simple part. So that's kind of, I would say, some of the basics on what you can make. Pretty straightforward stuff. I'm going to use one more example, and this is one that I actually have the prop and it's actually finished and printed. And that one is this one. I call it the next generation camera, and I've got a V2 on here for myself. And if you look, if I ungroup each one of these, you're going to see multiple cylinders, but you're going to see they're at different heights. And you're going to see kind of little steps inside of each one. And that's for these little things right here. And I'll hold one up to the webcam. These are threaded inserts. Now, normally on many of my decks, for an M5 screw, I'll make the hole 4.8 millimeters wide, and I'll just pressure fit the screw in. And if it's just getting assembled once, I think a popular YouTuber went and did a bunch of stress testing on threaded inserts versus pressure fit, and they're basically about the same strength. But the pressure fit ones, you can strip the threads, you can wear them out and stuff like that. But I wanted to make something to hold the next generation Raspberry Pi camera. I have one. I need to experiment with it. It's kind of heavy and kind of ungainly by itself. And I wanted something that would hold a Raspberry Pi and the camera. And I wanted something where I could attach and detach different things to it, because I wanted to kind of create one unit. And all of these parts are essentially it. Now, this part up here, I haven't made yet, but I'll hold up here and show you. This is what it looks like assembled. And each one of those holes has a pressure fit in there. Or sorry, not a pressure fit, has a threaded insert in each one. And so threaded inserts are probably not something I would consider beginner, but they're not that hard. You can get soldering tips for the threaded inserts on Amazon. I think it's like $20 for a set of 5, and that includes like M5 and M3, which are and even a little tiny M2.5 one. So I think from there, I'm going to hop over and I'm going to take a look at the questions in the, I'm going to look in both the general chat But if you have questions, feel free to jump into the Remoticon questions. I'd be happy to answer any questions you may have. Feel free to tag me. I'm in there as back7 at BACK, the number 7. But I'd be happy to go in and take a look and answer any questions that you might have about Tinkercad. While I'm looking for folks to ask questions, I will go into the gallery here, be a little brave, and go back into the very first, let's see, we have 31. You can see me printing out toys. You can see camera supports, solar receptor. You can see me starting with different kinds of pieces. So I see and I have a lot of hacker friends that talk about OpenSCAD. I would say if you want long-term kind of support, you want something that's free, you want something that works offline, it's pretty much got to be OpenSCAD. Tinkercad does require internet and does require an Autodesk account. Fusion can work offline for a little while, but does essentially need online access. The one thing that I would also add is that you really want to make sure that you're thinking about what it is you're trying to do. So if we go in and look, part of what I used Tinkercad for was learning about different aspects of design, making different brackets. I see Elliot's mentioning FreeCAD. I'm not familiar with FreeCAD, but definitely think about and make think about what, like, be intentional about your use of the platform. Yeah, and I see a question from Kevin. Am I worried about them charging for Tinkercad at some point? I'm not particularly worried, frankly. This is a great educational tool for individuals, and they really are focused on getting, and this is, frankly, it is designed for children. So if we go into the different shape galleries, they've got a lot of stuff in there for kids. I'm not worried about them charging for Tinkercad. But again, a lot of the designs that are in here aren't really portable to other systems. So I could take an STL out of Tinkercad and into another CAD program, but I'd still have to reverse engineer them. So that's the thing that you have to keep in mind, is that it is free, it is easy to use, but longer term, you want to definitely be looking at other platforms. All righty, let's see, I think we got one other question. So Immersive Pencil asks, why did I get into making? Well, I started I've been making stuff for quite a while. I would say earliest for me has been woodworking in high school. And it's very satisfying to have an idea and bring it into the world. I think it's immensely rewarding to do that. I would say I started back7 stuff after doing a class with Jimmy DiResta out in upstate New York, where I did blacksmithing and I did axe making, neither of which are realistic for me here in Southern California. But I learned you can focus your energy and focus on the things that you're passionate about, and that's part of what this is. As with CyberDex, I made the first one, and in fact, you can see it. It's hiding. It's sitting right there on my desk behind me. That's the first one I made. I think that's the Raspberry Pi recovery kit. I made that before I knew what CyberDex were. So I found the community after I made that. And I still love making them. And I make the plants freely available. I also sell them. And there's just so many different stories that I see. People tag me on Instagram all the time of things that they've made them for. Ham radio geeks use them. People use them for direction finding, off-grid computers, all kinds of stuff. So yeah, so NA, I think if I'm getting your name right, what's my strategy for multi-component projects and parts? We're almost out of time, but let me show you an example of one that I'm working on right now. And the really what it comes down to is making stuff line up and making stuff fit. And what I will do is I will do test prints. And so here's an example of one that I'm working on right now. And if I take this file, this yellow file, and actually, if I reach under my desk, I actually have a test print of that file. So I test print, I make sure that it fits within the enclosure or the space, and then I start printing. I don't often do, I rarely do top infill, top layers and things like that, just because I don't need it. I just need to make sure the shape is right, just need it to be rigid. That's part of the challenge, is making some of these more complex things. I kind of bump my head up against the limitations of Tinkercad, and I will need to move to another platform soon. I would say, Dim, I see you asked the question, would I say that planning builds in Tinkercad is still worth it if you're not into 3D printing? Yes, just for fit. Perfect example. I'm not a mental 3D person. I know what I think looks good, and I can see it on the screen, and I can say, yep, that's what I want. But if you ask me to visualize the clearance on one of my cyberdecks of the USB ports and the Raspberry Pi and the display and the bolts, I can't do it in my head. So I rely on a combination of CAD and the actual physical model. Now, if I had a more kind of professional CAD setup, I'd have 3D models for all of my parts. Like, you can actually import like a Raspberry Pi, and you can make 3D models for all of your stuff. And then you could just do it all in CAD. In fact, professional CAD folks, that's what they do. They have all of the components where I kind of get this close, kind of visualize it, throw it together. So this is not a professional setup. And so yes, you can, so real quick here, because I think we're almost out of time. If I go and collect the export, it will do everything in the design, which is like an unusable file. Or I can go in and click an individual file and click export, and I can export as an OBJ or a GLTF or an STL. And so, yes, you can do them one at a time. All righty. So a couple things that I would make sure to do if you're interested in cyberdecks. You can either follow me on Instagram. I'm kind of just there now. I'm not really anywhere else, at back7.co. You can message me here, and I can either provide a link for the Cyberdeck Discord, which is a fantastic Discord server. I kind of the one putting stuff in Pelican cases, but there's so many other designs out there. But hit me up. I'm on Discord. And happy to help. So with that, Jenny, I'll pass it back to you.
Hello, hello everybody. Thanks Jay for that talk. That was a fascinating talk. We're going away for about quarter of an hour right now. If you have any questions for Jay, you can find him on the Discord server. But meanwhile, stick around, because in quarter of an hour we'll be coming back with Joey Castillo. Thanks very much, everybody. See you in quarter of an hour.
Hey, Joey, if you can hear me, do you want to go ahead and turn on your camera and unmute your audio so we can do a quick AV check? Hey, Tom. Do you want to go ahead and unmute your audio and turn on your video so we can do the quick AV test? Tom, can you hear me?
Oh, okay. Now can anyone hear me? Okay, great. And is it possible I could just make sure to test my screen sharing?
Can you hear me?
Yes, I can now.
Okay.
Yeah, I think if I can't share my screen while y'all are sharing.
Mm.
That's right. We'll do the screen share during your presentation, unless you want to try it out now, in which case I can stop the current share.
Would
so
you
that
mind just to make sure, because I updated Zoom and I want to make sure.
Sure, no problem. Let me stop the current share. Okay, Joey, you should be able to go ahead now.
Okay, I think that worked. Thank you.
No problem. I'm going to go ahead and put the countdown video back up, and we can go ahead and turn off our audio and visual until that timer gets to 0.
Great, thank you.
Thank you. Okay, Joey and Tom, we are set for you to take it away.
Okay, well, welcome back to the Hackaday Remoticon. I'm contributing editor Tom Nardi, and I'll be introducing our next guest, who is perhaps best known to Hackaday readers as the creator of the Open Book, a very impressive and I think very important project that aims to design a fully open hardware ebook reader. But he's recently found himself with a new obsession, and today he's here to talk to us about the lowly segment LCD, specifically how they can be reverse engineered and ultimately bent to our will. So with that, please join me in welcoming Joey Castillo to Remoticon.
Awesome. Awesome. Thanks so much for that introduction. So I'm Joey, and my talk today is about kind of an old school display technology, segment liquid crystal displays. We have a lot to cover, but before I start, for those of you who don't know me, I figure I should do this. Who am I? And I can probably share my screen for this part. Let's click on screen share, desktop 2. Okay, great. Who am I? I'm at Jose Castillo on Twitter, where I share a lot of my process working on open source gadgets. A little while back, I designed this thing called the Open Book, which Tom just spoke about. And then recently, I've been working on the Sensor Watch. It's a board swap for the Casio F91W wristwatch, which is in pre-launch at Crowd Supply if you want to check out that link down there. It's in working on this latest gadget that I've learned a lot about LCD displays, these sort of old school, low cost, low power displays that you can find in lots of gadgets, from watches to pocket calculators. They're ubiquitous, they're cheap, and they're seemingly ideal for repurposing into hobbyist projects. Before we get to the talk though, let's just overview what segment LCDs are. They're generally small glass displays, and they tend to be monochrome, just black and white. They're very low power. This makes them attractive for battery-powered gadgets like wristwatches and digital thermometers, but could also make them attractive for DIY projects that want to use energy harvesting or solar power. And finally, they have a fixed layout, which is to say, you can't display arbitrary shapes on them. You're limited to turning individual segments on and off. This makes the layout of the LCD crucial to how useful it can be for your project. The display up top, for example, with just 3.5 digits, won't be as versatile as the display on the bottom with 8 alphanumeric characters. This is why I'm super into repurposing the LCDs from existing gadgets. These displays tend to have useful layouts for displaying a lot of information, like this Casio calculator watch. They're also often thoughtfully designed by, actual designers who do this for a living. This makes their designs nice in a way that industrial LCDs often aren't. They also tend to be thinner and finer pitched than off-the-shelf LCDs. The F91W LCD is sort of staggeringly thin. It's only 1 millimeter thick, and it's small enough to fit in a 38mm watch case. The finer pitch also allows for more segments to be addressed in this already small area. They're also just fun. Here's a watch with the Sensor Watch board swap installed. I've taken the F91W's display, which is only meant to display the time and date, and I've repurposed it to be a temperature display, 76.6 degrees Fahrenheit. Now, it's not perfect. The 7 is sort of a shorty lowercase 7, and the decimal point is a hyphen since there's no decimal point in this design. But if you're willing to embrace the limitations, you can take a small, well-designed display and coax it into doing all kinds of interesting stuff. Okay, so let's set the agenda. Today, I'm going to talk about how you can find these LCDs in the wild and bend them to your will. First, I'm going to introduce segment LCD tech, show off some of how it works, and explain what's required to drive very basic LCDs. Next, we're going to look at more complex LCDs through the lens of the classic wristwatch that I used to build the Sensor Watch. Then we're going to use what we learned in sections 1 and 2 to reverse engineer the LCD in a much more complex watch. And finally, if we have time, I'm going to share some of what I learned designing a custom LCD of my own. So that's a lot. So let's jump right into it. Chapter 1, Intro the Tech. I figured I'd start with a compare and contrast with a technology a lot of folks here are probably familiar with, segment LEDs. On their face, they look kind of similar. Each segment has a pin, and there's also a common pin. So for a 7-segment display like this, you'd need to run 8 wires to each digit. I've drawn a diagram here for how that works, and I actually found that I had to draw 2 diagrams, because you'll always find that these segment LED displays are either common cathode or common anode. That's because for a segment in the display to glow, current has to flow from the anode to the cathode. It's a complete DC circuit. You'll still use 8 wires with an LCD, but the first difference is in how the display works. Current doesn't really flow anywhere in an LCD. Instead, segments are energized when a difference in voltage exists between the common and the segment electrodes. You can imagine an LCD segment as being a little capacitor, with the special property that when there's a difference in charge between the segment pin and the common pin, it will darken and become opaque. That common pin is neither anode nor cathode, because you drive an LCD with an alternating signal. Sometimes COM is high, other times it's low. LCDs don't like a static charge building up on either side, so you have to alternate the polarity of the charge. What do I mean by that? Well, here's what it looks like. And I beg you, please stick with me through these scope traces. I promise they're going to make sense by the end. The voltage differential between the common and segment pin has to be above a certain threshold for a segment to turn dark or energize. Typically that's between 3 and 5 volts, but let's just go with 3 for now. Here we're looking at one common pin in cyan and one segment pin in yellow. The difference between the two is in purple. You can see that when the common and segment pins get the same square wave, there's no voltage difference and the segment is not energized. But when the segment pin's wave is inverted relative to the common pin, suddenly the voltage differential is plus or minus 3 volts. That's enough to energize the segment. The cruxy bit is that this has to be an AC signal with no DC bias. The frequency will depend on some factors, but don't worry about it too much for now. For now, let's give it a whirl, and let's do it really simply. This is a circuit Python script, and it should be easy to see what it's doing. It's setting up digital outputs for one common pin and a bunch of segment pins, as well as a button input. When we loop, we repeatedly set COM high and low by toggling this phase variable. If the button is up, we set all segments to the same value as COM, which gives them all the same square wave. But if the button is down, we set our on pins to the opposite value, giving them the opposite wave. So let's check it out. So here I have my Metro M4, which I've set up with this button, and my wire is going to the display. So the COM pin I've actually tied to the LED here, so you can see it flashing high and low. That's actually the frequency of the wave we're feeding this LCD. So we're not talking megahertz or even kilohertz here. This is in the dozens of hertz. You can see it with your eye. So right now, they're all getting the same square wave. But when I press the button, it's energizing the segments that are saying high by inverting the wave on those segments. I also have my little pocket oscilloscope here, and it's showing the difference between COM and seg, which is 0 until I press the button, and then it becomes plus or minus 3 volts. Okay, so that is section 1. To recap quickly, LCD segments are basically little capacitors that turn dark when they're charged. These displays are low power because current isn't really flowing anywhere. They do need to be driven by an AC signal. This part is important. The astute viewer might be thinking, hey, I could energize a segment by holding COM low and seg high. And that is true, you could, but it'll break your LCD after a while, so don't do that. Finally, the key is to keep the driving voltage across the segment below the threshold to turn the segment off and above the threshold to turn the segment on. Keep that in mind as we move right along to section 2, multiplexed displays. So at this point, you should have the gist of how LCDs work. Now we're going to take these basics and apply them to a more complex display, the display on our dear friend, the Casio F91W. So you'll notice there are a lot of segments on the left there. They're all driven by the row of pins on the top of that green circuit board, but there are a lot more segments than pins, which begs the question, how do they pull that off? What gives? And the answer is LCD multiplexing. So in short, where that screen from our demo had one common backplane, the F91W's LCD has 3. That means 3 common pins, and the rest, 24 of them, are segment pins. Whereas in the demo, the COM pin was linked to all of the segments, in this watch, each common only touches about a third of the segments. And whereas in our demo, each segment pin was linked to 1 segment, in this display, each segment line is linked to 3. The important thing here is that each segment that you want to address individually will have a unique common segment mapping. Okay, so yeah, I admit, that diagram was a lot to take in. To make it easier on ourselves, let's consider one segment in isolation. This is segment A of the last digit in the clock, which ticks the seconds. We would call this COM2 seg19, just numbering each pin from the left to right. You'll see that while COM2 is linked to a whole lot of segments, 24 of them all tinted in red, seg19 is only linked to the 3 segments tinted in blue. Only the purple segment, segment A of the seconds display, is linked to both COM2 and seg19. And that's the key to how we can address it individually. So before we do this ourselves, let's see how the F91W energizes this segment. Since the watch ticks once a second from 0 to 9, this top segment will be energized and de-energized fairly often. It's off when displaying the digits 1 and 4, and it's on the rest of the time. We're going to use a 1990s era Tektronix 2211 scope to visualize how the F91W achieves this. So here I have my F91W movement plugged into these oscilloscope probes, and the scope is showing us COM2 up top and seg19 on the bottom. So COM2, seg19. Technically, that's the inverse of seg19, but bear with me for a moment. So the interesting part comes when we subtract seg19 from COM2. So now we're seeing a lot of different waves, but the key is that there's really two peak voltages, plus or minus 3 volts and plus or minus 1.5 volts. Okay, so what did we see here and what can we learn from it? First, right at the outset, we saw the two waveforms separately. We saw that the COM waveform didn't change at all. It's just delivering 3 voltage levels repeatedly. We also saw the seg waveform with just 2 voltage levels and that it changes from time to time. Next, when we subtracted one from the other, we saw several different waveforms, but really 2 peak voltages, plus or minus 3 volts and plus or minus 1.5 volts. This tells us the voltage we need to energize a segment. This is a 3-volt display. So you might be asking yourself, in that middle photo, the segment only hits 3 volts about 1/3 of the time. Why is that? What about those other moments in between the plus or minus 3-volt peaks? And the answer is, those are time slots for the other segments. Remember, seg19 is controlling 3 segments on this watch, and we're only looking at it in relation to COM2. COM0 and COM1 are also doing their thing, and plotting seg19 against each of those would yield a different trace. So our workshop, The Prepared, also has a more modern scope with 4 inputs, and we can use that to visualize the waves in more detail. Here we have our segment 19 waveform in yellow, and our COM0, COM1, and COM2 waveforms in cyan, pink, and blue. It's actually easier to see this if I stack up all the COM signals. So looking at the top there, you can see 6 distinct phases in the period of this wave. COM0 has a beat at 3 volts, then 2 beats at 1.5 volts, a beat at 0 volts, 2 more beats at 1.5, and then 2 more beats at 1.5 volts. Basically, over the course of the wave, each COM signal has a chance to be at its maximum and minimum value once. And the other signals hang out at 1.5 volts in between to give them their turn. This is how we're going to get to the key terms for this slide, duty and bias. With 3 COM lines, we have 3 chances for each common to hit its maximum and minimum voltages. That makes this a 1/3 duty waveform. Not coincidentally, that corresponds to the number of COM pins that we have. Bias refers to the intermediate voltage level involved in driving the LCD. Looking at the common waveforms up top, you can see 3 voltage levels, 0 volts, 1.5 volts, and 3 volts. That 1.5 volts makes this a 1/2 bias waveform, 3 volts divided 2 ways. If you had intermediate steps of 1 volt and 2 volts, it would be a 1/3 bias waveform, as in 3 volts divided 3 ways. These two terms combine to describe the waveform. 1/3 duty refers to the number of COM pins, and 1/2 bias refers to the single 1.5 volt bias voltage in between 0 and the LCD voltage. The line in purple, again, is showing us the difference between an on state and an off state for this segment, looking at COM0 this time. The important thing to note is the COM waveforms never change. Look at the state of the yellow seg wave right after that first cursor. In that trace at the top, it's high when COM0 is high, which adds it to 0 volts, segment off. When COM0 goes to 1.5 volts, no matter what seg19 is doing, the difference between the two can't be more than 1.5 volts. That's something, but it's not nearly enough to hit that 3-volt threshold, so the segment again remains off. Now look at it in the trace at the bottom. The segment line here is low when COM0 is high, which adds up to -3 volts, segment on. This same process is repeating 2 beats later with the opposite polarity. It's also happening the whole time with the segments attached to COM1 and COM2 during COM0's 1.5 volt phase. So each of those segments connected to seg19 are getting their own unique waveforms that can turn these segments on and off independently. So I added this slide late, but I realized You might be looking at this and thinking, how am I supposed to generate all these waveforms and bias voltages anyway? This seems complicated. Well, the good news is, if you pick a microcontroller with an integrated LCD driver, all this hard work is done for you. This is the datasheet for my current favorite microcontroller, the SAM L22 from Microchip. It's a lot like the SAM D21, but it has an LCD driver that's fluent in the language of segment LCD glass. So if you use a chip like this, instead of trying to figure out how to generate a waveform that turns off all of your segments, you can just write directly to display memory. Or if you want to go one level further, you can use vendor driver code that abstracts even that away and lets you deal with the LCD using function calls like a civilized human. It's pretty cool to drive both your logic and your display with one chip. And while this list isn't exhaustive, there's definitely a fair number of microcontrollers out there that you can use to drive an LCD without getting your hands dirty. Okay, so here's a question. How exact do you need to be with this? Like the waveforms we were looking at, do we have to replicate that waveform exactly to drive this LCD glass? And the answer is not necessarily. This LCD glass is a pretty simple thing. The SAM L22 likes to drive a 1/3 duty displays with a 1/3 bias waveform, which again involves intermediate voltages of 1 and 2 instead of 1.5. This display glass was perfectly happy with that. Again, the key points are to drive the segment above its threshold to energize it, to keep it below its threshold to turn it off, and to avoid any DC bias in the waveform. The SAM L22, with its integrated segment LCD driver, is easily able to check all of these boxes. Okay, we'll recap later. For now, we're rolling right along into section 3. We've covered the basics of LCD technology, and we've talked about how complex displays use different multiplexing schemes to drive displays with more segments than pins. Let's take those lessons and apply them to another Casio watch, the Casio Databank. This is a really cool watch with a lot of segments and a lot of buttons. It would be a blank canvas for displaying all kinds of cool information if we could figure out how to drive it. So let's figure out how to drive it. But first, let's take it apart. What do we see inside? Well, we have a backplate and a rubber gasket, and then a circuit board sandwiched in between two assemblies, one for the battery and one for the display. The circuit board itself has 55 exposed LCD pads, 28 in the top row and 27 in the bottom. Finally, we glossed over this point earlier, but I do want to point out the 2 elastomer strips sitting in the LCD assembly. These are commonly called zebra strip connectors, and they're the way the LCD actually connects to the circuit board. I do want to stop here for a quick detour on these elastomer strips, because if you do try to upcycle an LCD, you're almost certainly going to run into them. These are called zebra strips because they have many conductive stripes. You might also see them referred to as ledge connectors, since they mash up against the ledge of glass with the electrodes, which you can see reflected there in the glass. The idea here is that your display's electrodes have the exact same spacing as the pads on your PCB. And the zebra strip is way denser, so when it gets squished in between, there will be at least a few stripes making contact, which makes a vertical connection between the board and the glass. They do require very precise alignment, especially for a fine-pitched LCD like the one on a wristwatch. But on the plus side, any gadget that uses this technology is going to come with a strip that works and hopefully an enclosure that holds it in place precisely. Just don't lose it. Okay, back on track. Let's reverse engineer this databank LCD. To do it, we're going to need some tools: scissors, an oscilloscope, and blue painter's tape. Actually, later on, I reshot some of this with Kapton tape, but you can just use plain Scotch tape. All we're doing is taping over one pad to break the connection between the LCD glass and the PCB. Why are we doing this? Well, we're doing this because some of these pins are common pins and some of them are segment pins. And before we do anything else, we're going to have to figure out which ones are which. So with this one leftmost pin covered up, we reassemble the watch and we get this screen, which looks pretty similar. Not much has changed. But there's this neat trick with a lot of Casio watches. If you press both left buttons and the bottom right button at the same time, oops. There we go. You can turn on all the segments in the watch. When we do that, we can see that we lost 5 segments, 2 of them in the dot matrix and 3 down there in that year display, which brings us to the first guideline for reverse engineering these things. If a few segments turned off when you covered a pad, you've found a segment line. This should make sense if you recall our diagram from earlier. The COM line sweeps across a vast swath of the display, but the seg line only touches as many segments as there are COM lines. The fact that we lost 5 segments when we covered this pin strongly hints to me that there are 5 COM lines. It's not a guarantee, sometimes segments can be shared, but that is my suspicion at this point. Okay, moving on. Let's try covering up one pin on the opposite side of the board. What happens then? Answer, we lose a ton of segments, which brings us to the second guideline. If a lot of segments turned off when you covered a pad, you found a common line. This should follow from the diagram, but let's just throw it on screen again. The COM line intersects with as many segments as there are seg pins. So if we had 5 COM lines, we'd expect losing one to lose us about 1/5 of the segments. Okay, so now I'm just going to start covering up pads on the right side of the board. Here it is with one pin covered, and covering a second one. Again, we lose a big chunk of the display. This is another COM line. Third pin, another 20% of the display is gone. Fourth pin, only 50 segments remain, 34 in the dot matrix and 16 down at the bottom. And with 5 pins covered, the whole display goes blank. So get this, by covering 5 pads with plain old Scotch tape, we've discovered not just which pins are the commons, but also half of the segment mapping. Because if you look at the segments that were left when only that last COM was working, COM 0, again, numbering from left to right, we know all of those red segments must be attached to COM 0. Working backwards based on when we saw the segments turn off, we have all of the COM lines mapped out. Moreover, we can combine that with what we saw when we taped off the top left pin, seg 0, again, numbering from left to right, and we now have full segment addresses for 5 segments of the display, those 2 in the matrix and the 3 on that bottom row. So there's one last step to know how to drive this display, and that's to figure out the voltage required to turn on a segment. We'll use the scope for that, but before we do, I find it helps to locate one segment that toggles fairly often. Ideally, I'd like to find a segment in the ones place of the seconds display, since all of them change at least once every 10 seconds. In this case, I just had a lucky guess. I just taped off one of the pads on the right, and it was the one that controlled the seconds display. So with that, to the scope. I really wanted to do this piece live, but it's a bit fiddly to keep the movement clip down while measuring, so I have it on video. But if you look at the scope traces, the key is that you can see the peak-to-peak voltage of the COM and the seg pins, and you can also see the purple waveform changing, de-energizing the segment from time to time, so we know we're on the right track. Okay, so what did we learn from this? Well, we know the duty is 1/5 because there are 5 COM pins. We also see 3 non-zero voltages, making this a 1/3 bias waveform. The most important thing, though, is we were able to measure the peak-to-peak voltage on the COM and the seg pins, and it looks like just about 4.1 volts. I actually measured this again later with a full battery and got 4.5 volts, but either way, it means my favorite LCD-oriented microcontroller, the SAM L22, can't drive this display since it maxes out at 3.6 volts. But that doesn't mean it's impossible. I'm going to throw up that list from earlier, the one that showed chips with built-in LCD drivers, and I get the sense that this PIC16 has the oomph required to drive a 4.5 volt LCD. With 53 pins, it might not be able to drive all of the segments, but you could get pretty dang close. Okay, so let's recap this back third of the talk. We talked about multiplexed LCDs and addressing them by their common and segment pins. We looked at some of the waveforms that drive these multiplexed LCDs, and we talked about how duty and bias work. We talked about microcontrollers with LCD drivers that can help wave away some of these complexities. But we also saw how understanding these concepts gives us the ability to poke at LCDs in the wild and understand how they work. So it looks like we have time, so this is the bonus round, in which your speaker discovers that it's actually not that impossible to have your own segment LCD manufactured. This is the Sensor Watch dev board. It's in a feather form factor, and if that LCD layout looks familiar, there's a reason. It's specifically designed to match the pinout and layout of the F91W LCD. Why do a custom LCD? Well, the answer will vary from project to project, but in my case, I needed something specific. I wanted to make a board whose display matched the one on the Sensor Watch, so folks could test their apps more easily. To do that, I needed a screen that matched the F91Ws. You may also have design constraints. In my case, the existing F91W LCD was too small, too thin, and too fragile for this application. I tried it. It barely worked. I almost crushed it to death. This also only makes sense if you want to make a lot of them. So there's an initial tooling cost that can range from hundreds to over $1,000. I bit the bullet and did it because I hope to end up making a lot of these, but it's not ideal for making just 5 or 10 of something. But if you want to make 1,000 of them, you could end up spending as little as $1 each for a display this size. And if you wanted to make 10,000 of them, you could end up spending even less per display. One note, this is not to say that you can spend $1,000 for 5 prototype displays. You'll need to work with a manufacturer, And their whole process is oriented around figuring out the tooling and then making a reasonably large run of the same display. So it's not for everyone. But if you're building a product and you need something more custom, this process could make sense for you. Okay, so to make a custom segment LCD, you can use just about any vector graphics program, Inkscape, Illustrator, whatever. Your manufacturer may ask for an AutoCAD DWG of your design, but I was able to provide an SVG and it worked just fine. Personally, I used Affinity Designer to lay this out and it worked great. Remember, you can't draw more segments in your design than you can actually control. The number of segments you can drive is going to be equal to the number of COM pins in your design times the number of segment pins. But you can tie multiple segments together. For example, the PM and the signal icons, those are just one addressable segment. Same with those 3 segments of that weird number in the date display. You can turn all 3 of those segments on or off, but you can't control them individually. It's a trade-off, right? It makes that position only good for displaying the numbers 1, 2, and 3, but it means you only need 4 addresses for that digit instead of 7. Next, you'll want to draw up a datasheet. Some LCD fabricators will just take your drawing and make it happen, but if you provide some more details, you can have a lot more control over the outcome. So you'll want to specify dimensions. Remember, there are going to be manufacturing tolerances, so this is just a nominal dimensions sort of thing. They will come back to you with final dimensions for your approval. You'll also need a bit of margin on the edges because they need to seal the glass and you can't have any segments in the area where they do that. Optionally, you can specify a segment map. They can just pick a map and route it for you, but if you have constraints like I did, you can specify it. Note that they may not be able to accommodate your segment map. Routing an LCD is a lot like routing a single layer board. So if your layout is particularly complex, they may not be able to route it. But you can at least specify certain things that are important to you, and you can hope that they can accommodate it. Finally, you need to specify some required parameters, and I'll just go over them very quickly. TN, or twisted nematic, is the most common type of LCD. It's cheap and it works well for segment LCDs. Viewing direction. Basically, it refers to the angle folks will view it at. It's like the clock hands. If they're looking at it from slightly below, like a wristwatch, it'll be 6 o'clock. If they're looking at it from slightly above, like a desk clock, it'll be 12 o'clock. Polarizer mode. There's 2 pieces to this. Positive means it's a light display with segments that darken when they're energized. And negative is that cool inverse look where it's all black and the segments turn light. Transflective has to do with the polarizer on the back of the glass. Transparent is totally see-through, like a heads-up display. Reflective is totally opaque. Transflective tends to be the best of both worlds. It has a backing layer so you can see the display, but it's semi-transparent so you can also light it from behind. Driver method we talked about. Duty will match the number of COM pins in your design, and your LCD driver's datasheet will likely recommend a bias scheme for a given duty ratio. Operating voltage, again, you just want to ask for something that works with your chip. They made me a 3-volt LCD. It is pretty standard. Temperature, I didn't really care about. And then connection method. I asked for zebra strip, which meant I needed to make that 3D printed enclosure to hold the whole thing together. It also meant that I had to find some zebra strips on eBay. You may want to have them crimp pins on, but this part is entirely up to you. Finally, there are some notes, but the only one I want to call out is the filling port. So after they etch your glass, they need to fill the inside with fluid. That's the liquid in a liquid crystal display. This means there will be a filling port bumping out from one side of your display glass. It's just a small bump of glass, about an extra millimeter. I asked for it on the bottom, they put it on the left. In my case, it really didn't matter. Just know that you'll have to account for that bump in your enclosure design. And again, they will send you a final data sheet with all of these dimensions for approval. Finally, you don't have to do this, but I just did it because I wanted to be sure it would work. At some point, someone is going to have to route your LCD. This means physically laying out the traces that will connect all of the common and segment lines. Again, it's a lot like laying out a single layer PCB. All the lines have to connect, they can't cross each other, and there are no vias to help you. I really don't know what tools the LCD fab houses use for this. All I know is I used Eagle and did some auto router hacks to get a sense for it. I laid out a schematic with some parts that resembled the pad layout for my electrodes, some single pin parts for icons, and some 8-pin parts for the segmented digits. And I connected them up to the COM lines I needed to lay out. I basically arranged them roughly the way I wanted them to look on the LCD, and I had the auto router take a stab at it. Same thing for the segment lines. I just assigned them all and let the auto router do that job for me. Okay, so here's a question. Are these best practices? Is this the right way to do this? And the answer is, I don't know, really. If anyone in the audience has any insights as to what tools they use to route these kinds of things in the real world, I'd love to hear it. Please reach out. For now, just know that it's what I did and it worked for me and got me to a working display. Okay, so wrapping up. I hope this talk offered some insight into making use of LCD technology. We talked about how these little pieces of glass are great for low power projects. We talked about how they work and how to recognize the different kinds of waveforms that drive them. We also talked about how you can drive them with peripherals designed for this exact purpose. We talked about how these displays are out there in gadgets all around you. And we talked about how you can unlock their secrets. Finally, we also went over the basics of how to design your own LCD for a device if you can't find anything in the salvage bin that fits your exact needs. So that wraps it up for me. These slides are available on the Remoticon slide share, so you can download them and check out some of my notes. And I'll be on Discord if you have any questions, but you can also ask any questions on Twitter at Jose Castillo. Thank you.
Hi, Colin.
Hey, can you hear me okay?
We can hear you and we can see you, so that is great. You can go ahead and mute and turn off your video for the next minute. And when the countdown clock gets to 0, Tom will introduce you. Thank you. Okay, Tom and Colin, if you'd like to bring back your cameras and audio, that would be great.
My camera will go on. It says host has stopped camera. There we go. All right. All right. So there's a higher than average chance that anyone spending their Saturday watching the Hackaday Remoticon has also spent an evening hunched over a PCB looking for an unmarked serial port. You may have even desoldered the occasional flash chip and tried to dump its firmware. But what if cracking into a device requires more advanced techniques, say side channel power analysis? Our next guest is here to show that with open source tools and low cost equipment, you too can add these exotic techniques to your bag of tricks. Please join me in welcoming Colin O'Flynn to Remoticon.
All right, thanks so much, Tom. So yeah, I hope you enjoyed this. This talk will be a little, I don't want to say that different, but what I sort of miss about the real conferences is the chance to, talk to people and to sit down next to someone doing some interesting work and say, oh, can you show me how this works? Can I just watch you do it? So one of the things about this talk is I'm going to have a number of demos. All the demos are going to use code that's available, that's either already posted or I've posted recently. So it's really supposed to be about not just, hey, here's a cool thing you can do, but here's what it looks like when you do it. And you can go and do that yourself, right away. So I have a few slides. I did just upload them. So I guess I'll do that. So we start with the slides. And then, as I say, I'm going to be switching back and forth between some hardware demos and some other stuff. I'll try to keep an eye on the Discord. So if you have questions, feel free to drop them in as well. I have quite a few different sort of demos I can cover, but if people want to see specific stuff, I'll try to move it that way. It's only half an hour though. So obviously I'm going to be a little constrained on what I can do. So really quickly about me. So I sort of got into power analysis and fault injection and really hardware hacking in general from previous work doing embedded systems design. I started this Chip Whisperer project, which was started as a fully open source tool. Now we have this kind of weird combination of some stuff open source, some stuff proprietary. Which is in itself, I think, an interesting topic for a different talk, right, is how you build sort of a business out of this, because there's lots of people you talk to that, do this as just a little side project. But what I'm curious about is how can we help everyone, help more people actually do this as a full-time job, right? And in our case, we have about 6 people that are, running full-time out of some of the various tools we built. So it's definitely not impossible. Right? You don't have to go work at a big company and just do this in your spare time. You can actually do this as something full-time, and you can get other people along with you. So it's a lot of fun that way. I was involved in academia for a while too. So I'm still a little bit looped in with that, but I was much more involved. Now I'm back kind of doing similar open ideas, sharing of information. I really like that part of academia. So I'm continuing to do that, but focusing more on my Chip Whisperer projects and related projects. Another cool thing recently is there's a book that came out. So this hardware hacking handbook. Hopefully you can see this on the screen here. So colleague Jasper Van Woonberg and I have co-wrote this book that was a year. So another topic is the effort in writing a book. We calculated, I forget exactly, it's like 0.1 pages a day or something. That's the rate you have to write a book at. And you too can write a book. So there's a lot of, a lot that goes into this beyond just writing it. So the other thing I'll note is there's a bunch of demos for this talk. Oh, there we go. So I tried to keep a bunch of hardware around. There's a physical book. So that's pretty cool, I think. There's some demos for the talk, so it's linked below. There's some tools I'm going to show you that I kind of just created for this talk. As I said, it's supposed to be a little more ad hoc. This isn't really great finished things. For all of them, I'm going to show you. Some of them are going to be Chip Whisperer tools. Some of them are going to be other stuff. This slide isn't online, so we're going to be giving away a few Chip Whisperer little mini kits. So these Chip Whisperer Nanos are these little boards with some other kits and some copies of the book. So if you want, feel free to fill that out. And it's just kind of like a random selection for now. So we couldn't figure out a better way for yet. So this one's just a random selection. All right, so on to the real talk itself. What are we going to focus on our talk? I'm going to show you a few examples of fault injection and power analysis. So if you're kind of curious about, how does this work in general? So I'm going to start with what, maybe you think is a little theoretical, but I'm going to try to link that into some real life stuff after. But at first, I want to show you that, in fact, you can run some pretty cool examples, I think anyway, about how these types of attacks work. I'm then actually going to target a different type of device. So I'm going to start with sort of like Cortex-M, STM type devices. I'm going to actually jump to a Raspberry Pi 3. So this is something that's new for this talk. I've done a tiny bit on this, but I've sort of gotten several different things working. The other thing I'm going to show that I promised on Twitter is that I actually made a really cheap EMFI tool. So as I said, this talk is not, it's supposed to be like, hey, here's something cool I did. So quite literally, I went to Walmart like yesterday to get the equipment to build this really quality device. But it's going to be a cool thing, right? So I'm going to show you that I'm not just trying to use only ChipWhisperer. There's a lot of different ways to do this. The information we post is available. So there's a lot of open source information out there. And you can use all sorts of different, tools you have on hand to learn a bit. That's the real point, is that it's not so much you have to use tool A, even if I'm using tool A. The actual fundamental information is applicable against a wide range of tools and examples. So I think that's the pretty cool part, is sort of what I want to get at. All right, so examples for power analysis, demos, right? That's all that's in the slides. So if you downloaded the slides, that's what you get. So let's take a look. Let's stop my share for a second. Where did Zoom go? Let's take a look at this guy. So I've got a bunch of different hardware here. We're not going to look at the Raspberry Pi yet. So I'm going to start with one of the original sort of things. So this is back from the Hackaday Prize timeline, and then there was a Kickstarter and stuff, was this ChipWhisperer Lite. So what this guy does is, this was an open source hardware project that basically has a target that we can run different code examples on, and then the board that does the actual power analysis and fault injection type stuff. So you kind of have everything on one board is the idea. And the whole point of this is that for understanding the attack, so this is really good for learning, you don't have any fidgeting around. So if you've tried to follow along, sometimes you find that, you need a specific device, and if you can't find the device, especially right now with supply chain, right, then you've got to figure out, okay, I've got to port this code to something else. So one of the ideas was to make this pretty straightforward for understanding. And you might notice there's like kind of this obvious location that you can split the boards apart, right, which was the original design for this. So you can split the boards apart afterwards and use it to target other things that aren't the built-in target. So, but that's what the hardware is looking like right now. And so that's just going to sit there blinking. So I'm going to go back to the screen share. And what we'll see is, out of the way. Okay, so I'm going to be using these examples that are part of ChipWhisperer. So you'll notice, you might not be able to see this, but in the URL, it's a local, so there's a server running for something called Jupyter Notebooks. But if you're just kind of curious, hey, what all could I do with this stuff? There's this ChipWhisperer Jupyter repository. So this is all available publicly. This has various different examples that are running. So the idea of this is you can actually kind of self-teach yourself quite a bit of this. So you have some sort of courses, stuff like that. So I'm just going to pull in a few of these to show you how these sort of attacks work. And in particular, I'm going to show you just a power analysis, kind of how you'd use that to understand if a password prompt had some sort of vulnerability that let us bypass it with power analysis. So this is what I'm going to do is I'm going to take a password check. I'm going to compile it for an ARM microcontroller, right? So this is actually compiling the source code. So I'm compiling the code that runs on this, right? This is not an offensive attack I'm doing right here. I have full control over it. And in this case, I actually know what the password is. So what I'm going to do first is I'm going to look at what's the difference in power consumption on a very fine grained level when I send like a known and an unknown password. And this is really interesting because if we see a difference between, or sort of a valid and invalid, and because I know what the password is, it can tell us something interesting might be possible. And we see some differences here. We don't know if it's random or not yet. But it's clear like there is some amount of difference that we can see in a power trace, right? So that's kind of the basic idea of power analysis, is there's some difference. And then all of the effort in power analysis is actually exploiting it. And so in this case, what we would do, in real life, you wouldn't know if the password was correct or incorrect. So what I will do here is I'm going to send every possible character to the device, right? I'm only covering lowercase. So to make the demo faster, it doesn't, you should do this for all 256 binary values, or at least lowercase and uppercase. In this case, I just try all lowercase, right? And so the sort of things power analysis tells you is, hey, for most of the time, and what you have along the bottom axis is samples or time, and along the y-axis is power trace, right? So most of the time, I'm just looking at Discord. Sorry, I had a dead link. Sorry about that. People figured out maybe. Anyway, so most of the time, the device takes one sequence, except for one other time, it takes the sequence in gray, right? So the system is taking a different path, it looks like, and it looks like it takes longer. So you can kind of see this offset. And why you might have that, right, is that if it's comparing the password, once the first character is correct, it continues comparing, at a longer time. So this is a classic sort of attack. You might see it written as like a mem compare type attack or anything like that. But this is the idea that using power analysis, we can actually figure out. So this would be a totally black box, right? I wouldn't need to know the correct password in this case, because I've just sent every possible first byte value, and then I figure out if we can go further than that. So that's the type of thing you can do with power analysis. You can go way further than that. So you can recover encryption keys with power analysis, but the fundamental idea is that we can use it to understand if the device has some difference when it's processing different values of the secret being a password, a key, or anything else. We can even, so in this case, we have what's called like a kind of instruction flow dependent on the data being processed. We can even leak information about the data itself. So different values of data going across a data bus internally do give you leakage. So all of those demos, you can do. I'm not going to go through all of them because I want to also show you a bunch more stuff too. Okay. So one little example for power analysis. As a note too, so we're talking about software. If you're, a lot of people are doing FPGAs these days. You can do similar attacks on FPGA devices. So let me stop this share to show you some hardware. Right, so what I'm going to do now is I'm going to use that same capture hardware. And so this is a board I've designed, but you can also modify other boards to do it. So this has an RTX A35 FPGA on it. And we can actually see power traces from hard, like FPGA blocks, right? So in this case, what I could do is I can load a AES core onto that FPGA. So it's a design, for an AES core that's loaded on the FPGA. So this is another example where, again, this is open source, so you can download the design that's being loaded onto the FPGA, right? You can download that. You can change the FPGA design. I don't know if you want to see me, probably not. So let's put that back because you'll see some different lights blinking. So maybe it's a little more interesting. And ignore the Raspberry Pi. That's for okay. I just want to short stuff out. Okay, so what's going to happen is that I'm basically going to, and I'm not going to run the full attack here. I'm just, again, trying to show you that sort of look over the shoulder that, hey, you can actually see this type of stuff. So I'm going to record a few power traces here, right? And so all this is available to you. And what you see is you can actually see, this is the device operating with different data. And depending on the data, there's going to be minor variations in the power usage. So if we were to operate with the same data, we should see much more consistent power traces than with different data. And so if you're kind of curious about, that sort of design where you're actually designing cores, again, the material is available for you to look at. So that's pretty cool. All right, fault injection. So fault injection is probably one of the more interesting areas. And as I said, these are all pretty quick because I want to show you that it's, the information's there. You can run these yourself. So fault injection, you might know it, mostly from like bypassing JTAG and stuff like that. Fundamentally, though, the idea is that we have the ability to change instruction flow, right, or change the data being loaded or something like that in a device. And so at a very basic level, what I'm going to do, and I'm going to run this on a few different examples here, is I'm going to run a simple loop where we have this double loop process. So we have two loops running. And why are we going to start with this? Really straightforward. It's very obvious when we get invalid results with this. So this is the interesting thing, is it makes it very easy to see invalid results. So I'm first going to show you how we would typically use this in like our little chip whisperer system. So I'm going to plug back in this board. So I'm going to run on the STM device, and it's not going to do a whole lot. So I'm going to pull that up. And what we can actually see, and so all it does is it programs in that little loop test, right? So it's doesn't seem very exciting. Oh, whoops. Doesn't like it when I switch the demos so much. Okay, should have checked things were working. And so again, the chip whisperer stuff gives you these toolings that what it's doing is it's running these loops, and it's simply checking if the output of the loops become invalid at some point. And so if we see these invalid loops, we'll kind of see it figure out that at some point in time, there's like an invalid output here. So we have these X's and pluses. So X means the device reset, plus means there was some kind of interesting output, AKA a fault coming out of this. Now, you might say like, okay, that's kind of boring. Why do we care about a loop being wrong? If we have the output of the loop wrong, that actually means we have some ability to control the instruction flow, which means we can do stuff. So there's another example. I won't run right here, but you can do things like bypass. If there's a password check, you can do things like bypass. So there's a really cool example running on the against the LPC device. So Chris Gerlinski had first shown this, basically a bypass on one of the fuse bits of it. So there's a ton of stuff you can do once you have that working. But what I want to jump into is kind of what I think the real interesting stuff is looking at a more complex device. So I have a Raspberry Pi Model 3, and ignore the fact the heat spreader's off for now. That was for another test. And what we're going to do is, let's just pull the slides up. Okay, is we're actually going to do some fault injection right on the Raspberry Pi Model 3. And this is cool because it's like a more complex device, right? So you might say, hey, you're just showing little microcontrollers. Let's kick it up a notch. So I had an old demo on this using Voltage FI, which if I have time, I can recreate. But what I want to show you real quickly is new demos with EMFI, and also very rapidly that you can build an EMFI tool for pretty cheap. So I built a more complex tool. And one of the interesting things I wanted to show is that you can, again, do this with stuff you might have kicking around. So let's, before we jump into the final part, the cheap EMFI tooling, let's just pull up the Raspberry Pi demo. And so there's the Raspberry Pi. Here's my Raspberry Pi. Need my mouse. Here's my Raspberry Pi. So hopefully you can see this. And we will open a terminal. Okay. And so what I have is that same, this same test that was running on, and let's see if I can get picture in picture. I'll just show you the board. So the same test that was running, where it's just doing this double loop, we can actually now try to insert faults. And there's different ways of inserting the fault. So this was a tool that I built that's kind of more complex for doing EMFI. And the idea is that you could hopefully insert EMFI by sort of, it inserts a large pulse into the device. And if we're really lucky, we'll see some sort of errors coming out here. If we're unlucky, you don't see any such errors, or the device resets. So you might see, errors, you might see the device reset. It's kind of a bit of, to be honest, a little bit lucky. So I'm just going to do this without showing you the output. We'll see if we get a fault. And so we'll see a fault if the count of these is invalid, or if the device crashes. Okay, so there you go. So that's an invalid count there. Means that we're seeing the actual fault being inserted into the device. Where this gets sort of interesting is that you can do a lot with that, right? So even on the Raspberry Pi, we can do something called a fault attack against RSA. So when RSA signs a device, there's a kind of a well-known attack that, and so I linked in the repo the code to do all of this. But what you have is this well-known attack against RSA. As it's signing, if there's a fault in RSA, it's actually going to allow us to recover the private key. So what this is doing is this is running a whole bunch of signing operations. It printed a secret value of the known P and known Q. And if we're lucky, so again, we could crash the device fully. All I'm doing here is I'm just holding this over the core like that, right? So I just kind of hit it somewhere and, oh crap, okay, that just worked. Got really lucky. So the output was faulty, and it's then able to recover the P and Q values. So it doesn't actually know. So this is printed purely, and you can go see the code in the repo. This is printed purely for your own interest, and you can confirm they match. So that's pretty cool, right? And that just kind of worked really well. All right, so, but that was using this larger, more expensive EMFI tool I built. What if you want to do this ultra cheap? So in the last kind of 5 minutes I've got here, what I'm going to do is let's go back to this and let's look at real cheap EMFI tooling. Because this is always the question. So all of this is going to use a flash device. So back in the day of, right, disposable cameras, lots of people probably saw these guys. These were like these disposable camera flash units. And so these were, you used to be able to get lots of them for free if you just asked. Now it's a little trickier. So I bought a pack of 2 of these for $20. So they're still pretty cheap, right? The downside of these devices, so if you kind of look at the online schematic, they have a lot of charge that goes everywhere. So they're not very good to try to use on their own. Oops, there you go. Because basically, relative to this battery, even like the switches and stuff will be at like a high voltage. So it's not something you really want to use on its own. So what I've done instead is I have sort of this tool that's slightly less dangerous, and it's slightly less dangerous because what it does is it exposes, or it uses battery power, so the high voltage never has a way to close a path around it. So it's basically a way to make a slightly less terrible, let's show this again, slightly less terrible EMFI tool. So this is basically what I've done. And there's more photos of this in the repo, basically. So you take your camera flash. I changed the capacitor out. So by default, they've got this big chunky electrolytic capacitor. I changed this out so that it's now using a ceramic capacitor. This reduces the amount of charge that has stored, so it's a tiny bit safer, but it also gives us higher current through the coil. So that's one part of it. We have a coil we built, so I have some details of that on the repo, and we basically just connect it through to a little, in this case, an IGBT. You can use a MOSFET or whatever too. Yeah, so that's kind of the base design of it. And then in this case, I have a pulse button. As I mentioned, you can use an opto isolator or anything else. So does it work? So it's a bit questionable, and I'll show you. Let's just try it. I found that it's not quite as reliable, but basically you have two buttons. One button charges it. So if I hold down one button, you'll see a flashing, there's a little neon light. It may or may not show through. And then you kind of click the other button. So I'm going to show you, I'm going to jump right to the, this guy here. So this is just going to do repeated RSA signing operations, right? But if it works, it's pretty cool. And it has worked a few times for me. We'll see if the demo gods. And so this is what it looks like, FYI, right? I'm just going to do that and click it. And so you can see it signing. And if you get real lucky, I'm not going to spend too long trying. Yeah, if you get real lucky, what you get is there's an error during the signing. Okay, you got segmentation fault, which can also happen, but that's good because that means, I mean, you're getting errors. Right, so it just wasn't in the right time, because remember, this is a whole OS running, so a legal instruction, right? When we insert a fault, nobody guarantees that the fault is where we want it. So normally we'd have some timing and stuff like that as well. Okay, oh, there we go. So that was my cheap EMFI tool, right? Inserting a fault into the Raspberry Pi. And so you can give it a shot yourself. It's easier to test first with the little loop test, but you can see that actually works. So that's pretty cool, right? Like that was a little real self-built EMFI that was able to work, you know, in some degree pretty well. Other demos, so low cost, to kind of wrap it up, right? Low cost demos that might be interesting. You can do something similar with a barbecue lighter. So it's a little trickier. You want to make sure you have some capped on tape and stuff protecting you. But it's actually possible to do this type of attack in another way as well. So this bottom photo was pulled from the hardware hacking handbook. The other real cool one to watch out for, so Thomas Roth, who you've probably seen through a bunch of stuff, the AirTags most recently, but some other really nice attacks, and does some really nice documentation for them. Had this working on a Raspberry Pi Pico, where it's basically glitching from one core to the other. So again, something that you can try if you want to learn about this yourself, with very minimal investment in it. With that, I think I'm basically at the end. So if you're interested in seeing updates on this, feel free to ping me on Twitter, of course, on the Discord here. I'll be around. And I post occasional blog posts, as well as a lot of the work goes into the Chip Whisperer itself. So there's all sorts of tutorials that get pushed in to that. So if you're curious about, you know, ECDSA, ECC, AES, DES, we have examples on all of those. We have fault attacks on RSA, fault attacks on AES. It's all available, right? The documentation, the examples are all fully open. A lot of the firmware, hardware, all that stuff's open as well. So there's quite a bit of resources available for you to get started in the area. I know this was really quick. As I said, I wanted to kind of show some examples and hopefully that accomplished that feel for you and you enjoy the rest of the talk.
Well, thanks a lot. I'm sure there will be plenty of questions in the Discord about your little MacGyver gadget there. We'll be taking a short break and then we'll be back with Rob Weinstein.
Welcome, Christina and Rob. If you can hear me, if you would go ahead and please unmute and turn your cameras on so that we can check out your video and audio.
Hello.
Okay.
Christina, I can see you clearly.
Okay. Excuse
And
me.
we can hear you as well. So you can go ahead and turn your mic and video off until the timer reaches 0.
So some reason I am getting an error on my webcam. I know it works, but it won't let me choose it.
Okay.
Well, that's
Let's
disappointing.
see. Do you want to try changing your webcam settings? We have about 3.5 minutes, so you might have time to try to problem solve if you want to check your Zoom video
Maybe
selection.
you know what, I may have another, maybe I have to turn off Teams or something. Let me try that real quick.
Yes, if it's in use by a different application, that could be the issue.
Okay, let's try that. Okay, so now. Geez, it's just not working. Oh man, this is not happening. Let's see what else could be using it. Maybe. No. Well, let me unplug it and plug it back in. Okay. video. Come on, video. This is unbelievable. What a disaster.
It's okay, Rob. We can still hear your audio. I've gone ahead and paused the countdown. So we'll give you 1 or 2 more minutes to try to problem solve. If you want to try any last things, and then I will put 2 minutes back on the countdown and we will get started in just a couple of minutes.
Okay, thank you.
Okay, welcome back to Remoticon, everyone. Our next presenter's video is currently not working, but we will work with him afterward to re-record and make that available with video to everyone, as we may only have audio for this next segment, but hopefully he'll be able to share some visual as we go. So Christina, if you want to go ahead and hop in and introduce our next speaker, that would be great.
Okay, thank you, Angie. Hello, everyone. My name is Christina Panos. I'm one of Hackaday's staff writers. Our next speaker, Rob Weinstein, is an electrical engineer who has spent 30 years designing with FPGAs, primarily in the wireless communications field. But like most of us, he was doing fun stuff on the side the entire time. Most recently, Rob reverse engineered a 45-year-old patent into a working replica of the HP35, just in time for the calculator's 50th birthday. Please welcome Rob Weinstein.
Rob, if you can hear us, can you please unmute yourself?
Okay, is that better?
Yes, we can hear you now.
Okay, can you see my slide?
No, we cannot.
This is unbelievable. How about now? No slide?
No.
Okay, where?
Have you clicked share screen on Zoom?
Probably not.
It's the
Share
green
screen.
button
There
at the
we
bottom.
go.
There you go. And then
All
select the window that you would like us to see.
Okay, let's do that one. share. Okay, do you see something that looks like a calculator?
We currently see a blue video.
Oh, geez. Okay. Boy, this is. Come on.
So if you go back to the share screen button at the bottom, you should be able to toggle to a different window to share to select.
Well, for some reason, it is not letting me. I click meeting controls and I get nothing. Oh, there we go. Okay, it's on the other screen. Okay. Boy, I'm sure sorry about this. Stop share. Okay, so now share screen. Okay, let's go with this one. Share. Now do you see something?
We sure do. Looks good. Thank you.
Okay, sorry about that. Okay, hello, I'm Rob Weinstein. In commemoration of the upcoming 50-year anniversary of the introduction of the HP35 calculator, I'm presenting Patently Obvious, reverse engineering a 45-year-old patent into a fully functional replica of the HP35 scientific calculator. This presentation is about how I built a fully functional replica of the HP35 calculator based on US patent 4,001,569. I used a small FPGA board for each of the 7 ICs, each designed faithfully to what's described in 569. Together, the 7 ICs comprise a 56-bit serial CPU and display subsystem that runs a calculator program stored in 3 of the ICs. There's no microprocessor emulation here. How I got here. In college, my trusty HP41C calculator got me through my engineering degree. In my career, I migrated to PC-based tools, and my HP41C eventually bit the dust with a corroded flex circuit. Years later, about 2007, I bought HP's newly introduced HP35S, a modern update of their first pocket calculator, the HP35. About that time, I discovered a whole world of classic HP calculator enthusiasts on the web. First, I thought they were lunatics, but I couldn't look away. Eventually, I quietly became one of them. Here's a short list of the websites that sent me on my way. Eric Smith. My first introduction to reverse engineering of classic HP calculators was the work of Eric Smith, namely his Chasm Sim and Nonpareil software simulators that run the original HP calculator ROM code. In the README files included in those simulators, I read, quote, the design of the processor and the instruction set are described in detail in United States patents 3,863,060 and 4,001,569. My curiosity was piqued, so I downloaded copies of those patents and was amazed at the level of detail. I learned that 060 describes the HP80, while 569 describes the HP45. These 2 patents contain much of the same information with differences only for the specific functionality of their respective calculators. Jacques Laporte. I had come across Jacques Laporte's website some years earlier, but I hadn't yet been bitten by the classic HP calculator bug. I've since learned that Monsieur Laporte has passed away and his website fell into disrepair. Lucky for me, and for classic HP calculator aficionados everywhere, Eric Recklin, proprietor of hpcalc.org, had rebuilt and rehosted the site at the link shown here. Other than the 569 patent, this site is the single most comprehensive source of technical information about the HP35 calculator available anywhere. Peter Monta. Peter has physically opened the original HP35 ROMs and, through optical methods, extracted the raw bit array and converted it to a list of machine code instructions. Tony Nixon. Tony has a trove of classic HP calculator information, as well as an emulator and various reproduction hardware for sale. His notes on classic calculator operation is a fantastic resource for the classic HPs in general and their display operation in particular. David Hicks, HP Museum. great resource for all HP calculators. I've been lurking on their forum for years. HP35 background. The HP 9100A came first. Its basic architecture, designed by Tom Osborne, machine coding by Dave Cochran. The final product was the result of significant contributions by many at HP. With the 9100A family finally shipping, Bill Hewlett asked Dave Cochran, "When can I have a 9100 that fits in my shirt pocket?" Dave Cochran was the project leader for the HP35. In addition to leading the project, he used his experience in the 9100A to develop the algorithms and write the microcode for the HP35. The HP35 was introduced in early 1972 for $395. That's $2,500 today. Their first 100,000 unit production run sold out in 2 months. The amazing 569 patent. As I mentioned above, I was surprised at what I found in the 569 patent. I was expecting a quaint collection of special purpose logic circuits that directly implement the arithmetic functions. To my surprise, I found that the calculator is a portable, battery-operated microcomputer running a scientific calculator program. I was amazed at the level of detail in the patent. There are block diagrams, logic diagrams, schematic diagrams, timing diagrams, flowcharts, instruction tables, operating instructions, and even a complete assembly language code listing. 569 is a gold mine. I'll just point out that 569 describes the HP45 calculator. There is no patent specific to the HP35. However, since the HP35 is a subset of the 45, 569 has everything I need to reverse engineer the HP35 hardware. Here's a sampling of the images. Here's a sampling of the 37 figures in 569. Here's a sampling of the 77 or so tables in 569. And here's a sampling of the 28 pages of the HP45's machine code listings in 569. In addition to plentiful figures, tables, and code listings, the text describes every aspect of the calculator's operation. The basic machine architecture, the 5-wire serial bus that connects the main ICs, a precise detailed description of each of the IC's operation, the energy-saving inductive drive technique for the LED display, the complete instruction set, a switch mode power supply, and even the keyboard, including details of its over center or fall away feel. And I'm just going to point out here, in the middle, we have the main block diagram, figure 2 of the patent. And then I've put different color boxes around each of the submodules in that block diagram. And you'll see that the patent has additional, more detailed figures for each of those blocks. And behind each of those is many paragraphs of text describing exactly how it works. How does the HP35 work? Those of you who are students of computer history might recognize this as the block diagram of the computer that von Neumann described in section 2 of his famous 1945 paper, First Draft of a Report on the EDVAC. This is now called the von Neumann architecture. Let's compare this to figure 2 in the patent. At the top is von Neumann's architecture, and at the bottom is figure 2 from the 569 patent. As you can see, there's a one-to-one correspondence between the von Neumann architecture and what's described in 569. It's clear the HP35 is a computer. After reading the patent, I fell in love with the HP35. Why? Because of how much they did with the resources they had. For example, there were no microprocessors available when the HP35 was designed. Intel had launched their 4004 just 3 months before the HP35 was introduced. HP had to design their own processor. Static memory was too large and power hungry. They had to use dynamic shift register memory instead, implemented in PMOS. And since all the registers were shift registers, this forced the designers to employ serial processing throughout. It could be carried in your shirt pocket. Because it was small and portable, it had to be battery operated, which forced the designers to employ low power design techniques. An LED display that's powered by batteries. They had to coax power hungry LEDs to only SIP power. A tiny ROM, only 768 10-bit words. This required handcrafted machine language coding. The algorithms for the transcendental functions were based on the work of Henry Briggs from the year 1624. Talk about your prior art. And floating point arithmetic, 10-digit accuracy in most cases. Of all the amazing techniques revealed in the 569 patent, I only have time to talk about 2 of them. I've chosen the inductive drive technique for the LED display and the serial processing architecture used throughout the calculator. So much was left on the cutting room floor, so to speak. Let's get started. The patent says the inductive drive technique employed for the LED display is inherently efficient because there are no dissipative components. What they mean is no dropping resistors are used. Dropping resistors work by throwing away power, and they can't afford that in a battery-operated pre-CMOS design. The basic scheme they developed is closing an anode switch puts energy in its inductor. Opening that anode switch discharges that energy through an LED segment. By carefully choosing the inductor value and the switch timing, the designers delivered exactly the right amount of current to light the LEDs without wasting any power. In the next slide, I'm going to demonstrate how HP engineers carefully orchestrated the timing of their inductive drive technique to multiplex a 7-segment plus decimal point LED display across the calculator's 15 digits. This animation demonstrates the inductive drive technique in combination with multiplexing the first 2 digits of the display. First, a note about the conventions I'm using. Blue lines represent current flow that builds up the inductor's magnetic field. Red lines represent current flow resulting from a collapse in the inductor's magnetic field. The thickness of the colored line represents the magnitude of the current flow, a thin line for a small current, a fat line for a large current. In this demonstration, digits 1 and 2 will display 8-8, all segments lit. We start with digit 1. Its cathode switch is closed. It remains closed until all segments in that digit are processed. And I'm going to show that right here. These are the cathode switches. With the digit selected, the topmost anode switch is closed. And here's the anode switches, the topmost. Current starts flowing through the inductor, and its magnetic field starts to build, a blue line. Now we repeat the following sequence for each segment in the selected digit. 1, close the next anode switch. Current starts flowing through its inductor, a thin blue line, and its magnetic field starts building. 2, open the previous anode switch. Its inductor's magnetic field begins to collapse, and the induced current, a fat red line, discharges through the LED segment and through the selected cathode switch. When the last anode switch for digit 1 has been opened and its current allowed to decay, move the cathode selector from digit 1 to digit 2. Repeat this sequence for digit 2. As you can see, while the inductor's magnetic field for the currently lit segment is collapsing, a red line, the next segment's inductor is building up, a blue line. So if you didn't quite follow all of that, then just pay attention to this one thing. Notice how the blue lines step their way down through the rows and the red lines trail just behind. This diagram is not in the patent, but I wanted to show how the inductive drive technique and display multiplexing are orchestrated within the calculator's 56 clock machine cycle. It reveals the synchronicity, or a kind of harmony between every element of the design. What's not shown is that the keyboard scanning and the serial processor's fetch and execute cycles all map into this timing exactly. Not a single clock cycle is wasted. This is what makes the HP35 so amazing. Now let's look at the serial processing architecture. Don't try to absorb the details of this diagram. It's only meant to demonstrate that the register bits within the main processor components are constantly shifting to the right and recirculating. I want to point out that this recirculation doesn't happen as a result of some operation, but rather it's happening continuously. As long as power is applied, all bits shift by one position on each and every clock cycle. This means that if you want to perform an operation on a particular bit or bits, you must precisely time when those bits become available at the rightmost end of the shift register. Then steer those bits through the desired functional block, such as the add or subtractor. Paper design and documentation. This photo shows some of the binders full of design documentation I created for the project. This spreadsheet lists most of the 45 separate diagrams I made during the course of this project. Many of these diagrams have multiple pages, as shown in the 5th column. In total, I drew 338 individual pages. You'll be relieved to know that I'm not going to show all 338 pages of diagrams in this presentation, but I want to show a few of the more interesting diagrams. For example, display animation, barber pole timing, algorithmic state machines. This animation shows how the recirculating A and B registers in the arithmetic and register circuit are encoded on the A and E lines. And I'm going to point out a couple items. At the top, we have the 56-bit registers of the calculator, the A and B registers. These registers will contain what gets displayed. Then down here, we have the display buffer. This holds every group of 4 bits gets held in this register. Then we have the BCD to 7-segment decoder that converts those into the 7 segments. And then we have a set of multiplexers that time multiplexes those 7 segments out through these 5 lines. What you'll see on the right are some timing diagrams. These come out of figure 12 in the patent, and I've put in kind of an animation overlay to show what's happening at every instant. And finally, at the bottom, we have the LED display. And what you'll notice is the display starts drawing from the rightmost display and works its way to the left. And you'll notice, if you're careful, that the segments don't all light up at once. They light up in a staggered fashion. That's to preserve the batteries by reducing simultaneous switching. Barber pole timing diagram. In order to work out the detailed timing of the recirculating registers within the control and timing circuit, I developed a technique I call the barber pole timing diagram for reasons that will become obvious. The contents of the 28-bit register are shown as horizontal row of boxes. At the next clock cycle, I show the 28 boxes shifted 1 position to the right, and the rightmost box returned to the leftmost position. Each subsequent clock cycle shows the register contents circulated to the right by 1 bit. Since I used different colors for the 3 fields, a barber pole pattern emerges. So I'm going to point out these fields. At the left, we have the ROM address in yellow. In the middle, we have the status bits in green. And at the right, we have the return address, sort of a pink color. In modern parlance, the ROM address is what we now call the program counter. The status bits are what we now call the condition codes register. And the return address is the stack. And that's not the stack pointer, that's the entire stack. You only get 1 subroutine call. Okay, now that I've got the shift register content shown over time, I refer to the patent, which tells me that the ROM address will be incremented during bit times B47 through B54. Since the bits can only be used when they reach the rightmost end of the shift register, then these bits must reach the rightmost position during those times, right here in blue. The patent goes on to say that the incremented address is transmitted during bit times B19 through B26. Again, bits can only be used when they reach the rightmost end of the shift register, so the incremented address bits must reach the rightmost position at those times. With this information, I can fill in the remaining bit times and the main bus signals. With the bit times and main bus signals all sketched in, the state of the microprogrammed controller can be added. The purpose of this exercise was to determine the state sequences for a particular instruction type. To determine all the state sequences, I drew 18 separate barber pole timing diagrams, just like this, except each had about twice as much information as what's depicted here. A microprogrammed controller. The patent discloses much of the calculator's logic in ample detail. However, it's silent on the internal details of one very important block, item 46, the microprogrammed controller. Since a microprogrammed controller is an optimized implementation of a finite state machine, I decided to start by designing the state machine using the technique that Tom Osborne pioneered during his time at HP, called algorithmic state machine, or ASM. This is very likely the same approach that the designers of this calculator employed. Osborne's ASM techniques were collected, organized, and expanded by HP's Christopher Clare in the book shown here. At this stage, my barber pole timing diagrams showed how the bits had to move between the shift registers and the various resources to perform each instruction type. A few slides ago, I showed that I added the state signal to the barber pole timing diagrams. A state shows what needs to be done during each bit time to perform the steps required for each instruction type. Once I had the states worked out for every instruction type, I sketched the state transition diagrams using the ASM techniques in Clare's book. The ASM diagrams fully document the operation of the microprogrammed controller. FPGA coding and simulation. To demonstrate how I performed FPGA coding and simulation from the patent, I'll focus on a small but important submodule, the serial adder subtractor, item 84, as shown here in figure 10 within the arithmetic and register circuit. This submodule is essentially the calculator's entire ALU, or just AU, because there are no logic instructions in the HP35's processor. A little digression. The HP35 employs a 56-bit word size, but the data that's represented in that word are always decimal numbers. So data such as characters or binary values are not allowed. A common technique for working with decimal numbers in a binary computer is to represent each digit using binary coded decimal, or BCD for short. BCD uses 4-digit to represent any BCD uses 4 bits to represent any digit 0 to 9. There's room for 14 BCD values in the HP35's 56-bit word size, so 14-digit decimal arithmetic is theoretically possible. On the right side of this slide is the block diagram of the arithmetic and register circuit. On the left side is what the patent has to say about the serial adder subtractor. Using this information, we'll try to write the Verilog code for the serial adder subtractor circuit. Since I knew a serial adder can be done with a simple full adder circuit, this should be easy. The patent even explains how, so I'll start sketching it up. I start with a full adder and a flip-flop to hold the previous bits carry, some multiplexers to choose what goes into the adder. Wait, what's this about BCD correction? The patent says, it is not known if a correction is needed until the first 3 bits of the sum have been generated. So I'll add a 3-bit shifter on the main sum. If the sum exceeds 9, so I need to compare the sum to 9, a correction, addition of 6 to a BCD sum must be made. So I need another adder with its carry flip-flop and a shifter to supply the 6. The next sentence is the key. It tells me I was doing it all wrong. So I have to undo my first attempt and do what it says. This is accomplished by 4-bit holding register 86, A60 through A57, and inserting the corrected sum into a portion, 88, A56 through A53 of register A if a carry is generated. Well, now I have 2 carries here, and I still haven't addressed subtraction. The patent only says a similar correction for subtraction is necessary, not much to go on. I'm starting to realize this is more complex than it seems. At this point, I thought it might be a good idea to see what I could find on the web. A lot of searching led me to a paper by Glenn Langdon of IBM, published in the IEEE Transactions on Computers in 1969. This paper was a goldmine of information on BCD subtraction. I learned that typical BCD subtraction circuits using binary adders employ a method called subtrahend complementation and add-10 decimal correction. Langdon presents an alternative called minuend complementation. I'll sketch 2 versions. This one employs subtraction by traditional subtrahend complementation and add-10 correction. The next one employs subtraction using Langdon's minuend complementation. Of the 2 options, I've chosen the second version that employs Langdon's subtraction by minuend complementation because it always adds 6 regardless of add or subtract, and the carry output logic is simpler. Using the second logic diagram, I'll code it in Verilog. This image shows the module ports. Up to now, it's all been paper design. But finally, this is where I go from just writing about an HP35 to actually making one. With this level of detail in the diagram, it's just a simple matter of coding up each related idea into a block of Verilog. Let's go through it real quick. So this few gates right here I'm showing are the carry into the first adder, and that's coded in this block of Verilog. The main full adder and its exclusive OR for doing the minuend complementation is coded in this small block of Verilog. I've got a multiplexer that sequentially shifts in the value of 6, and that's coded in this block of Verilog. The second adder and its AND gate on the carry in is coded in this block. The 2 sum outputs and their exclusive ORs are coded in this block. The carry output logic coded in this block, and the 2 individual carry flip-flops are coded in this block. Once the module is coded in Verilog, I need to test it. Since the serial adder subtractor is the fundamental element where all HP35 results are calculated, it needs to be rock solid. I chose to write a self-checking test bench in which I could run thousands or even millions of test values through my module. I drew the detailed test bench and coded it in Verilog by inspection. I'll point out a few highlights. Well, the big yellow one in the middle is the UUT, unit under test, or the serial adder subtractor. On the left over here, we have the test vector generator. It generates a random set of operands for it to operate on the adder subtractor, and it also generates the expected values. Of course, we have to have shift registers because it's a serial adder, and these values get shifted in, and their sums get shifted out into a serial shifter on the output. A couple of registers are used here to match the latency through all those shift registers. And then finally, we get the actual results and the expected results. We compare them, and if they match, we increment a counter. If they don't match, we increment the bad counter. And then we take all of these results and write them to a file. Again, once I've sketched up the detailed diagram of the test bench this time, it's a simple matter of coding up each idea into a chunk of Verilog. And you can see there, that's the entire test bench. Test bench results file. The self-checking test bench compares the expected and actual results and dumps the results to a text file shown here. I print a tally of good and bad comparisons, num good and num bad. For the 1,000 iterations of random values that I ran in this test, I got num good equal 1,000 and num bad equals 0. And I've done the same thing with millions of vectors. I used the techniques described above, first to diagram, then to code up and simulate each module in the patent. It took me roughly 18 months or about 750 hours to complete the RTL design. Constructing a working replica. Once I had the FPGA code written and simulated, I drew up a schematic. I used a commercially available FPGA board for each of the 7 ICs in the design. I worked out a preliminary component placement, then a final component placement, then I assembled a replica. Let's go over the details of the front side. I have a 1.6 megahertz crystal oscillator. I have these two modules make up the anode driver, the circuit for detecting a low battery voltage. These 3 modules make up the cathode driver, and of course, the 7-segment display. To the right are the actual parts I used. You can review those later. Now a detailed view of the lower part of the front side. Let's step through the circled blocks. Here's the arithmetic and register circuit. Here's the read-only memory circuits, the control and timing circuit, the power on reset circuit using, yes, a 555. And these 5 brass wires represent the interconnecting buses and lines. That's the entire bus for the CPU, 5 wires. And again, I list the parts I used here. Of course, I also sketched up the backside, added the wiring and power supply. Then I hooked it all up. Again, let's go over some details. I've got a lithium-ion cell, 18650, an Adafruit load-sharing lithium-ion battery charge management controller, some Pololu step-up, step-down DC to DC converters, and again, some details about the design. The bottom half of the backside of the displays, the backside of the 5x8 matrix of switches with the matrix clearly visible, the back of the arithmetic and register, the back of the ROMs, the back of the timing and control circuit, and the back of the power on circuit. Now I'll show a short video that demonstrates a few example calculations from the 50-year-old operating manual. So future goals. I would like to do a printed circuit board version of this, and then ultimately I'd like to do a gate level version, something along the lines of the Monster 6502, which I'm sure many of you have seen. And finally, I've come to the end. My niece drew a little picture of me admiring my own work, and I've provided an email address, and I've got a GitLab project repository, although right now it's It's just a placeholder, but eventually I'll get all the files loaded up there. And that's the end of my presentation.
All right, Rob, thank you very much for a fascinating presentation. I think we all love those animations quite a bit.
Thanks.
Will you be around in Discord to answer questions?
I can, yeah, sure.
Okay, wonderful. We would love to see you there. We're going to take a short break and we'll be back at the top of the hour. So we hope to see you then. Our next speaker is going to be Debra Ansell.
We're going to do a little AV test so we're ready for the next session. Debra, if you want to unmute your mic and camera, we can do a test, but just be aware that everything's going out into the live stream.
All right. The bombing will begin in 10 minutes. I think that's the I think that's the standard audio test.
Ooh, people are going to be in for a treat when they get to see your video for the
Well,
first time. That looks great.
Oh, thanks. I feel like you should have a flashing lights warning actually across the screen before I start, but that's how I roll.
It's Hackaday. I think people know that's a hazard that they might encounter.
Okay.
Everything looks and sounds good to me. Do you have any questions before we?
No, just the usual share screen, right? You should work, I assume.
Should be, and if there's an issue, we'll be happy to work through it. But for now, if you just want to mute and turn your camera off, we'll be back with an intro from Christina in 11-ish minutes.
All right, everyone, welcome back to Hackaday Remoticon. Our next speaker, Debra Ansell, has spent the last decade making things blink. You might remember her exquisite leather and LED handbag from a few years ago. Nowadays, she is creating modular PCBs that form dynamically reconfigurable electronic systems for PCB-based displays and wearables. In other words, she's still making things blink, but in cooler ways. Earlier this year, we covered Debra's interlocking triangle light panel sculpture that uses a clever electromechanical interconnection system in the form of spring contacts. Today, she will speak all about the building blocks of modular PCB design. Please welcome Debra Ansell.
Thank you. I hope everything sounds okay. Hi, I'm Debra Ansell, and thank you for attending my talk on modular systems of printed circuit boards, generally known as PCBs. As was said, I've been building electronics, mostly LEDs projects for over a decade, but I only learned to design PCBs a few years ago. Perhaps because it's a recent skill that I'm still building, I often find myself exploring non-standard ways to apply it. And a brief digression that's not in my notes, I have been tremendously enjoying the wonderful talks at Remoticon thus far, and was a bit anxious that I think my talk has a little bit lower information density than the previous ones, but I hope that after absorbing so much information, if you're watching this live, that you'll enjoy listening a bit more to the process and looking at some bright blinky LEDs a little bit. So let's go to share screen if I can get this going. Okay, this should be okay. Let me know if it's not, but I think I am now sharing screen. All right, so in a project, PCBs are usually used for their electrical function, but they can make good mechanical building blocks as well. When circuit boards are a construction material, their shape and the ways in which they connect determine the form and function of the final project. This talk will show several different kinds of modular circuit board designs created by me as well as other makers. I frequently post new builds online under the screen name Geek Mom Projects, and my motto is LEDs improve everything. My projects obviously reflect that philosophy. As these pictures show, a lot of my LED projects are wearables. I first learned to design PCBs because I wanted to create my own LED wearables product line called Bright Wearables. And in that process, I designed and manufactured an LED accessory board for the Microbit microcontroller, which attaches with snaps to the interior of specially designed bags and backpacks. That's the idea that got me started with PCBs, but I keep finding new ways to use them in my projects. So the next few slides show modular PCB assemblies from a few other makers. There are no established rules or best practice techniques for creating modular PCB assemblies. The concept can be applied in a number of ways. The two projects shown here are kits consisting of PCB panels where the PCBs in the panel have different shapes and functions. The cat lamp kit at left, the PCBs in the panel are organically shaped with plated slots that solder together directly. Some of the PCB elements form the lamp's electronic circuit, but others only provide structure or decoration. The HackMod Wear Kit was created by Mary Etta West and Angela Sheehan, who both have wonderful, amazing individual maker projects online. They designed this kit for SuperCon 2018, and the PCB elements are designed to be separated and assembled into wearables. The elements have different shapes and components like LEDs, sensors, and processors, and you can create arrangements with different looks and functions by using different subsets of this kit. On this next slide, the projects are a different kind of modular PCB build. They are designed and assembled from many identical PCB-based elements. These designs work by assembling simple PCBs into larger, interesting geometric shapes that come together and feel much greater than the sum of their PCB building blocks. On the left, Daniel Hinch's icosahedron build uses two different shapes of PCBs. The red pentagons have a neopixel in their center, and are the vertices of an icosahedron, while the longer boards form the edges. The addressable LED signal travels along the soldered edges through a carefully mapped path that reaches each LED exactly once. The lamp on the right, by Twitter maker Eric Bozeman, who goes as Brain Smoke online, connects irregularly shaped PCBs into a near sphere that has circular holes, which are pretty impressive because they're made from cutouts in the side. The design is amazing. So, and seeing how cool these aluminum PCBs look in this build has convinced me that I'm going to have to try out aluminum PCBs sometime. But note that in both these builds, the final form is fixed. It's predetermined by the shapes of the individual boards, which are directly soldered together. So my inspiration to make a modular circuit board system came from seeing nanoleaf light tiles. These are, like I said, light tiles which attach to a wall in different configurations and display colorful changing light patterns. Many manufacturers have copied this product, and many makers have been inspired to create their own versions. If you Google DIY nanoleaf tiles, you'll find many different creative ways to build similar displays. So I'm innately drawn to changeable art, especially if it has LEDs, but I found it hard to justify buying myself a set of tiles because I already have so many LED strips and strings at home. I set about trying to make my own version instead. It turns out that most of my modular builds, which you'll see in this, some of which you'll see in this presentation, have a lot of common elements with the nanoleaf tiles, which makes sense because they're intended as art. And the traits here are qualities I usually try to incorporate in my modular designs. So first off, I usually use identical base circuit boards in my project because it's simpler to design and usually more flexible to rearrange the elements. The circuits themselves are simple, again, because it's easier. Complexity comes from the way in which the circuit boards are assembled or programmed. The PCBs are self-connecting because I prefer to minimize the number of different parts in a build, and the builds just tend to look cleaner that way. I like easily reconfigurable projects because your tastes change, and I think it's fun to be able to rearrange your art to match. They're scalable because I want to be able to use the same base elements for a small project or a big project. I like that flexibility. And of course, LEDs. My goal is always blinky bright, colorful, and attractive builds because that's my aesthetic. Now, of course, making custom PCB projects requires that you design your own PCBs, which I initially found intimidating. Now that I have more experience, I thought I'd share my secrets to low-stress PCB projects. And I swear this slide is not just an excuse to work a Dr. Strangelove joke into my talk, but that was a bonus. I really hope to encourage more novice makers to learn circuit board design because it's such a powerful tool to have in your maker toolbox. This one single element can provide your build with electronics, aesthetics, and mechanical support. So it's easy to make mistakes when designing and ordering circuit boards. And I used to worry about wasting time and money. Circuit board design software has a steep learning curve, and the process of ordering boards is confusing. So here's my secret to overcoming the fear of making mistakes with PCBs. First, start by reading tutorials on how to design them. I found the Spark Fun tutorials on using EagleCAD very helpful when I got started. Second, review your designs carefully, have a friend check them, send them off, place an order. Don't sweat the details because it's the third step here that's critical. Inevitably, you'll make mistakes, but you'll also find those mistakes are rarely a big deal. You can order small prototype PCB runs cheaply. If you find some mistakes, use it as a learning opportunity, revise the design, and redo the order. It's not that expensive to experiment. I felt better about making so many mistakes when an experienced circuit board maker told me that sometimes even his orders came back only functional as coasters. So most PCBs you see in builds have been redesigned and tested through several iterations. They're rarely perfect the first time. So ultimately, the trick to low stress PCB projects is simply not to stress and just try out your ideas to see what happens. I have learned more from my mistakes than my successes, and I have a bonus collection of really weird shaped coasters now. So This slide shows how some of my previous projects contributed to the design of the PCB-based light tiles. I had built a series of what I called inner glow projects that embed an LED strip sideways into laser cut acrylic sheet. The LEDs shine directly into the plane of the acrylic. The 3 projects on the left use that technique. These projects, which place the LEDs inside the acrylic, gave me the idea of how to design the light tiles. The base layer of a tile is a PCB with side-emitting LEDs covered with a layer of laser-cut translucent acrylic. The LEDs shine directly into the acrylic, which diffuses their light. Now, the pictures on the right show views of the final tile assemblies, which I made using both triangular and hexagonal tiles. You can see how the inner glow effect worked out. Each tile polygon has 1 LED at each corner, pointed towards the tile's center. The hexagon LEDs diffused more uniformly than the triangles, probably because they contain twice as many LEDs. And the non-uniformity of the triangle tiles is actually more pronounced on camera than it is in real life. And even so, it creates a pretty effect. And it is also actually dependent on the brightness at which you run the LEDs. So it still looks nice, even if it's not perfect diffusion. The circuitry in the light tiles is extremely simple. This schematic shows all the components in a triangle tile: 3 addressable LEDs, 3 decoupling capacitors, and 3 connectors. I included this slide to show you that you don't need to be an electronics whiz to make interesting PCBs. Super simple circuits can produce great results. So I made a few different prototypes of the tile PCBs, so their appearance may differ in some pictures, but this version here in the upper left have a solder mask story. These light tiles work best with a white surface on the top to reflect any downward directed light back into the acrylic. When I ordered them, white solder mask was more expensive than black, but happily it turns out that white silkscreen is free. So these tiles actually have black solder mask with a top surface almost completely covered in white silkscreen. I did my own assembly using the fancy skillet you see in the bottom row. Surface mount soldering with an inexpensive electric skillet is a neat trick I learned from another SparkFun tutorial. It's a great way for makers who are new to the process to assemble their own surface mount PCBs. I've since upgraded to a reflow hot plate, but absolutely recommend the skillet method if you're just getting started. I called out this SK6812 4020 side illuminating LED because I have a love-hate relationship with them. Side illumination is a really, really great way to let you view the LED's colors without it getting overwhelmed by the blinding glare. But these LEDs have teeny tiny pads and are a big challenge to solder. So consider yourself warned if you decide to use them. Once I had working PCBs, I laser cut translucent acrylic for the top layer with cutouts at the position of the LEDs and capacitors so it could sit flush against the top layer of the circuit board. And nylon screws hold the layers together and blend in nicely visually with the white acrylic. And this is how I made the individual light tiles. It was a bigger challenge to connect them together, but before I get into that, I'm going to digress for just a moment. So since I'm advocating using PCBs as a construction material, I feel like I should be able to tell you whether it's cost effective. So I did some simple math. PCBs and acrylic are the 2 main components of the light tiles and cover the same surface area. So it's reasonable to compare their cost per tile. The calculations here use retail prices for the acrylic I used and PCBs minus shipping and tax. So at left, we see that cutting 33 acrylic tiles efficiently laid out on a 12 by 24 inch sheet of translucent acrylic cost about 54 cents per tile for materials only. And on the right, it turns out that ordering 50 lead-free circuit boards with black solder mask from JLC PCB averaged 84 cents a tile, which is a little over 50% more per tile for the PCBs than the acrylic. But the PCB cost will drop at higher quantities And if I didn't own a laser cutter, I'd have to pay to have the acrylic laser cut, while the PCBs arrive fully cut and drilled with whatever customizable silkscreen artwork I want at no extra cost. So I think that if we're going to examine the cost effectiveness hypothesis of PCBs as a construction material, I would call it confirmed. So now back to the tile construction. As I said before, connecting the tiles was the hardest part, though that's not unique to this project. I find that in most of my builds, the biggest challenge is figuring out how to connect and hold everything together. I wanted the light tile assemblies to be reconfigurable so they couldn't be soldered together directly. I needed to find a connector. And the first step was to figure out what I needed. I identified these characteristics: mechanical strength, because unlike the real nanoleaf tiles, which used a wall for support, I wanted my build to be freestanding. Electrically, the LED data signals needed to travel through a long chain of connections in a potentially very large assembly. And for safety reasons, I didn't want exposed power contacts. Aesthetics were really important because this is functional art. I wanted unobtrusive, low-profile connectors, and they also had to be surface mount because any through-hole parts would stop the acrylic sitting flush against the circuit board. Affordability is important because of the sheer quantities of connectors required. Each edge of each tile has a connector, and there are many tiles in a large assembly. And part availability is a bigger issue now than it was at the time, but even then, I didn't want parts that would be obscure or hard to get. So with these criteria established, I started to search and became intimately familiar with the board-to-board connector categories on Mouser and DigiKey. There were a lot of potential candidates to sift through, and you'll have to humor me for another brief digression, because when I was writing up this portion of the talk, it struck me that the connector search was actually starting to sound a lot like dating. So briefly, these are the similarities I noticed. With so many possible candidates, it really feels like it should be easier to find the right one. Second, when you're searching online, an effective filter is very helpful. And the biggest similarity to dating is that you start out with like certain ideals in your mind and take a good hard look at what's available and realize pretty soon that there are gonna be some compromises. So back to the connectors. I did consider a lot of candidates and none were perfect. You could potentially apply dating metaphors to this slide as well. The connectors shown here were actually among the sturdiest I could find, but none of them could support a vertical column of PCB light tiles by themselves, and most of them were expensive. The one actually that came closest to meeting all my criteria was surprisingly also the simplest and cheapest. Surface mount header pins were easily available, flexible enough to survive a bit of stress, but still not strong enough on their own. So in the end, I created my own connector by designing a second circuit board, you see here. The fiberglass cores of PCBs make them good structural reinforcements. On these connector PCBs, power and signal pass through small pressure connectors that have little spring-loaded prongs that can move up or down. I chose pressure connectors over header pins because they require fewer parts, since header pins work in header socket pairs, while the complement to a pressure connector can be a simple solder pad, which is basically free. So the pressure connectors were also lower profile and had a smaller footprint. To keep them from getting squished, there's a laser cut 1/16 inch layer of clear acrylic with cutouts on the connector side of the PCB. And in the assembly, what I really liked is that these custom connectors completely covered the contacts, so electronics were not exposed. And this video shows the tile assemblies running some simple animations. I want to point out that the stands for these structures are just wooden versions of the PCB light tiles that I laser cut with slots so they could be cross-braced perpendicularly. So these cross-braced bottom layer of wooden tiles are just attached to the bottom row of light tiles in the same method as the light tiles attached to each other. And they make a really nice, adaptable, actually pretty good looking base. So It worked really nicely, but it wasn't perfect. And as usual, the connections were the issue. The larger assemblies had some mechanical issues, mostly because of torque from the combined weight of the tiles. There was some sagging in the plane of the tiles, and also what was worse was that the bending perpendicular to the plane of the tiles could sometimes be enough to lift the pressure connectors completely off the contacts. So I think that tighter tolerances and smaller gaps between tiles would help future builds. To shore up the existing build, I laser cut some small clear acrylic shims to just slide between the tiles, and added extra laser cut acrylic connectors for extra support. Tightening the screws helped with electrical connections. And in future designs, I think it would be a good idea to place the electrical contact points as near to the screws in the connectors as possible, and maybe even add some more screws to really hold things together tightly. Electrically, this is probably a novice mistake, but I really hadn't thought enough about power distribution. If you route power in a single line, the voltage drops significantly by the end of the tile sequence, making LEDs dimmer. So I added extra power taps to my assemblies, but in future revisions, it's best addressed by redesigning the connectors. And without too much detail, the PCB connectors I made only attached the input of one tile to the output of another, so they only work along the signal path. It would be better if they could distribute power between any adjacent tile edges, which would be most easily accomplished by making all the pinouts on the edges symmetric at the connection points, like this example down here in yellow. And that would also help with safety because it's harder, probably not impossible, but harder to hook symmetric connections up along. But despite, or probably because of the challenges of this build, I've really enjoyed having these displays in my house. So that was the first, but not the last of my modular PCB builds. And just to show that they can't all be winners, this was my attempt at a wearable version of light tiles. I scaled the project way down, way down. And at this side, the only detachable connectors which fit were these 1.27 millimeter pitch through hole header pins, which turned out to be really difficult to solder. I was able to construct a working assembly, but it was ugly. And in the end, I just scavenged the tiles to use in a wired cuff bracelet project instead. So I still had PCB light tiles left over and wanted to use them in a three-dimensional build. So I joined 8 of the tiles into an octahedron. I 3D printed some screw brackets to hold the sides together at the right angles. The wiring, a Gemma M0 controller, and a LiPo battery all fit inside the octahedron, and I didn't need to make the wiring neat because it's not visible from the exterior. Adjacent tiles in each build half were soldered together so they couldn't be reconfigured, but the screw brackets did make them quite sturdy. The 2 octahedron halves snap together with neodymium magnets, and the final build has a nice futuristic look when illuminated, and I would really like to create more 3D PCB light projects in the future. Now, this next project has a bit of a twist, pun intended. I couldn't stay away from the idea of creating modular PCB wearables, so I thought I'd scale up a little and make a cuff bracelet, a flexible cuff bracelet. Wearable builds are a special challenge because they need to conform to our irregular bendy bodies, and I wanted a bendy connector. So I'm not really sure where I got the idea to use dollhouse hinges because I certainly did not find them on Mouser or DigiKey, but they're appealing because they're cheap, small, and have screw holes for reinforcement. They're brass, which can be soldered. So I designed a footprint for them, then fabricated small PCBs to use as links in a cuff bracelet. Adjacent links connect with 3 hinges for power, signal, and ground. Each link has 3 layers. The PCBs sit between a laser cut acrylic bezel on top and the hinges on the bottom layer. Wires go through the matching holes in all 3 layers for mechanical reinforcement. So in this build, the side emitting LEDs fit inside cutouts in the bezel, which I filled with hot glue for light diffusion. I covered the exposed back of the hinges with black tape to insulate it and make it more comfortable to wear. And as you can see here, the aesthetics were terrific. I love the way this looks. The hinges are very low profile, making the bracelet quite thin. The assembly flexes smoothly and easily. Unfortunately, There were electrical issues. You don't see it in this video, but repeatedly bending the hinges causes glitches in the LED patterns. And after playing around a bit, I believe that it's the friction between the hinges and the pins holding them together, plus having large open metal surfaces for signal creates interference on the signal line. I did not continue with this project because I couldn't figure out a good way to overcome safety issues of having a wearable running current through large regions of exposed metal. Also, under stress, it turns out that the pins inside the hinges can slip out and cause shorts, which is obviously bad and even more obviously bad inside a wearable. So while they were fun to play with, I've stopped using them and strongly recommend that you don't use dollhouse hinges in your electrical projects, just in case you were tempted. But I still did want to find a way to make a bendable PCB assembly and tried a different approach. A Twitter recommendation pointed me to these rotating connectors. They only cost about 60 cents a piece, have 4 circuits, and even better, they're actually designed for use with PCBs. So these connectors give a much safer and more reliable electrical connection. Unfortunately, I didn't find them that attractive in a wearable, and they aren't very strong mechanically. They separate too easily under stress. So a running theme in this talk is that it's very difficult to use the same PCB connector for both electrical connections and mechanical support. So next up, more motion. This is my articulated PCB projects, also known as bendy boards. It's another moving PCB assembly, but it uses a different technique. With the hinged builds, the boards move perpendicular to one another, but this design rotates the boards within the same plane. The full assembly is a chain of pivoting links. Each removable link consists of 2 parallel PCBs with holes in the center that pivot around a common axis provided by a plastic push rivet. The links use the same pressure connectors as the light tiles did, except in this case, the pressure connectors make contact with a ring-shaped pad on the surface of a rotating PCB. Each ring in the pad, each ring on the PCB makes contacts with 2 pressure connectors on the other board in the link, and this redundancy helps maintain the connection in case there's a bit of wobble. Just like with the light tiles, there is a buffer layer of acrylic to keep the pressure connectors from getting crushed. The other connector in this design is a small mezzanine connector, which joins links together detachably. 2 M2 screws on either side provide additional mechanical reinforcement to keep the links together. It was a fiddly, iterative design process to get all the tolerances right, but the result is actually remarkably sturdy and doesn't glitch, even with a lot of handling. I'm really fond of this project, though I haven't found a good purpose for it other than a fidget toy. But I'm still thinking about ways I could use this design as a practical technique for flexing other circuit board designs. So fortunately, I have a little time left because we're at the last project of my talk. And this one is fun because I'm still right in the middle of it. I have not yet explored its full potential. I haven't even shown it publicly before because I couldn't. I only just recently finished assembling a few of the PCBs, and here they are. The left side shows the unpopulated boards, and the ones on the right show that when populated, they contain 2 addressable LEDs, decoupling capacitors, header pins, male and female, and very short header pins, male and female, and a double pole, double throw slide switch, and the function will become clearer shortly. This was the first prototype of this design, and there was a significant mistake, but after a lot of unnecessary, I won't explain it, but basically in the end, the silk screen is on the wrong side, so which is fine as long as you're really, really careful about knowing which is voltage and ground. So by themselves, these boards aren't very exciting, but when you put them together, things start to get fun. These LED boards are another light tile project, but instead of the PCB forming the face of the tile, these little circuit boards form the sides instead. So this is how it works. The castellated edges of these PCBs can be soldered together at any angle, which means you can make a light tile in any shape with as many sides as you want, as long as all sides have the same length. So the same base PCBs can create a variety of shaped tiles. To hold the configuration in place, the tile faces are just laser cut translucent acrylic with slots to hold the tabs at the sides of the PCBs. The acrylic diffuses the LED light and also doubles as a jig for soldering the castellated edges, which is a nice efficiency. Using translucent acrylic on both sides of the tile gives you a two-sided display, or placing mirrored acrylic on one side just gives you a brighter glow on the other. I left holes in the acrylic to use standoffs to help hold each tile together, and the slide switches on each side determine whether that side is an input or output, and it's designed to work no matter how many sides are in the shape. So in any tile, one side gets set as input and the rest is outputs. And I'm running short on time. I'm going to count on the fact that I have, I think, a minute or two of overage because I'm close. So I've only had time to make a few working triangle and square tiles, but I have plans for different shapes, and there are a lot of possibilities. As long as you place slots in the acrylic, which correspond to the PCB tabs, it's pretty easy to assemble. So, all right, I know I'm getting closer. So once you've built the blocks, all you have to do is slide the header bins together, and voila, you have a rearrangeable modular assembly of modular PCB assemblies. And I have some additional ideas to try with these blocks because the holes in the PCBs, you see right here, allow adjacent tiles to be reinforced with standoffs, or you could put magnets in there and use pogo pins to make snappable magnetic light tiles, which I think would be fun. So all of this is going to be future experimentation because magnets like LEDs make everything better. And just to wrap it up, because I know I'm really getting close to going over, I hope that you see that there's a lot to be done with modular tile assemblies and that PCBs make a terrific construction material for projects. They also make good DIY connectors when you can't find an existing connector you like. Remember never to use dollhouse hinges as connectors, and I hope that somebody watching this talk will be inspired to go out and try using PCBs in a way they haven't thought of before. Thank you very much.
Wow, thank you, Deborah. That was a very illuminating talk. That was awesome.
Thank you.
I wanted to use dollhouse hinges, but I guess I won't.
I would recommend against it, yes.
Okay. I definitely want to try some modular PCB building though.
Good. Then I've done my job. Thank you.
Will you be around to answer questions on Discord?
I am going to drop into the Discord right now. Thank you.
Awesome. Thank you very much.
Okay. Thanks.
Have a great night.
You too.
Thank you. All right, everybody, we're going to take a short break. Please stick around for our next speaker, Vaibhav Chhabra.
All right, we're going to do an AV test to make sure everything's working. Vaibhav, if you want to unmute and turn your camera on, we can test those out. Just know that it's going to go out on the live stream so people can hear you.
Yep.
Looks great. I can see a nice clear picture. And do you want to say a few more words just so we know your mic works?
Sure. Hi, this is Vaibhav, joining in from India.
That sounds very clear to me. I think we're good to go.
Should I get rid of this virtual background? 1 second, sorry. I'll just blur it. Yeah.
Sure.
Or maybe blur. Yeah, there we go.
All right, looks great. Did you have any questions before we get started?
No, I think I'm okay.
Great. If you want to turn your camera and mic off, we'll be back in about 2 minutes and 45 seconds, and Christina will introduce you.
Sounds good. Thank you so much, Mike.
Thanks.
All right, everyone, welcome back to Hackaday Remoticon. Our next speaker is a mechanical engineer and carpenter. He's also the co-founder of Makers Asylum in India, along with Hackaday's own Anul Mahidariya. Once the pandemic began, he started the M19 initiative to manufacture face shields for frontline workers. Soon after, he met up with other makers to multiply efforts, and together, they managed to make 1 million face shields in 49 days. What's it like to innovate, produce, and distribute products at scale during a pandemic? Please welcome Vaibhav Chhabra to tell us all about it.
Thank you so much, Christina. Thank you, Mike, for having me. Really excited to be here. Been a fan of Hackaday for many, many years now, and so excited to be with all these amazing makers and hackers over here. It's really early morning in India. It's about 6 a.m. So I'm gonna try and be as exciting as possible and share my screen so I can show you some photographs from what really happened over here. But before I talk about the M19 initiative, let me tell you about Makers Asylum real quick, just to put some context. So we run a makerspace in India called Makers Asylum. We're based in beach town Goa now. We moved here in the pandemic just about last year. That's our space right there in the center. It's this beautiful 100-year-old Portuguese house that we hacked into a makerspace. I think it was always meant to be a makerspace, but they just didn't know when they were building it 100 years back. So it works perfectly. It's just the beautiful flow of this Portuguese house that we have our makerspace in. There is everything from a woodworking workshop inside to a metalworking space to a 3D printing lab with a lot of 3D printers now, and electronics lab. And all of this started in Mumbai in 2013 when the ceiling of my old office fell down. At that time, I was working for a startup which is called iNetra. iNetra was a startup that was based at MIT Media Labs in Boston. I was there for a few years. And then we were using, and where I really got inspired was using Artisans Asylum in Boston and a bunch of other makerspaces to build this device and to prototype it. But when I came back to India, there were no hackerspaces or makerspaces, at least in 2013. So Makers Asylum started with just a DIY meetup to bring together people back in 2013 and to build some tables and furniture post the ceiling breaking down at iNetra's office. That day, about 6 people showed up and it was amazing. We built 3 tables and we celebrated over pizza, and it was super fun. It just felt like being back at Makerspace in Boston. So post that, we moved around 8 times over 8 years. I wouldn't say that we moved by choice. Most of the times we were kicked out of the space, but our space kept getting bigger. The first space that we started off was about a 250 square foot garage that you can see on the top left. And then as you progress, our space sort of started to grow as more and more people started coming to the space. Makers Asylum naturally over the years started getting known as a bit of an innovation hub, and a lot of people started coming to the space from all across India and other parts of the world to come share skills and learn. And that's when we started a bunch of programs. Now we primarily, that's what sustains us. We run 2 exciting programs. One is called Innovation School, the other one's called SDG School. SDG School focuses on the Sustainable Development Goals, and Innovation School focuses on profile building and sort of doing your own project and sort of design thinking and learning about different technologies like CAD, drone, IoT, etc. And then the pandemic happened. So we were doing all of this stuff, and then boom, the pandemic happened and everything had to shut down. So to be, and being a makerspace, it's pretty difficult not to run a physical space, right? And we were in Mumbai, and Mumbai happens to be super, super expensive, just like I would say comparable rents to Manhattan. And we had a huge space now, where we were paying rent and we had to shut it down because the entire country was going under lockdown. So all of us was super scared. But however, it was also a pandemic. And I mean, growing up, it felt like the time not to do something. So what we did next was super fun. We didn't go back home. Instead, we quarantined at Maker's Asylum because we thought it'll be much more fun to be at the makerspace and have access to our tools than to go back home and do nothing for the next 2 weeks. Because at that time, the lockdown was supposed to be for 2 weeks. However, the lockdown lasted for almost 3 months in India. So we said, let's just stay at Maker's Asylum and do something. So the first thing, what happened is we started reading the news, and just like everywhere in the world, India had a huge shortage of PPE equipment. And there were news coming in from every part of the country that there was so much shortage of beds, there's so much shortage of PPE, there was nothing really out there. So we started working on our first little prototype of face shields. So thanks to a lot of the open source communities, open source medical supplies, and a bunch of others, we were able to see very earlier on some designs that were coming up that were 3D printed. However, we went with a laser cut design because laser cutting is faster, better, and cheaper according to us. And because with a 3D printer, we could only make maybe one face shield in about 30 to 40 minutes. However, with the laser cutter, we could make one face shield in under 30 seconds. So that was great. And we have laser cutters at the asylum. And also one thing, what we realized in a very, very short amount of time is that India by itself has a huge network of laser cutters all across India, because laser cutting is also used in marketing and in so many other things, because there is an industry around laser cutters which is not really existing around 3D printers. So laser cutting turned out to be a very interesting idea. So we immediately started to make some prototypes of face shields. We started to show them to doctors at night. We went to their homes because we were too scared to go to the hospital. So we went to the doctors' homes and showed them our prototypes. They gave us feedback and we got somewhere, which was pretty exciting. That worked. So post that, we started an initiative that we said that, all right, we're going to make 10,000 face shields. Mind you, this is the time when the entire streets were empty. There was not a single soul out on the streets in India, and that's very, very rare. And all the shops were closed. There were no places to find materials. We were just four guys inside a lab planning to make 10,000 face shields. So it was pretty scary. We said it, but we didn't know how we were going to do it. But what happened next was really, really beautiful. Over 20 other people moved into Maker's Asylum with us and started making face shields quietly. They also started living there, and quietly we woke up, made face shields all day long, ate food, slept, and repeat. It was magical. The entire makerspace in Mumbai turned into this gigantic factory where all that was happening was we were making face shields day in and day out. We went through 21 design iterations to get to the final design that we finally made, which was injection molded, but we didn't get to injection molded during the pandemic. During the pandemic, we were laser cutting them. So we started with a paper prototype in the middle. We tried different materials. The first material that we tried was wood, and wood turns out to be a really, really bad material for hospital environments, as you can imagine, because one, it's porous. That's one thing that we learned, because porous substances are very, very bad because obviously they keep a lot of bacteria inside them. So that was a big no. The next one was acrylic, which happens to be brittle and keeps breaking. So that was also a no-no and super heavy and expensive. Then came the aha moment when Anul, who happens to be also a Hackaday writer, suggested this very, very interesting material called sunboard. Sunboard or foam board happens to be super exciting because it's super common. It's available in any single stationery store all across India and the world rather. And it happens to be waterproof. So we took the material, we took the facial prototype to a hospital, to the deans of the hospital and the ethical committees, and they loved it. They said that this is perfect. Can you please make more? And we got to work. And that's when all of this happened, where people started getting together and started making them. What happened next was super interesting. There were ambulances, there were police personnel, there were vans. They were all parked outside of Maker's Asylum. There was literally a line of police people and ambulances and doctors standing outside of Maker's Asylum waiting to pick up facials, because literally we were finishing making them and we were handing it to them. They were putting it inside ambulances and off they went to the hospital. It was quite intense because the supply chain was completely choked up. All the there were no aircrafts running, there were no taxis running, there was no public transport running, there was nothing. So at this time, moving stuff from one place to another was very, very tricky. So, and it was really surreal for doctors and police personnel to be waiting outside the makerspace. We were too scared to bring them in. So we requested them to stay outside while we quickly finished as much of the making as possible and sent it over to the hospitals. So what we did next was that we open sourced our design, which were open source since the beginning while we were making them. But what we also did was we made assembly videos and other videos to sort of easily explain people how to make these wherever they were, how to create an assembly line inside your lab, how to keep your lab safe during COVID. We made a bunch of videos for other labs to start easily joining in and making with us. What happened next was crazy. 42 other cities, towns, and villages joined the force. So they all started making with us. Some of these were makerspaces, some of these were new makerspaces that got formed at this time. Some of these were universities, some of these were small businesses that wanted to contribute, and 42, all of them joined in. And from BBC News to Vogue magazine to all the newspapers in India started to talk about this M19 initiative, not really knowing what M19 meant for most of the time, which was really funny. But they kept talking about it, which is quite nice. And this really accelerated and allowed a lot of people to join. And that's how we went from 0 facials to 1 million facials in a matter of 49 days. To just put that into perspective, the yellow line over there is Maker's Asylum. We were doing our steady pace. We didn't go too crazy. We were making our steady 2,000-3,000 facials a day. But what happened after that was super cool, because a lot of other labs that started joining us came with different thought processes. They had different technologies with them. Some of them had injection molders. They had different kind of labs because some of them were manufacturers. So as you can see, some of them were much faster than us and were able to make many, many more facials than Maker's Asylum in a very short amount of time. And that was super cool because now we weren't only contributing and teaching, we were also learning from them. And it was a two-way street. We were all sharing designs, contributing and learning from each other to be able to create as fast as we can and supply it to the local ecosystems in our cities or towns or villages, wherever we were. So Richa, my partner, what she was doing was that she was mapping out India, and literally we had the north, south, east, west of India taken care of. And what she was doing was also super interesting. What she was doing was she was connecting the foundations to the hospitals, to the makerspaces, so that all of them started working together in their cities or towns and villages. She was actually connecting the dots for most of us in all the country. So literally, no matter which part of India gave a call to the M19 collective, they could find a local makerspace or a local manufacturer to supply them facials within their city or at least within the state, which was super interesting because in the time of a pandemic, that's how you need it to be, right? You don't want so much movement. You want something which is more local. And that's one of the reasons why it worked. The people who made this happen were from all different backgrounds. We weren't all makers before. There were chefs in the room. There were filmmakers in the room. There were doctors in the room. There were medical students in the room who couldn't be working at that time. There were people from literally all, there was a musician in the room. There were people from all different backgrounds who were contributing in whatever ways that we could, and they were able to join the collective and the maker movement to make that happen. The youngest member of the M19 collective was only 12 years old, and he made over 344 face shields with his family at home in Gujarat. Eventually, within the 49 days, we managed to make a strong enough team of about 300 volunteers all across India that was contributing to make this happen. It became so exciting that the University of Cambridge reached out to us and then wrote a case study about it, which was super cool because at least for a bunch of makers in India, getting written by Cambridge University was a big deal, at least for us. So it was super exciting that they reached out to us, and we started talking more. And actually, there's a very interesting thing that happened later, which I'll talk about. And then we also started talking much more with open source medical supplies, which I'll also get to. These makers from the M19 collective did not just make regular face shields, they also made a lot of different products during this time. So we made baby face shields, which we're still making because infants and babies can't wear masks. And baby face shields happen to be a very interesting product for them. We made superhero face shields inspired by some of the makers in Boston, and created a version for teenagers so that they can go out and still be protected. We made active respirators for doctors. This one we made with a collaboration with Ames Hospital in India. We made this rebreather mask with a little small active respirator that just pushed in air into your mask for senior citizens. While this was happening in India, and as you can know, all across the world, especially in the United States and other parts of the world, a lot of PPE was created by makers, almost 48.3 million units of PPE, and open source medical supplies did a beautiful job of putting these numbers together. And this just has something to say about the maker movement, right? We were all in silos. We didn't know that this was happening in the US. We didn't know that this was happening in Europe. They didn't know that this was happening in India. But when the pandemic hit, all the makers just knew it's time to get to work. And that's what happened. All the maker spaces across in different parts of the world got active. A lot of make groups formed and to contribute in whatever ways we could at that time. However, there was one big issue. There was an issue of quality check that varied a lot. Because if you think about it, in different maker spaces with different tools and with different resources, because not a lot of material was available in different parts of the country, there were different kinds of face shields being produced, which is not good because there was no quality checks and quality assurances to make sure that the same face shield, which is verified, is being produced everywhere. And that's around the time when the second wave in India hit. So we were trying to just be at the crux of this issue, which is about quality checks. And then the second wave hit, and there was this huge oxygen crisis in India. So we asked a bit of a question that why aren't we making oxygen concentrators in India? And that's when we got to work. We started, we anyways were researching some of these open source oxygen concentrator designs, which were really interesting. However, they weren't manufacturing ready. So we researched all of them and started to work on our own design. Anul led the team with us, and we did a lot of prototyping. We went through 4 designs in a matter of 8 weeks. And within a very quick way, we were able to produce something that we call the M1902, which is the image that you can see on the right. Once again, all of this under the second wave of the pandemic. All of these designs, by the way, are all on GitHub, and you can download them and try and make your own as well. And 30 other labs and small manufacturers in India were able to take these designs and be able to create their own versions. This time, however, we did something different. Now, remember I talked about Cambridge University. So they happen to have a very interesting department inside them called Center for Distributed Manufacturing. So we started really closely collaborating with them to work on QA/QC for makerspaces and for open hardware projects. And we're still doing a bunch of research with them. Professor Mukesh and Professor Jaideep joined the team, and they've been helping us to not just look at how we can get our own certification, which we've already pushed out, but also create a way in which other maker spaces, when they're trying to follow design which is certified or is a medical grade equipment, how can they copy it while still maintaining quality checks and quality standards? And how can the nodal lab then verify that to allow them to start producing with that name or whatever we decide on, so that everything still remains open source, everything still shares, but at the same time, especially for medical devices and other things, at least quality checks and quality assurances are kept in place. So we're still doing work on that. We don't have anything final over there, but it's going on, it's work in progress. The M1902 currently is, thanks to Schmidt Futures and Fab Foundation, has gone for functional certification in Mumbai and is being tested as we speak. While in Goa and other parts of India, all the makers and the maker spaces, all this consortium that we had put together, we've been repairing oxygen concentrators for free for a lot of the hospitals across India. And I think this is very interesting and very exciting, because while it's important and fun to make a oxygen concentrator, it is also very, very important to save the ones that are going into the landfill, because so many of the oxygen concentrators that came into India during that time, 2 years back, a few months back during the second wave, were not working because of multiple issues. Some of them broke while coming in. Some of them have issues because of humidity in India. Some of them had some electronic issue and basic issues. So we could fix them. And that's what we did. So we've been running repair camps in Mumbai, Goa, and Pune to sort of repair as many of these as we can as well. We're doing another one digitally in a few days, in the first week of December, for some of the countries outside of India to at least share what we know about how to repair them. And it will be again led by Anul, myself, and a few of others who've been repairing these over here in India, to share our insights as to what all you need and how you can do this very effectively to save some time. So we'll be doing like a little event. So if you guys are interested, you can just let me know and I can get you guys in or send you the details later. So the 300 volunteers that we had started with as part of the first wave grew to over 600 volunteers now. And instead of 42 labs, now we are 125 labs strong as part of the M19 collective. And we are continuing to build knowledge and share everything that we know for the open source community. This presentation is also in the open shared folder that's where all the slides are available, and the links are here to some of the things that I talked about and the GitHub repository, or you can just go to our website at makersasylum.com and get all the details over there. Thank you very much. That's all from my side. Happy to take any questions or spend some time with you guys.
All right, thank you. Oh, I did want to ask one question. What are your recommendations for people who want to organize their own groups like this?
Get started. I mean, that's what we did. So we just started making ourselves and started sharing. And people definitely, actually, you know what, let me answer this a little bit better. So a few things that really help. One, a strong purpose really helps. When you're trying to create something and trying to form a group, putting a purpose together. So for us, it was to help the frontline workers and to make face shields. So the purpose was helping the frontline workers. So that really helped. So everyone that sort of resonated with the thought was able to quickly join in and align themselves to the purpose. The second thing was a specific goal really helps. So we put down a goal that, okay, fine, we're going to make 100,000 face shields at the beginning. That's what we said, or 10,000 face shields, which is a very, very specific goal again. So they were able to sort of align to that and say, yes, I can contribute towards it and add my numbers or start working towards it. The other thing that really helped for us when we were forming such a group was initially we were able to share and handhold everything that we know for other new groups to easily get joined in or bring them into motion. After that, they did that with other makerspaces and other labs, so they were able to handhold other makerspaces. So initially, it's important to sort of teach them your dance steps, and then after that, more people can sort of copy and join. So I would say these three things really help in creating their own larger groups.
Oh, great. Well, that makes me want to know how you were able to share information between all these groups, what worked and what didn't.
WhatsApp worked, but a lot of different things. So one, we made videos. So videos were a nice way to communicate quickly as to how to use everything on GitHub and how to create an assembly line and how to keep lab safe. So those videos really helped a lot of the other labs, is what I know. They were able to take that very quickly and get working. The second thing that helped was that we were on, we created WhatsApp groups for each city. So while there was a main WhatsApp group, we were also creating WhatsApp groups for each city. So once the main WhatsApp group was sort of like this space where a lot of chatter was there. Then we had an engineering WhatsApp group where we were only talking about engineering stuff. And then we had a separate WhatsApp group for every city, town, village eventually, that we were able to put only the key people for that city to be there, because it's really important to have relevant conversation really quickly and not have too much chatter. So creating sort of the subgroups inside the larger group really helped to have some streamlined conversation. And then, of course, we had the power of Anul as well in our team, who is very, very organized when it comes to documenting on GitHub and documenting things. So he was able to sort of really help in organizing and documenting everything in a very streamlined manner so that everyone was able to grab what they needed very quickly.
Oh, great. Wonderful. Will you be around for more questions on Discord?
Yep, I'm on it now.
Okay, great. Thank you. Thank you for your great talk.
Thank you so much. It was great to be here.
All right, everyone, we're going to take another short break and we should be back. We'll be back in about 15 minutes. Be sure to stick around for our final keynote speaker, Jeremy Fielding. He's going to talk all about making hardware that moves. And we will follow that immediately with the Hackaday Prize ceremony, which we know you've been waiting for.
All right, we're going to do a little AV test while we're preparing for our next talk. Jeremy, if you want to unmute your microphone and camera, we can test them out, but just know that it will be going out live to the feed.
All right. So I should be clicking my GoPro on. Oh, there we go. It says active here. I can see it. All right.
Looking good. I get great picture and wonderful audio. It's almost as if you do a lot of audio video stuff. Do you have any questions?
I don't. Oh, I've got double audio. 1 second. Oh, never mind. I still have the live feed on.
Right.
Okay, that's gone now. I was getting nervous.
It's on a little bit of a delay.
Yeah, no problem. So I just forgot the window was back there. Okay, your audio sounds good. The double audio is gone, and I think we're okay on my side.
Great. All right. We have about 13 minutes left, and I hate to start it early because I don't want people to miss the beginning. But if you want to mute your microphone and video, we'll come back in about 13 minutes and I'll introduce you.
Okay, let me do a quick, cannot start screen sharing. Oh, because you're sharing.
Yeah.
Okay, never mind.
No, I'll stop the screen share. You can give it a try to test it out. That sounds
Okay.
good.
Yeah, I just wanted to turn it on, make sure the right one comes on, and okay. All right.
I see the robot arm.
Good. So I can get rid of this other stuff. Okay. I'm gonna stop sharing. And I'll go ahead and mute now.
All right, we'll see you back in a few minutes. Welcome back to the Hackaday Remoticon, everyone. Thank you for sticking around with us all day. I'm really excited to be introducing our final speaker of the event. There are certainly distinctions between people working in software, electronics, and mechanical engineering fields, but I think the productivity of your average engineer has risen so much that it's blurred these lines. And it means that every one of us needs to have cross-disciplinary skills. And if you're like me and you want to level up your mechanical engineering skills, we are in for a treat with our next keynote speaker. Jeremy Fielding has been chasing down an incredible range of skills useful to anyone building hardware. I first took note of his YouTube channel early last year when he was turning a relatively inexpensive yet beefy electric motor into a dynamometer to characterize other motors. But of late, I think the buzz on everyone's mind is this incredible industrial arm that he has built completely from scratch. Jeremy calls himself a contraption engineer, and I'm excited to hear more about how you do the wonderful things that you do. It is my pleasure to introduce Hackaday Remoticon keynote speaker, Jeremy Fielding.
Well, good evening, ladies and gentlemen. I am going to go ahead and turn on the screen sharing so that you can see the presentation. There we go. Okay, so as you can see, or as you know by this point, the topic is building hardware that moves. And I felt it was fitting probably to give you a little bit of a background about myself first. And that is, I design machines that do stuff. And I got a timer over here that I want to get going. So that could be anything from science experiments all the way up to full-on industrial equipment. Most of that stuff is not stuff I could share with you here, but there's one project that I have just to give you a sense of scale. And that's this project. I did this about 3 years ago, and that's me to give you a sense of how big this pit is. But essentially, the customer was trying to move all of this sand to another location, and they were driving it with trucks quite a long distance. So my chief engineer said, what if we pumped it into this tank, turned it into a slurry, and then sucked it out like a milkshake, pumping it down the line? Then we can dry it out when we get it to where we're going. So long story short, that's what all this is that you see in the background. Go back one, there we go. All of this equipment is designed to turn this dirt into a milkshake, pump it through this pumping line here, and then send it on down the line to where it needs to go. Saved a whole bunch of money and gas and all that good stuff. But the idea is that this is the kind of stuff that I do. I love making things. And when I'm not doing it at work, I'm also doing it at home. So that's where the YouTube channel comes in. So I put my home page up here, not because I wanted to show you my page, you could find that, but I want to show you this because all throughout this talk, I'm going to be talking about a lot of things that I've covered on my YouTube channel before. And on everybody's YouTube page, there is a place right here where you can search within a YouTube channel. So I'm going to strongly encourage that you go to here. And if you have any follow-up questions where you want more details about the things I'm going to be covering, you'll very likely be able to find a whole video on that very topic. So that's where you can go to my homepage, click on the little search icon, and then all of the videos will come up related to your search. All right. So this is the latest project from my YouTube channel. It's a full-size industrial robot arm that I built myself. And this is definitely by far the most difficult project I've ever done in my workshop. Maybe except the one that I just started, we'll see, but this one is pretty hard. So what makes this so challenging is not just the mechanical build, which is where I feel the strongest. It's all of the electrical design. I mean, this part of the project, in my opinion, was almost as complicated as the mechanical design. And so I invested a lot of time in working out the relay logic, working out all the servo controllers, their settings. A lot of energy and time went into a project like this. And I think it shows on my YouTube channel. So I frequently get this question, where do I start? And that's how I decided on the topic today, because people see these projects and they say, man, I want to do something like that, but they don't really know where to get started. And I'm hoping to close that gap just a little bit today by talking to you about how to build things yourself, your own ideas, your own designs. And I think if you're an engineer, you have a lot of tools at your disposal. I mean, we're talking about everything from grabbing your calculator, putting in formulas and doing the math to figure out if your structure is strong enough. I've got CAD tools available to me. I've got reference books. I can go over here and say, hey, you know, I can look through a list and find if the beam is going to be strong enough and things like that. But if you're making things at home, not only do you not have those tools, for the most part, you don't need them. And what I suggest is that you make prototypes. For me, one of my favorite prototypes is this. If you go to my YouTube channel, you'll see the very first video is this guy. When I started my YouTube channel, I had no engineering training at all. So I was literally just making it up as I go. And I didn't know anything about linkages, but you can see this guy has linkages on it. Again, a project that moves. What inspired this idea was I had a really tiny workshop and I wanted to figure out how do I squeeze more tools into that little tiny space. And I came up with this idea. I said, man, it would be great if I could have a workbench where I'd have my miter saw, my router on one side, and then you could flip it over inside the same space and have a little benchtop bandsaw on top. So I made this thing out of wood, and I even made one out of cardboard as well, which is what this clip is that you see on your screen. This is where I figured out how long the linkages need to be. I knew nothing about calculating linkages. I was just sticking pins in the cardboard and figuring it out. And so this is the first thing you need to do before you spend a lot of time just telling yourself, I don't know how to do this. Grab some cardboard, grab some pieces of wood, and just start making shapes and trying to figure it out. You'll be surprised how quickly you can get to a working prototype if you just grab some cheap materials and go for it. Over here is the only picture I could find of the actual build. This is right before I put the bandsaw on it. But I used that thing for about 3 years before I upgraded the bench and started doing some different stuff. So here is another project that was a similar idea. I built this a few months later. I wanted to build my kids a giant toy box, which is what you're looking at, but my kids were really small at the time. And I was concerned about that heavy wooden lid, you know, it's falling on little baby fingers. So I came up with this linkage idea, which again, linkages were already on the brain. Using this linkage allowed me to keep the lid very low. So when they pull on it, it comes down and it stays only a couple inches above the surface as it comes down and closes the toy box. Again, they played with this for a long time. They got a lot of good use out of this. And I did the same thing with this. I just had one 2-dimensional piece of cardboard. I drew out these linkages on the side and I worked it until I could close the lid in cardboard. And then I actually built the structure. Later on, I went back and added this little rod. Let me see if I can turn on my laser pointer. Here we go. Later on, I came back and added this as a support because there was a position where it would go too far and lock down at the bottom. So this was sort of an iteration of the design. I put that little lid on there and then that solved that problem. It never locked in the back and the kids could open and close it very easily. So let's talk about designing a little bit. First thing you want to do is sketch out your idea. I don't recommend that you go right out to your tools and start making stuff. That is a recipe for disaster. In my opinion, you should at least draw out a scale model. I always use graphing paper. In fact, I keep some right here on my desk. And then I've also got my iPad, which is a little bit further away from me. And that's what this drawing is. So if you get my laser pointer back. Here we go. This is a drawing I did for a parabolic mirror. This is a science project that I had to design a rig that would allow us to very carefully position a really heavy parabolic mirror. And if you look at the top, I just started sketching. I didn't erase anything. I didn't scratch anything through. I just drew the first iteration, then moved over, drew the second, and kept going as I was thinking through how I would hold on to the mirror, how I would mount it, how I would tilt it. And you can just sort of see the evolution of the design. And I ended up with a square tube column and some adjustable pieces that would allow me to slide this thing up and down. But the thing that I want you to take away from this is it can start very crude, right? Like these are ugly drawings. They're not to scale. They don't need to be. At this point, you're just trying to figure out kind of what the shape is going to be. Once you have that, then I strongly recommend that you start making it to scale. So on your graph paper, you can make each block worth a millimeter or a centimeter or a foot, whatever units you want to use, and then draw it out to scale. From there, you're going to step up and actually start cutting out some pieces. And again, I strongly recommend you make some kind of prototype, either out of wood, which is really easy to make. Wood is easy to cut with very cheap tools. It doesn't cost you very much to get into woodworking. But even cheaper than this is cardboard and a box cutter, and you can be right on top of it. And oh, look at that. I left a note on the screen for me. Cheap and fast materials, cardboard and wood. Another common mistake that I see beginners make is they make holes size on size. And what that means is if they expect to put a 1/4 inch pin inside of a hole, they make the hole a 1/4 inch. And again, that's another recipe for problems. Your holes should always have some clearance around it. Now, there's a book you can get called The Machinery Handbook, and it goes into great detail down to thousandths of an inch, how big that hole should be to get the kind of fit that you want. But again, if you're not an engineer, you don't need to do that. All you need to do is oversize it a little bit. I usually just, if I don't really care what the number is and don't care how loose it is, I just go the next drill size up, plunge the hole, and keep working. And that's a decent rule of thumb to get started with. As you get further along or your precision needs to be higher, then you might need to start thinking in thousandths of an inch to make sure that you get the right kind of fit. All right. I'm doing pretty good here. Know your raw material dimensions. I bring this up because if you're new to woodworking or even metalworking, the raw material that you get is not always the nominal dimension that it comes in. So if you go to your big box, store that's selling your lumber, you can walk up and it says 2x4, but it's not actually 2 inches by 4 inches. It's 1.5 inches by 3.5 inches. And so when you're designing your parts, you need to know that. As the part gets bigger, the dimensions actually change more. So a 2x10 is, I think, 9.25 inches instead, or it might actually be 9.125. Somebody will correct me on that. But the key is it's not 9.5. That number is getting smaller and smaller as the wood gets bigger. And you just want to be aware of what the actual dimension is so that you know how much raw material you're working with. And then now that you know how much raw material you're working with, you got to be sure you have enough material to actually cut out your parts and that you have enough raw material to actually work the piece. So this is more important with metalworking than woodworking. But if you are machining a piece, for example, you got to have enough not only to cut your part out, but you also need to have enough material left that you can hold it in your vise, or if it's in the jaws, whatever it is, you need to make sure that you've got enough material to actually hold on to the part while you're machining it. And then you can run into similar problems with woodworking, but not quite as often as machining. Again, one of those things to be thinking about during the design process. You don't want to think about this when you're already cutting out your pieces. This one is pretty important. It's a surprising problem, and that is when you're designing it, you have to make sure that you can actually assemble it. And here's what I mean. Like if you're using CAD software, for example, you can put fasteners anywhere. It doesn't really matter if there's actually room to put the fastener in and take it out, or if there's room to put a tool on top of the fastener and then tighten it down. So all of these are things that you want to think about. If you're putting nails in your piece, do you actually have room to swing a hammer and hit the nail? These are things that are really easy to overlook when you are a beginner and just getting started at this. So it's something you want to think about as you're designing it. Can I assemble this? All of the fasteners, if I want to glue this thing up, if it's a woodworking project, can I actually put clamps on it to hold it together while the glue is drying? Thinking about the assembly process while you're designing it will save you a lot of headaches along the way. And then don't forget the fasteners. But here, I'm not just talking about what I just mentioned earlier about how the fasteners will fit, but just thinking about them, the whole process of the fastener. whether you're going to have a nut on the back or not. Do you need threads in there? How long the fastener needs to be, and whether that full length fastener will still get in and out of place if you need to disassemble it. So just thinking through the fasteners as a separate thing from the whole assembly will also save you a lot of trouble. All right, a few more here. Check whether it moves freely. So this goes back to my prototyping. When I first built this, I noticed that it would actually stick. So the first iteration of this, I couldn't quite get it to tilt. Again, I was new to designing stuff like this. So I actually loosened up the holes, and I found that that gave me just a little bit more room to allow it to flip over. In the final design, I ended up adding slots there, which allowed it to slide back and forth during the movement. And that gave me just enough play to make it work fluently. So these are things you want to think about, whether you need slots or not, whether your structure actually has enough room to move. And then also, well, while we're talking about prototypes, you want to think about how it's going to withstand the load. So I would take the time to kind of push on the different sides of it, where the weight would be, and just thinking through what your loads will actually be. And I think we covered those two. All right. So moving on, shapes. Now, I'm showing you an I-beam because this really represents like the ideal material and shape, right? It's the perfect marriage of having a good shape as well as the right material. Steel is extremely strong, and I-beams optimize the shape of the material. That's why you see them used so much in order to withstand bending. But there's another element that I want you to think about here. So I'm gonna give you a second to look at this. And which one of these would withstand the load better? Would it be this I-beam or this I-beam? I'm expecting this to be a fairly easy question. It's the follow-up question that makes this a little bit more surprising. So hopefully you selected this one, right? This is what an I-beam is designed for. It's got the maximum amount of material lined up with the load. But here's where people make mistakes, including engineers sometimes, is your load is not always gravity. You can have loads on the side. So let's use a ruler, for example. If this ruler was my I-beam and I have it in this orientation, and then there's a load on it, you can see even this piece of steel starts to bow way more than I wanted to. And hopefully you wouldn't want it to bow this much either, unless you were designing a diving board. But if you rotate it this way, there's no bending at all, right? And it's imperceptible, the amount of bending. And that's because the load is in line with the maximum amount of material. But here's the part I want you to think about. Sometimes the load is not gravity. Sometimes the load is in the other direction. So if I had a load going like this, I've got the same problem, right? Rotated this way, it's still bending. So this happens when you are designing something that, say it was overhung and you had a motor here with a belt drive, then the belt actually creates a pulling force in this direction, and therefore your beam will bend. So under those applications, it might actually be better if it was designed this way to resist the load. So the key message that I want you to take away from this is think about the orientation of the load, and then that'll help you design a better structure. That way you don't make all your I-beams like this when the load is actually in this direction, is what I'm getting at. Probably a really good example that we can all think of, if you've ever assembled a bookshelf, then you know you can put the framing together first. And if you put something on it, it's probably fine. But if you lean on the side, it tips right over if you don't have the back on it, right? Because that back plate is what gives you stiffness in that lateral direction. Without that back plate in place, then your whole bookcase will collapse. And it's the same with all of your designs. If you design it in such a way that it can handle whatever load you put on it, whether you're leaning on your bookcase from the side or stacking heavy books on the top, it can stand up to the load in both applications. All right. All right, so I'm not going to dwell on this one too much, but this one is just a fun one, I think, both for engineers as well as those who aren't engineers. So I want to kind of differentiate between strength and stiffness. A lot of people think because they normally come together, we kind of think of them as being the same, but they're not. Like I'm using breadsticks here, because I think they represent stiffness in a way that makes a lot of sense to us. Even if you don't eat breadsticks, you've broken one before, and you know they're extremely stiff, but also very brittle. They have almost no strength. And rubber bands are kind of the opposite. They are not stiff at all. They stretch with even the slightest load, but they can be really strong. I mean, the thicker the rubber band, obviously, the stronger it is. So we have materials where we can see examples of high strength and low stiffness, and vice versa, high stiffness and low strength. Now, what does that mean to you? Well, different materials have different combinations of strength and stiffness. And so you want to think about that whenever you are designing your structure. If you're making like a fancy coffee table, let's say with a glass top, well, that glass, it has kind of medium strength, but it's extremely stiff and brittle. So if you put that glass top on a wooden table that's not designed to be stiff, then any flexing of the table can break your glass. So obviously we don't want that, right? Ideally, you want your materials to have similar strength and stiffness. But you can design your system in such a way that it can handle that. Remember what I said earlier about if you orient the material in the direction of the load, it'll be stiffer. You could do the same thing with your wooden coffee table. If you orient the legs in such a way that they're stiff in the way that they would bend under the glass, then you can keep that from causing any damage to your glass table. And then there's one more that I find really interesting, and that's the difference between steel and high strength steel. This is a problem that engineers, or this is an issue that engineers can mess up. High strength steel and regular steel have exactly the same modulus of elasticity. Now, I just threw a big word at you. All that means is they have exactly the same amount of flexibility. So if you have a steel structure like this with a load on it, and it's bending more than you like, then you might think, and some engineers think, oh, well, I'll just get some high strength steel instead of using this, replace it with a high strength steel beam, and then I'm good. And then you put the high strength steel beam in there and it bends exactly the same amount. It's going to slide off. Okay, it's good. It will bend exactly the same amount because they have the same amount of stiffness. So even though the high strength steel can handle a higher load, it's not any stiffer. And aluminum and rubber are just some more examples. Aluminum has kind of a interesting mixture. It's a little bit less stiff and a little less strong than steel. And then we've already talked about rubber. All right, we're getting to the fun stuff now. So that was a little bit about design, but let's talk about creating motion here. So there's several different ways that you can get your projects to move. Obviously, there's automatic motion, which is mostly what I work with using electric motors and pneumatics. We will maybe come back to this later, but this is an example of a pneumatic tube. If I wanted to get something to move, then you would hook up your air lines here, and with some electrical valves, you could push your load back and forth just by flipping a switch. So maybe we'll come back to this if we have time. I'll leave that there for now. But for DIY projects, you might be looking for manual controls. So perhaps a hand crank or just levers, rollers, whatever. Hydraulics can be kind of messy, but you can get a lot of power. So that's another avenue that's similar to pneumatics, but typically a little bit more expensive and requires more equipment. All right, let's focus on electric motors here for a moment. Let me turn that off. All right, I'm going to try not to use up all my time here because this is by far my favorite topic in the world. All right, two kinds of motors. Let's start with DC. Stepper motors fall under the DC category, although you can buy AC stepper motors. Stepper motors are really good for applications where you need very precise control of the position. These motors don't usually have feedback. In other words, they're kind of blind. You just send a pulse to them and they move forward without sending any information back. So if you overload them, then you can lose your position without knowing it. It's one of the downsides to stepper motors. But what makes them really good is, again, their capacity to very precisely control the position of your load. So if you have something that you want to move to 2 spots back and forth, then you could write a little program, set up your stepper motor, and it can hit those 2 positions over and over again, as long as you're not overloading the motor. Some of the downsides to stepper motors, though, is they don't go very fast. So their speeds are typically very low, like 1,000 RPM or less. And again, they don't have any encoder feedback unless you get a special type. So if you overload them, you can lose your position. Permanent magnet DC motors are probably the most widely used motors for small applications, for remote control applications. I'm talking about if you have ever taken apart an RC car, then you've seen one of these little permanent magnet DC motors. But they go all the way up to 1 to 2 horsepower. In some cases, you can get them to about 3 horsepower. But after that, the permanent magnets, you don't have the same economy of scale. You start to lose the efficiency. And they usually switch to a different motor type after that. But that gives you a sense of the range. If you're looking for very small motors, you want something that's portable, you can run it with batteries, that's the kind of motor you're looking for. They're usually very responsive to speed control. So they're a good option for projects where you need to be able to control the speed, and you don't need fancy controls for that usually. So that's what makes them a good choice. Brushless DC motors are a relatively new invention in the sense that they've kind of exploded on the market. It's not that they haven't been around, but now we see this huge explosion in the last several years of not only these high-end RC cars, but the explosion of drones. Those kinds of applications tend to have these types of motors. So they require a little bit more sophisticated controller. But again, because of the economy of scale, there's so many of these things out on the market, you can still get controllers for pretty cheap. Servo motors come in 2 flavors. There's this little tiny guy that, depending upon what you're used to working with, this might be what you think of when you think of a servo motor. But then there's the bigger one, like this one that you see down here in the corner. That is a 1 horsepower or 750 watt AC servo motor. And it's got a little gearbox on it as well. So this is usually what I'm thinking about when I say servo motor. So if you hear me say servo motor later in the video or in this conference, this is probably what I'm talking about. But there's also this little guy as well. Both of them are similar in that they give you very precise control over the position of whatever's connected to it. But obviously there's a huge difference in power output. These usually don't scale up to very large sizes or high speeds, whereas these you can get both. You can go both very large as well as very high in speed. All right, breaking down the AC motors. So if you're using an AC motor, your project is probably getting a little larger at this point. We're talking about possibly making your own power tools. At least that's the kind of project I'm usually thinking about when I think of AC motors. And this first one, the single phase induction motor, is by far the most widely available one. What makes this guy good is you can usually just plug it into the wall and you got 1,750 RPM or sometimes 3,600 RPM, depending upon which one you get. And so this is a good choice if you need very good speed control, good power, and that guy will give you good torque as well. The universal motor, so single phase motors, if you are scrapping motors and stuff, which is something I often do. Like if I see a treadmill on the side of the road, I might drag that thing home and take the motor out of it. So a treadmill will most likely have a PMDC, permanent magnet DC motor. But sometimes they have these 3-phase AC motors in them. It just depends on how new the treadmill is. This is kind of a recent trend. The single phase induction motor, you will usually find these in washing machines, dryers, at least here in the US. In other countries, you might see a universal motor in a washing machine. But so single phase induction motor, it's very common on power tools. So if you have a drill press or table saw, anything like that, it's probably got a single phase induction motor on it. Even your air compressor would have that on it. 3-phase AC is also an induction motor, but these are usually found in industrial applications. So these motors can be very large. We're talking about thousands of horsepower. It would be a 3-phase AC motor. So very good speed, very good torque. But if you're in an American household, then you're going to need a special controller that's going to take the power from the wall and convert it to 3-phase AC, which is what you would need. Servo motors come in a lot of different flavors. Some of them are DC powered actually, which could be used, which could fall into this category, but still be this type. But most of them are AC synchronous servo motors. That's a mouthful. And these motors are what you find on my robot arm. So all of the joints, all 7 or 6 joints in the freestanding arm are servo motors like the one that you see over here. And oh man, we're doing good on time too. We are almost there, people. All right, so sizing a motor, what do you need to do? Now, I'm spending a lot of time on this because I feel like if your projects are going to move, you probably have a motor inside of it. So I thought this was worth investing some time in. All right, how much torque do you need? I have talked about this in a whole bunch of different videos. And so I decided rather than try to ad-lib it here and possibly fumble it, I've got a nice edited version of this discussion from a YouTube video. And this is about a minute and a half, maybe. So I'm just going to play that for you rather than try to explain it live, since it'll likely be better. Let's try that.
Many of us have experienced the sensation of sitting on a seesaw with someone whose weight doesn't equal ours. Even kids, without thinking about it, intuitively adjust their position on the seesaw to try to balance out their weights. What you're actually doing is balancing out the torque. Torque is a combination of the force you're applying, in this case your body weight, multiplied by the length of your lever, or the distance to the center of rotation. These two variables are equally important. In this example, you can see we've got twice the weight on one side, being balanced out by a lever that's twice as long. Now I want you to think of this pulley as a lever, with the length of the lever being the radius of the circle here. The motor has a fixed amount of torque that it can put out. And just like we saw in the example with the seesaw, if you increase the length of the lever on one side, you're going to need to decrease the force in order for them to be equal. So using different size pulleys will give you different amounts of force output. But there's an interesting trade-off. Because the arc length here is much greater on this one, I've given up some force, but I've increased in speed. In fact, they're directly proportional. Putting this one on the motor will give me a lower speed, but more force output. Putting this one on the motor will give me a much higher speed, but a lot less force. Now that we have that foundation, let's take a closer look at the power formula. Here in the US, the horsepower is the customary unit, but I'll be happy to show you watts on the screen here as well, since pretty much everyone else in the world uses that. We're simply multiplying torque times speed and dividing it by a constant. You can also back calculate whatever variables you need. Let's take this motor, for example. We have both the horsepower and the speed, but we want to figure out how much torque this motor has. We can rearrange this formula a little bit, and you can calculate how much torque the motor is producing at that speed.
All right. So let's elaborate a little bit on that topic. Here you see an example of me trying to figure out how much power I need to rotate the handle on my table saw. This is a project that I did, and there's a YouTube video about this, where I fully automated my table saw. I made a touch screen, I wrote a program so that I could type in, okay, I want the fence to go to 40 inches, I want the blade height to be 2 inches, and so on, or I want the blade angle to be 45 degrees. You punch in those numbers, you hit enter, and then all of the various items will move to their right position. And that's what I'm doing here. So essentially what I did is I bought a fish scale, and that's what you're looking at, hooked it onto the handle, and then started pulling on the handle. Well, the fish scale is going to read out the force required to move the handle. So that's the first part of my torque formula. And then the second part is the length from the center of this circle out to where the hook is. So if I multiply this length by the force that's written on the screen, now I have my torque. And I know how much torque it takes from the motor to rotate the handle. That's all of the math I'm going to give you in this entire video. Measure the torque, actually, and you got to put that in another formula. So the next thing you need to know is how fast you want the thing to move. So again, for my table saw, I decided I wanted the handle to spin about twice as fast as if I was spinning it by hand. I picked that completely arbitrarily, just basically deciding that I wanted it to be faster than me, maybe by about 2 times. And that was all the decision that went into that. But of course, it depends a lot on what you're making, right? As to how fast you want this thing to go. But what's interesting about that is once you plug these into your formula and in using horsepower, you're going to divide by 52, and you'll get the units in horsepower. Well, now you know exactly how big a motor to buy. As long as your motor has the right amount of power, then you can use gears to get the right speed and torque ratio. So we'll come back to that idea here in just a minute. But now this is all of the math that you're going to need in order to figure out how big your motor is going to be. You can calculate torque by using a simple fish scale and a ruler, and then you can figure out the speed based on whatever performance parameters you need. And once you multiply those two together, you'll figure out how much power you need. And then, of course, I've got the little conversion from horsepower to watts since everybody else in the world uses watts and we like our customary units here in the US. I feel pretty comfortable working in both. So you'll hear me kind of intermixing the millimeters and inches and horsepower and so on. All right, so I mentioned gears. Well, I think the best way to think about gears is to just think of them as spinning levers. So this image here is a clock that I built several years ago now, and I used a whole bunch of different combinations of gears, but because mostly I just wanted it to be visually interesting. But I'm bringing this up because I had the full amount of power I needed to move all of these gears, but to keep time, I had to make sure the gears were all moving at the right speeds for their position. I've got a certain set of gears driving the hour hand, and then following that, I've got another set that's driving the minute hand, and their ratios need to be correct in order for the clock to read time. And that's all based on the ratios between their sizes, even though I'm using the same amount of power input for the whole system. So I want to go back to that illustration I gave you earlier, which is this lever. Now, if you consider this to be, think of this as a gearbox. And on the left side, we've got our gear input, and on the right side, we've got our gear output. Essentially, what you're looking at here is the side on the left has to move a greater distance, but with less force. And on the output side, we can move a greater load, but it's going to move a shorter distance, a shorter arc distance. That's the trade-off. Gears are only useful when you have enough power, but the wrong speed. I really want to be careful. I want to make sure I point out that gears do not add power. This is a very common misconception that people have. And I get this email all the time. Like, I'll have a system and I say, well, I need it to go faster. And then people will say, oh, well, can't you just use gears to make it go faster? Like, yes, but only if you have more power to make up for the additional speed. So this is why you don't see drag racers with drill size motors on the back and just a huge gearbox, is because it doesn't scale up that way. You have to add more power to increase the speed or increase the torque while keeping the other the same. But if the total power output stays the same, then you can increase the speed by giving up torque, or you can increase the torque by giving up speed. And that's the trade-off that gears give you. But doing either of those will not give you any more total power. Got it? Good. All right. And I got 8 minutes left on the clock. But so I do want to share one more thing about the pneumatics, and that is these guys have a lot of pros and cons. All right. So number one, when it comes to pneumatics,
I stopped your slide share to put you full screen, so you can start it again if you'd like. Sorry about that.
No, that's good. I was actually, when I saw the pop-up on this side, I had the same idea, but you were just doing it ahead of me. So that's good. Thank you for that. All right. So back to pneumatics. Here with pneumatics, you can get very fast motion. So if you need to move something in a straight line, pneumatics will give you very high speed, not as good position control, although there are a lot of options here and the more expensive options here in the recent past that have come out. But in general, you're not looking for a lot of precision, but you're just looking for one extreme or the other, then pneumatics will get you there. Very high speed, linear motion. And the only thing that you do need other auxiliary equipment. For example, you got your airlines, you're going to need a power, you're going to need your air compressor, filters to get the moisture out, things like that. So it's just something to consider that gears and motors aren't the only way to create motion. You could also use pneumatics. Hydraulics will be very much the same, except you're pumping fluid instead of pumping air, or a liquid fluid instead of air. And then I also grabbed a few gearboxes just to show you that they come in a lot of different form factors. This is called a harmonic drive. This is kind of a high dollar gearbox. Actually, I should have grabbed a cheaper one. But these guys give you a huge amount of speed reduction in a very small package. This is a 100-to-1 gearbox, and look how small that is. It's incredible. This one is 50-to-1, but this is a planetary gear, and these are rated for about the same amount of power. So that gives you a sense of how much difference there is in size. But anyway, you don't even really know, you don't need to know the difference between a harmonic drive and a planetary gear. What you need to know is that a harmonic drive will cost more, but they're much smaller and they're more precise. They don't have any backlash. And then planetary gears, these guys will be a little bit cheaper, but you know, they're larger. I don't want to say sloppy, but they have just a tiny bit more play in them. So I think I am ready to take some questions.
That was an incredible talk. Thank you so much. And we do have some questions from Discord. If you're watching and you want to ask questions, drop into the Discord Remoticon questions channel, and I'll try to harvest those. Jeremy, one of the really interesting ones that came up was someone said, I always struggle with understanding static force to get a motor moving versus how much force a motor can provide once it's at speed. What do you think about that?
Okay, so certainly there is a difference there, but for the most part, it's not a significant factor. And the reason I say that is because most motor types, pretty much all of them, well, that's not entirely true. If you're using the right motor type, and I have a couple of videos on this that I'd refer you to, there's one where I discuss, I can't remember the title right off the top of my head, but in the thumbnail, you see two motors there, like a big one and a small one. And I'm just basically comparing the pros and cons of each motor type. But if you watch that video, you'll see the ones that fit what I'm about to say. But for the most part, motors have all of their torque when they start. So that means that if the motor is still, and then you hit it with power, everything that motor has, and then even above its rated power, is available to push the load forward. So as long as the running load is not too high for the rated power, then you're usually okay, because the starting torque of the motor is usually enough to kind of get the thing pushed off. But if you want to be safe, I mean, like when I'm designing a system, I make sure that the rating of the motor is actually higher than whatever the starting torque requirement is. And that way you're way over in the safety margin. But you don't necessarily have to do that. When I'm doing my home projects, for example, I don't go through the trouble of that because that raises the cost a lot. You need a much larger, much more powerful motor for a higher load that only lasts for a fraction of a second. It's just that first 1 second where you've got that big spike that you need a lot of power to get the load moving. But then after that, the motor's just, coasting and it's easy to handle. So that question can get really deep. So I think I'm just going to leave it right there. But hopefully I can point you to that video that'll tell you what kind of motor you should be using for those kinds of things.
So you talked about dimensioning your materials. You also talked about elasticity and stiffness. But I'm wondering, how do you discover new materials? It seems like material science is its whole other thing. And what do you do when you're working on something and you find you've hit a limitation of the material you plan to use?
Well, generally what I do is I literally just, there's a website called Make It From. And well, I don't need to pull it up, but there's a website called Make It From, and there you'll see a huge list of materials you can do, put them side by side and see how elastic they are, how strong they are, what their breaking strength is, and things like that. And so that would usually be the place that I go. But I would caution you though, instead of making, how do I want to put this? I would be more concerned about the shape than the strength of the material. Remember earlier in the slide, I said that strength and that shape is just as important as strength. Very often your project fails because you've designed it like this when it should be like this. So if you can always keep that in mind, very often, I mean, you can certainly reach the limit of the material. There are applications where you need something stronger, but I would look at this problem first. Have you designed it shape-wise to be strong enough for the load and put the maximum amount of material in line with the direction of the load before you change the material? Because you can end up spending way more money on buying like this high dollar titanium when just a small change in the shape would have revolutionized your product. And for me, obviously, that's a huge deal, right? Because I'm designing these products for companies and they don't want their product to cost 10 times as much if I could have changed it just a little bit and allowed them to use a cheaper material. So steel is just readily available. It's in many cases, it's even cheaper than aluminum. So if I can make it out of steel, that's usually a better alternative. And I try to make the shape, I try to optimize the shape before I change the material.
So someone mentioned that high strength steel has the same modulus elasticity. What kind of strength does it win at?
Well, it depends on which one. You can get different grades of steel, and so you're going to have a different strength at each one. In some cases, you can get grades of steel that are 2 and 3 times stronger than the standard steel that you might buy at just your local dealer. But in terms of the modulus of elasticity, that's what I was talking about earlier, in the sense that it's just as flexible. So if the point is to make sure that this thing doesn't break, oh, sorry about that. So if you're just concerned about it breaking, then it's still making noise. There we go. If you're just concerned about it breaking, then you might switch to a higher grade of steel. But if your structure is too flexible, then it's not the steel, it's not the strength of the steel, it's the shape. So I think I answered that question. Hopefully I did.
I'm going to say yes. Another question that came in says, I've always seen pneumatics portrayed as dangerous because if the load changes, the actuator can extend instantly. How do you design around that?
Okay. I guess there's a lot of factors there. So it kind of depends on why your load would change and what other sort of systems you have in play. I don't think of pneumatics as really being dangerous, except the fact that because it's a high pressure system, I mean, it does move very fast when it moves. So you can mitigate that with a lot of different things. There are dampeners that you can install in your system, which will allow the air to come in or exit out very slowly. So when I was working with Destin at Smarter Every Day on the baseball cannon, we put a dampener behind the receiving end of the cannon. So this is I don't know if you guys have seen it or not, but this baseball cannon fires baseball at supersonic speeds. We're talking about thousands of miles per hour launching a baseball out of the end. And so there's a piston that flies back when the cannon is released because of all the enormous pressure we have to sling that baseball out of there. And we have to catch it, so to speak. So we're using a pneumatic cylinder. But that pneumatic cylinder, when it hits, there's a valve on the back that just sort of lets the air slowly leak out. And we're using it like a dampener. In this case, you would do that in reverse. You can make it so that the air coming in is dampened. And if your load suddenly shifts, then it can only move at a very slow speed. There are way more options than that, but that's just the first one that comes to mind. There's all kinds of little gadgets you can hook onto your pneumatics to control the position, control the speed, you can do all kinds of stuff with it.
There's an interesting question in here about three-phase motors. The person that's asking it thinks that you use three-phase in your robot arm, but whether you did or not, they're asking if there's a way to, how difficult or expensive is it to get a converter or like bake a converter into the design so that you don't need three-phase power always to power the machine?
Okay, this is a fantastic question. I love this. I am always building with industrial stuff. So three-phase is like a constant challenge for me. And there are two solutions that I have used most often. The first one is you can buy speed controllers that take single phase in and put three-phase out. So you are right. All of the motors on my robot arm are three-phase servo motors, three-phase AC servo. So they require three-phase power, but they're not plugged into three-phase in my shop. It's just plugged into 240 volts single phase. And then that comes into one single block that goes out to all of my servo controllers, and the controllers themselves actually break out that single phase into three-phase. Well, there's a lot of things happening, but basically it's turning it into DC and then breaking it up and then making it kind of look like three-phase AC. And that's what it's sending out to the motors. So, motors are dumb in that sense, and they just kind of move because they think they're getting the right signal, and they do what they're supposed to do. But so that's one method. The other method would be to get something like a rotary phase converter, which is another option that I have in my shop. But that requires like a capacitor bank, and a three-phase motor. So that three-phase motor will be hooked up to single phase. You have to kick it off somehow, which is something I explain in a video I have. And the video, I think, is actually titled How to Get Three-Phase from Single Phase. And so, yeah, I think I'll leave it at that. In that video, I explain exactly how to do it. But the short version of that story is you're going to need a three-phase motor, a bunch of capacitors, and a way to start the motor. And I'll explain all that in that video.
So it looks like we have two questions left. One of them is on motors and another on CAD. So on the motors one, when you're connecting a motor, do you have approaches that you like to use in your designs for the system to either slip or fail in non-destructive ways?
Oh man, I love that question. I got more engineers on this call than I expected, I think. Or it sounds like a question an engineer would ask. But okay, so by far my favorite method for transmitting power is with belts. And it's for this very reason. Number one, or this is one of the reasons, is because if you have a significant overload, that can be taken up by the belt breaking, and then your system is released. So it can fail safe in that sense. I'm much less concerned about a belt, breaking loose and whipping around. Usually I have belt guards and stuff too, but that's much less dangerous than, my motor driving a system hard or destroying an expensive gearbox or things like that. A belt's very cheap to replace. So it doesn't destroy your whole system. And then, so that's number one. Number two, belts are really cheap, and so are pulleys. And if you just think about it, it makes sense from a manufacturing standpoint. Making a pulley, it can just be cast and duplicated over and over again, where gears are usually machined and they're just much more expensive to make. So they're cheaper, they're easier to align. When you are setting your system up with a gearbox, it's got to be almost perfect. But with belts, you're supposed to align your belts, but even if it's 1 degree off, what you end up with is just wearing out the belt faster. Your system will still run. And again, because the belts are cheap, it's not a problem. So belt drive will be my go-to for systems where I want the motor to decouple in case of some kind of catastrophic failure. And again, there are other options, but that's by far my favorite. And if you go back through my catalog of videos, you will see that's the most common method that I use throughout my projects for those reasons.
Right. And the last one, you made a really interesting point when you were talking about design at the beginning. And I really appreciated the thought of like the fastener conundrum,
where
you've designed something and you can't then fit the fastener in there. So that kind of makes me think about like design rule checks for electronic CAD. Like, is there some kind of design rule check where you can assign lengths to the fasteners and have your CAD program warn you that you're going to be in trouble?
Not that I'm aware of. That's a fantastic question, but I use SolidWorks for 3D modeling, and there are a whole bunch of tools for checking for things like whether parts are interfering, whether you have proper clearances. You can have it checked for tolerances and fits, but I'm not aware of an option to check for clearance in the sense of an object being removed or placed manually. So there are even options for if parts are moving, will they hit each other, like collision detection while in motion? You can do that as well. But I'm not aware of anything that would allow you to check for something like that. To me, it's a combination of experience and prototyping. If you can, well, sometimes it's simple enough where you can just see it's obvious. I won't be able to get my hand in there and get that fastener out, or I can move the fastener back and then it's stuck. I can't get it out, or vice versa. I can't get it in after it's fully assembled. So, but while I'm talking about that, I do want to mention that it's easy to trap in both directions. And what I mean by that is you can have it where the fastener can go in at one part of the assembly, but then when it's complete, you can't get it back out. So you do want to think about it in all of the different states. Like when I mentioned how you want to make sure that your prototype can actually move and rest in all of the different positions and that it won't tip over or fall, that like moving this like this changes the center of gravity. So that's another thing to think about when you are making things that move, is how does the load shift around in all the different positions? So it will probably be helpful to just, for me, what I normally do is I just, think through all the positions it's going to be in. And then I try to check the things that have burned me in the past, like, oh, I trapped a fastener, or I didn't make this opening wide enough to get tools in, things like that.
Well, Jeremy, thank you so much. I mean, first of all, what I need to thank you for is that on your YouTube channels, you have spent so much time making sure that you go into the educational background of the thing and not just the building of the thing. And I know I've learned a ton from it, and I've heard from a lot of different people who are the same way. So that is awesome. Thank you so much for that. And making time to come and do this talk for all of us. It's been a real treat. I appreciate it.
Hey, yeah, thank you so much for having me. This has been fun.
All right, so we'll be moving right along in about 3 minutes to the Hackaday prize ceremony. Stay tuned for that. We will be right back.
Welcome back, everyone. My name is Magenta, and I'm thrilled to be announcing the 2021 Supply Frame Design Lab Hackaday Prize. This is our chance to reset the clock, reframe the challenge, to hack the future. Rethink the way we communicate through technology, design solutions for remote collaboration, create hardware that solves problems and invites the next generation of engineers, build electronic companions or robots for everything from support to functional assistance, or chase the wild card and pursue your own idea. Reimagine, refresh, rebuild. This is the Hackaday Prize, brought to you by Supply Frame and DigiKey Electronics. Be sure to stay tuned for updates. There's so many ways to engage, both online and in person. So gather your team, nominate your mentors, and get hacking.
Hello and welcome to the 2021 Hackaday Prize Award Ceremony. It's so nice to have you with us today. My name is Mike Stish. I'm editor-in-chief of Hackaday.
My name is Magenta Strongheart. I'm head of design and partnerships at Supply Frame's Design Lab. And I've been helping run the Hackaday Prize for the last couple of years. And it's been such an honor to be able to see all the amazing projects that come out of this initiative each year. This year, as you all know, of course, we asked you to rethink, refresh, and rebuild. And you all did that and so much more. And we're so excited to dive into these projects and announce our awardees very shortly. This is the second year that we've been entirely remote and virtual. And I just want to say that I really appreciate that. I don't feel we lost any momentum in the last 2 years, even with everything going on in the world. It's really just powerful to see our community still come together and continue to push the boundaries of open source hardware through the entries to the Hackaday Prize. So thank you all, and thank you to our broader Hackaday community, of course, and everyone joining us, tuning in right now. We're also excited to announce that we'll be having a Where Are They Now video series coming out shortly about some of the past Hackaday Prize winners, so you can see where their projects have evolved to since their grand prize winnings and their design lab residency. So keep an eye out for that. If you're tuning in, you already know our Hackaday YouTube channel, so be sure to subscribe so that you can get those notifications and check out all that awesome content when it comes out.
We'd like to take a moment to thank our exclusive distributor partner, DigiKey. DigiKey really believes in the vision of the Hackaday Prize and has been with us as a major sponsor since the very beginning, and we're so thankful for that. We're lucky today to have with us someone from DigiKey. I'd like to introduce Kevin Walseth to say a few words.
Hey, Mike, thanks for the introduction. It's great to be here. It's great to see everybody's faces. I think the Hackaday Prize is absolutely incredible. You know, there are so many reasons why we as DigiKey are so supportive of the Hackaday Prize. You know, the prize is always about building a better tomorrow, creating a future where technology and the world go forward hand in hand. DigiKey's here to be a part of that. We want to be a part of that. We want to fuel that innovation, because I don't see it slowing down anytime. Pandemic and everything, there's been no issues with innovation going further and further and further. Open source hardware is also something that DigiKey is built on. Our founder was a hobbyist, maker, engineer, and that happens to be our customer base. So as tomorrow's innovation continues to shift between platforms, hardware, software, any or all of those, we're here to support it every step of the way. And we wouldn't be here if it wasn't for everybody on this call having such amazing inspiration and projects. And I wish the best of luck to each and every one of you, and great work to everybody. And thank you to the Hackaday team for allowing DigiKey to be a part of this.
Thank you so much, Kevin. We so appreciate your support and DigiKey's support, of course, and we're really excited to get to our awardees shortly. So next we have, we want to give a moment of appreciation for all of our finalists. Of course, we're only giving out 5 awards today, but there's been some incredible entries across the whole year. And we were so excited to be able to support these finalists with an additional, $500 to continue prototyping and developing all the way up to the finals. So we have a top 50 that you're able to view on hackaday.io. If you search for Hackaday Prize 2021, You can see all these amazing projects, click through them, see what people contributed. And of course, also on that page, you can see all of the entrants. Over 500 people entered this year, and we really appreciate just how much enthusiasm came from the community, and we know all of the work that goes into all of these projects. So we just want to give a virtual round of applause for everyone that submitted this year and for our top 50 finalists that we're featuring here. I think we can give a little round of applause, even though we won't turn everyone's sound on here. But big virtual round of applause to our broader community and to these finalists. Thank you everyone who entered this year. And I'm gonna admit we have a new judge joining us as well really quick.
One of the real problems that you have when you say, hey, go out and invent something new and do something incredible is how do you look at that? How do you find people that look at that project and know how to judge it on its technical merit? And so we have been so lucky to have a wonderful slate of expert judges come on and share their skill and share their time this year to take a look through and come down to the final decisions tonight. I am also happy to say that if you look close at these slides of judges, you will see more than just one past grand prize winner from the Hackaday Prize. Thank you to all of the judges for coming in and helping with this. I think it's a really important thing, and we understand that you all have very busy lives, and it's appreciated that you've done this. Thank you.
And on that note, we also want to give a shout out to our awesome mentors. This is the third year we've done the mentorship program where we're able to provide one-on-one mentor sessions to our entrants. And thanks to these individuals for dedicating their time and expertise to this initiative. And again, it's really awesome always to see, as Mike said, past winners being involved as judges, being involved as mentors, and just continuing that cycle of support and community, which is really what Hackaday IO and the Hackaday Prize is all about. So thank you to all of our collaborators who have contributed to this year and past years. It really means a lot. And I know that it means a lot to the entrants who are able to not feel like they're alone in this prototyping and documenting phases that we all know can be incredibly challenging. So we love the support from all of our community members and especially our mentors and judges. So without further ado, we're gonna get right into our awards, sort of the moment we've all been waiting for, right? So first up, we have our 5th place award and winner of $3,000. I'm so excited to have this creator getting to be awarded this prize. Their project is very near and dear to my own heart. It's something that we are focusing on the design lab this past year and into next year. We're creating our own tools to try to address this challenge. But before I give too much away, I want us to hear more from the judges.
The reason why this stands out for me and why I think it is so critically important, it's almost impossible to overstate just how important this project is because it, as far as I can see, it appears to be an actual viable solution to the reuse of plastics. And having some kind of a system for reusing plastic without great expense, without a separate expense, not having to buy some extra thing that you don't already have in order to make use of the plastic, but instead making it something that is actually just, built in, it's a part of the machine. We're starting from that point. I think it's absolutely just fantastic. And as somebody who has, the other thing about it that just blows me away is just making stuff out of junk and getting it to work. And that's what I've seen in this project as well, which is, in my mind, the highest form of engineering. So fantastic work. Congratulations to the creator of the Direct Granules Extruder project. Seriously, this is a step towards saving the world. I don't think I'm overstating that when I say it.
Woo! Congratulations to our 5th place winner and winner of $3,000. I believe you're on the call. Many of you may know him as Homo Faciens, his YouTube channel and incredible YouTube personality. I will turn it over to you to accept your award. Give you just a moment to spotlight you as I find you in the list here.
Okay, so
Thank you, Hackaday. Thank you, DigiKey. Thank you, Supply Frame, for the prize money. It will, of course, be used to bring this machine forward and to hopefully bring granules to 3D printing and to remove the filament. So will be exciting weeks ahead to bring this to life and to make it ready for serious production someday. Hopefully we can see it on the market in 2022. Thank you.
Congratulations and thank you for joining us today, and thank you for all your awesome work and beautiful documentation of this project. I'm really excited to be able to access it for our own purposes at Design Lab, as I mentioned, and really excited to just see what the broader community does with this tool from here.
I am super excited about the 4th place winner this year because I think about the problem of making research more widely available. And if you think about citizen science and getting more people, I guess, casually or like a hobby involved in research, that's awesome. But if you can also outfit more labs with affordable equipment that works well, that is really a game changer. And so this winning entry found a way to bring together modular electronics with some custom designed glue to put them all together into a useful lab tool in an affordable way. Let's take a look.
This project proved the fact that electronics can be very affordable. The fact that it's small and handheld makes it be something modular that I can envision it going into some kind of bigger testing machine or learning tool that opens up a new idea or a new type of tester.
With the Raspberry Pi spectrometer, I was really impressed at how compact they were able to make it. The machines I'm used to are, desktop, bigger sized, refrigerator sized, and they got it really small and really cheap, and that's just best of both worlds. Congratulations, Raspberry Pi spectrometer, to see the impact you'll have on the world.
So congratulations to the Raspberry Pi spectrometer project. It looks like this project had a lot of hard work been put into it, so congratulations, and I can't wait to see where this project goes. I'll definitely be following it.
Raspberry Pi spectrometer, woohoo!
And I believe we have you on the call here. Give me just a moment to spotlight you.
Hi, thank you so much, guys. This is a huge honor. I can honestly say I've never won anything in my life, so this is fantastic. It's great to have recognition, and more importantly, I'm really glad that so many people have found this so useful. Where was I? Yeah, I was going to say this is a huge, fantastic honor. Thank you so much. I've never won anything in my life before, so it's really, really nice to have recognition. And more importantly, I'm really, really glad that people have found this project very, very useful. So thank you so much to Hackaday, DigiKey, and Supply Frame. I have no more words to say. Thank you.
Thank you so much, and congratulations. All right, next up, we have our 3rd place winner and award of $10,000. I'm really excited to share with you this winner. They really exemplified how good design can make something feel effortless, even though we know it's not effortless, and just really proves sort of the power of simplicity. Let's hear more from our judges.
This project potentially gives people without the resources to build large turbines or to have access to 3D printers. And I really love the way that decentralizes that process and gets more people working on this specific space.
The elegance of this design really shines in the way that the finished project is just beautiful. It moves in a really elegant way. The type of lighting that they're getting out of the electricity that they're generating is really kind of haunting and elegant. And that's just a byproduct of the actual design.
Congratulations to the flexible circuit wind generator. The work and design that went into this project was amazing, and I think a lot of people are really excited to see what's next for this project.
Congratulations, flexible circuit wind generator. Really beautiful, elegant work.
Congratulations. I believe we have you in the audience, so I'm going to spotlight you now. There you go. Congratulations on winning 3rd place.
Oh, thank you so much. It's amazing. Yeah, when I was a kid, my dad was always inventing and making things. He made a bunch of crazy things, a solar barbecue in our backyard. We would cook hot dogs on it. An ice sailboat that we would ride around on a lake near our house before deciding that was really way too dangerous. He showed me you could shoot very spherical fireballs out of a vacuum cleaner, and all kinds of nutty things like that. But really, he showed me that there might be a better way to do just about anything if you're not afraid to give it a try, and that even if you fail, you can learn and enjoy so much in the effort. So thankfully, my wife also came to understand that philosophy after about 20 years of messing around with plastic and foil wind generators on our kitchen counter. But anyways, thanks very much to Supply Frame, DigiKey, and Hackaday for supporting innovation for anyone who's willing to give it a try. Innovation is what makes the world get better and better over time, and this contest is helping make anyone into an innovator. Thank you very much.
Thank you so much. We always love to hear where people get their sort of, hacker innovator spirit. It's great to hear when it's passed down through family members and passed on throughout the community and friends and connections. So thanks for sharing that story, and we're excited to see where this project goes.
I've got to say, it is so cool after watching all these projects this year to get to hear these personal stories about the people that are making them. I'm really having fun because of that. Looking at the video from the judges on the last one of the things that Clarissa said is that these projects are getting people to work in areas where we need more people working in them. And I think the 2nd place winner is another one just exactly like that. Looking back over the last few years, I think it's pretty easy to look into the future and see that there's going to be less and less in-person events and more remote things. And one side effect of that is people aren't interacting with other people quite as much. And one of the ways that solutions have been kind of envisioned for that are through companion robots. It's kind of a newer area, and you may have even heard it called cobots. This 2nd place winner is bubbling up that idea and doing research in that area. Let's see what the judges had to say.
In an elegantly simple way, mimics the kind of expressions that we're used to seeing on human beings. It's so powerful. And I think putting that kind of ability, that sort of design ability into people's hands is just so powerful.
An amazing number of people have actually gotten involved and done something with it. And that actually, from that point of view, it's totally a success. He has somehow managed to get other people involved. And that's a really difficult thing to do because everybody's working on their own project. I'm not sure how we manage that, but that's really impressive.
That takes this really sophisticated aspect of robotics and puts it in the hands of people who are coming to it from a tinkering perspective, or coming to it from a way that is not a traditional path into robotics. So I think that this is really powerful, and I'm excited to see how people would integrate this into their projects. So congratulations to StackChan for winning this award for your excellent work. I'm excited to see where this goes.
It's a JavaScript-driven super kawaii robot called StackChan, and they are the winners of the 2nd place this year and $15,000.
Thank you so much. I'm not a native English speaker, so I prepared a script. I'm glad I didn't have to trash it. Thank you, Hackaday Prize, for giving me honorable 2nd award. First of all, I'd like to thank all members of the worldwide StackChan community. Without your passion and creativity, I wouldn't be standing here. Actually, I'm sitting now. And next, I'd like to thank Jimmy Rai and the M5 Stack team. And thanks to Peter Hardy and the Modular SDK team, I couldn't have achieved the concept of a cute robot that runs in JavaScript without the help of the excellent devices and frameworks. Thank you, Hackaday, for giving me the opportunity to share StackChan with the world. And Finally, I'd like to thank my wife and 3 children for their patience. I have dedicated almost all of my non-work time to Structure. The kids have been Structure's best playmates. Also, the most strict reviewers of new features. They can easily detect childish tricks. They get bored so easily. I put a lot of effort into how to keep them happy. Okay, so I will continue to spread Structure all over the world. I will continue to develop Structure so that it does not end up being a movement. That's all for now. Thank you very much.
Thank you so much, and congratulations again. All right, the moment we've all been waiting for, our grand prize, winner of $25,000 and a design lab residency. This project, I think, really just shows off how open source technology can make something that's super challenging much more accessible, and really push the bar on design and engineering and how something can fit into a beautifully designed user-friendly package. So without further ado, let's hear from our judges.
So an Arduino for pneumatics, I mean, that right there is just enough to sell it to me. Because I've had to do quick prototypes in pneumatics before, and it's never easy. You gotta have to go and like find all the right components. There's tubes, there's pumps, all electronics. It's hard to make it digitally controlled. Super useful, and if it's a need, that's definitely there on the market.
I loved how the creators behind this project openly talked about inviting people to collaborate in the project page. That was so amazing to see, just that sort of open invitation for anyone who believes in the vision to join them.
And not only have they obviously solved the problem completely, but they've solved the problem with polish. It's beautifully documented, beautifully done. It's far smaller than I would have imagined that you could do that and still have sufficient power. And yet there it is.
Congratulations, Flow.io, for being the Hackaday Grand Prize winner.
Congratulations to Flow.io. You have brought great credit upon yourself, your university, and your team.
Congrats to Flow.io. This is an amazing project. I'm super excited to see how the Hackaday community runs with Flow.io.
Congratulations to the Flow.io team. Woo! Woohoo!
Dear Hackaday community, I'm absolutely thrilled that Flow.io was selected as winner of the Hackaday Grand Prize. I would first like to say special thanks to my closest collaborators, Haejun Yoon and Ozgun Afsar, to my advisor, Joseph Paradiso from MIT Media Lab, and to all the other donors and contributors listed on the softrobotics.io website. Without your help, this project would not have been where it is today. My mission is to make innovation and prototyping in emerging fields seamless and easily accessible to people from all technical backgrounds through the creation and deployment of novel development platforms like Flow.io, which has now been used by people in multiple countries. And I'm incredibly grateful to the Hackaday jury for selecting Flow.io as winner of the Hackaday Grand Prize. This award would greatly help with our development and deployment efforts, and to ultimately enable more people to realize their creative project ideas with this technology. Thank you.
But we really appreciate all of their contributions to this project. I think it's really, as we heard from our judges, going to be such a game changer in the world of hardware, with pneumatics having a platform that makes that easier to take on and easier for people to build off of is just hugely impactful. And we're really excited to continue to work with Flow.io through their residency next year and see the Hackaday community continue to build off of this incredible innovation. Maybe one more round of applause for Flow.io and for all of our awardees. Woo!
So Magenta and I were on a test run of the prize ceremony yesterday, and she mentioned that this is the 8th year of the Hackaday Prize, which I cannot believe. It seems like it's such a huge mountain to climb every year, but there's a huge turnout from the community, and it's over before you want it to be. And one of the things that has always made this possible is SupplyFrame. Steve Flagg founded the Hackaday Prize back in 2014. He's of course the CEO of SupplyFrame, and every single year we've seen an incredible amount of excitement and support, and really anything that we need to get people involved in the Hackaday Prize, to bring in judges, to pull everyone together. SupplyFrame has always been there for us. So thank you so much for making the Hackaday Prize possible.
And on that note, of course, we have to again thank everyone that's involved in this incredible community. We have such a diverse group of makers, designers, engineers, hackers, scientists, and everything in between. And it's really you all that keep this initiative going. And I also want to, of course, thank again our exclusive distributor sponsor, DigiKey, for continuing to support these awards and this initiative and give funding to these projects that really make a difference in open source hardware and in the lives of one another. It's always so incredible to just see the time and curiosity and dedication that people put towards these projects, not only taking an idea and making it into a reality and building something physical in the world, which we all know hardware is hard. It's not easy to make something that has to work and look good and help other people use it with no problem, ideally. So thank you all for continuing to do that, and also to support one another. Something that really just warms my heart every year being involved with the Hackaday Prize is seeing the way you all continue to push each other and challenge each other. As we mentioned, it's been, you know, a difficult couple of years, and moving this all online, we weren't sure, you know, exactly how it was going to go, but there's been no bumps in the road. It's incredible to see just everyone continue to want to support one another and build something that helps their neighbor out. You know, it's not easy to think about something that's going to be socially impactful and really make a difference in the lives of others, but you guys continue to raise the bar and really impress us and inspire a broader community of individuals to get involved and make a difference in their community. So thank you all. So exciting to wrap up the 8th year of the Hackaday Prize, and I'm really excited to see what everyone brings to the table next year. So get those tools warmed up and those ideas bubbling, and we'll see you on Hackaday IO.
All right, everyone. What an exciting conclusion to the Hackaday Prize. I am so happy for Flow.io and all of the other winners. And Angie, I'm so happy for Remoticon.
I know, we made it. What a fantastic couple of days we've had. But it's not over yet. We do have the after party with a live set from DJ Jackalope. She'll be streaming on Twitch, and please continue to socialize on Discord. Links for both are in the description of this stream and at remoticon.io.
I can't express enough how thankful I am to the speakers. We learned so much from each other, and at some point, it's great to give back and to show the things that we've learned and help other people that are coming up. And each one of these speakers took a huge amount of time and effort to put together their talks, and they're the reason that we were all together this weekend. Thank you so much. Go on social media and show them some love, send them emails if you know them, follow their YouTube channels, support them because it's amazing. And you know what? Consider giving your own talk. We will do events again, and we'd love to hear from you. I want to give a huge thanks to Angie Weiss-Gamel. She jumped in about 4 weeks ago, short notice, and picked up and did great organizing for this conference. Angie, thank you so much.
Thank you for having me.
Tom Nardi, contributing editor at Hackaday, he jumped in without being asked and got the Discord channel going and figured out the bots and made it a really great place and spent a ton of time on it. I think it's been fantastic. I've had a ton of fun over there. Thank you, Tom, for that. Alexander Bradish designed the conference art, and he's designed the conference art forever. If you've seen those beautiful Hack Chat posters that come out, he's designed all of those, and it really makes this feel more like a super conference where we have the generative video, and I just love having that kind of like up the ante branding. Lewin Day put together an incredible hacker trivia last night. I hope you were there because it was a ton of fun. I loved it. I know Angie was playing. She didn't know the answers, so it was okay.
No, Chris bailed me out.
Lewin also had great help from Justin there. Thank you to both of them. If you did watch that, you definitely thought the musical interludes were awesome. That was, of course, Rich Hogben, who I always think of as the soundtrack of Super Conference. To help take us back there, he made a bunch of tracks that's still available for watching. I think we're going to ask him if we can just publish those to the Hackaday YouTube as well, because they're amazing. I want to thank the wonderful Hackaday writers, because day in and day out, in the middle of the night, on weekends and holidays, we are bringing you fresh hacks every day. We are bringing you an article every 3 hours, and we cannot do that without amazing dedication from all of the Hackaday writing staff. I also want to thank the Hackaday writers who came on and did MC duties to introduce people. I think most of them, I said, hey, you should think about, writing for a living, because you did a great job of writing intros. I mean, it was just wonderful, interesting things to say about the speakers, which I think is how we should celebrate people who go to the trouble of speaking. So thank you to all the MCs for doing that. And of course, you just heard me talk about it on the Hackaday Prize, but I'll talk about it again and again and again. We have such amazing support from SupplyFrame and, of course, from Siemens for this community. And so always making it a priority for us to bring things that build the community and make the community better. Thank you so much to SupplyFrame for making that possible and making it a priority. Of course, I think it's everyone's priority to get together in person for SuperCon next year. So we're going to do everything we can to make that happen. Thanks for supporting Remoticon. And I think that's all the thank yous, Angie.
No, you forgot one, Mike, which is one last final thank you to our fearless leader this weekend, which is Mike Stish himself. He truly did it all this weekend to make sure that the rest of us had an optimal experience. So don't be afraid to tell him what an awesome job he did in Discord. GIFs are welcome and even encouraged. But with that, I do think Remoticon is a wrap. So we hope to see you at the after party. It starts right now. Good night, everyone.
Good night.